Hello, everyone, and welcome to 8KB. We have 5 amazing sessions for you today with 5 top-class speakers. The first session is kicking off in about 15 minutes, but up until then, we have just a little bit of information about our event. My name is Andrew Prusky, and I'm here with my co-hosts, Anthony Nocentino and Mark Wilkinson. Hello, chaps, are you there?
Yes, we are.
Hello, how's it going, everybody?
Good morning, good morning, good morning. Excited for today?
Yes, and nervous. Like
Nervous.
I said, even though I'm not presenting, I'm just going to be here hanging out. But
we've done this before. Why are you nervous?
I have no idea.
And the second you stop getting nervous is the second you stop doing it. So, yeah. Okay, so that's our team. The 3 of us will be here all day. I wanted to talk a little bit about why we put this event on. 2020 happened and in-person conferences aren't going to be a thing for a while. So we wanted to put on a virtual conference. And we had a look out there, and there are loads of great virtual conferences out there at the moment, but we did notice that there was a gap in those conference offerings. Specifically, no conferences that provided high-level, level 300 and above, in-depth SQL Server internals content. So that's why 8KB exists, to provide level 300 and above content into SQL Server internals. And we're allowing our speakers to really dive into their content, so to go as deep as they want and go absolutely demo crazy, because that helps us SQL Server folks expand and improve our knowledge. And I don't know about you, but I kind of need a refresher on these courses every now and again, the new stuff that's coming out with SQL Server all the time, and the old stuff that I haven't revisited for a while. And we get some really, really good content with this conference. And of course, we want to have some fun as well. We don't want this to be a dry, boring technical conference. We want people to get involved. So we have Q&A. Please ask the speakers questions, and also get involved over on the 8KB channel in the SQL community Slack. So here's our schedule. Kicking off in about 15 minutes, we have Amit with SQL Server Memory internals and troubleshooting. Then at 15:45 UTC, we have Bob with the ins and outs of SQL Server data compression. 5 o'clock, we have Gail with intelligent query processing. What's up with that? And at 6:30, we have Klaus with Latches, Spinlocks, and lot-free data structures. And then finally, rounding off the event at 8 o'clock UTC with Thomas with scaling SQL Server beyond 2 CPUs. 5 amazing sessions, 5 great speakers. And I want to take a moment now just to say thank you to all our speakers, because we can't put this conference on without the speakers. So thank you for coming today and delivering your sessions. We also want to say thank you to our amazing moderators, our awesome volunteers. Without them, we can't put the conference on either. They're going to be helping out with the QA and in the SQL community Slack. So I want to say thank you to Angela, our Janice, Ben, Erin, Joey, John, Matt, Ree, and Rob. Thank you so much for giving up your time and helping us out today. Got some links for you. All the speakers upload some content to our GitHub channel. So if you want to grab the content after today, please go to that link there, github.com 8KB 2021-January, and you'll be able to pull the stuff down and have a look at their content. We've also got a YouTube channel where we will post all the sessions and the full event up to after Mark gets his act together and does some editing for us. Cheers, Mark. We also have all the old conferences there, so there's a load of great content on our YouTube channel. We've also streaming this live to YouTube at the moment, so anyone who don't want to use the Zoom link can also view the content there. We've got our webpage, 8kb.online. Loads of great content about our conference, and we're on Twitter as well at 8kbconf using the hashtag 8kb. If you want to talk to us directly, we're more than welcome to send us an email, info@8kb.online. Just tell us, you can give us some feedback if you like, or just get some information about when the next conference is coming up, things like that. We'll do our best to get back to you ASAP. Then we have the SQL community Slack. We don't have chat in Zoom this time. It's all going to be handled in the Slack, and I'll post a link to how you can sign up there if you haven't already done that. And then finally, probably the most important link on this slide is the event feedback. If you go to 8kb.online/feedback, you will see a link to the total event feedback and the individual speakers feedback as well. Please, please, please do go ahead and leave us some feedback. We want to make 8KB as great a conference as possible, and we can only do that if we hear from you. So please go there, tell us what you like, what you didn't like, any general comments, and we'll take those on board and we'll make 8KB as great as it possibly can be. So I mentioned the SQL Server Community Slack sign up. If you haven't already done that, please do go to dbatools.io/Slack, and then you can sign up, and we're all hanging out in the 8KB challenge, channel even. That's where we'll all be hanging out today. Please do get involved. We can have a chat about the sessions, about the event, and generally mucking about a little bit. If you like what you see with 8KB, we actually run a monthly podcast. We get top speakers from the SQL Server community to come on and talk about some individual topic in the SQL Server community world. So we've got things like we've talked about virtualization, statistics and indexes, high availability. And last month we had Bob Ward and Anna Hoffman on talking about Azure SQL. So there's a load of great content on that channel. You can view it on YouTube or wherever you get your podcasts. Please do go ahead and check that out. And the final thing I've got for you is we are 100% community funded. We don't have any sponsors. Everything is funded through either ourselves, or if you want to help us out, you can buy a t-shirt on bonfire.com/mixedextents, one of these awesome ones, if you can see that. And all the proceeds from selling those t-shirts will go straight back into the event, basically paying for our Zoom license so that we can continue putting this conference on. Okay, so that's about 5 minutes in. We've got about 10 minutes to go, and we've got our first session with Amit with SQL Server, SQL Memory internals, and troubleshooting. Should be a really good one. So we've got about 10 minutes to go. Please do go ahead, get a cup of tea, cup of coffee, get yourself settled, and we'll be kicking off with the first session in about 10 minutes. Amit, you there?
Yes, I'm all set.
He's all set, good to go. Right, so we got about 10 minutes to kick off. Really looking forward to this one. This is SQL Memory internals is something I learn it, and then all of a sudden it goes a little bit fuzzy and I have to go back and revisit it. So I'll be definitely checking this out and grabbing the recording once you're done.
Is this where we awkwardly chat for 10 minutes?
We can talk about anything you'd like, Ben.
Yeah, you can be as awkward.
Oh, don't go down that rabbit hole.
No.
And for
Hello,
anybody
Rob. I can see you've just joined there as well.
For anybody that missed the t-shirts, because I don't know if it showed up on the screen when Andrew was talking because he's sharing his screen. I've got one on as well. You can take a look.
Oh, yep. There we go. Looking good, Mark. Looking good.
Head on over to our store and you can pick one of those up.
Mine hasn't arrived yet, so boo.
They are based. It's a third-party hosted site, so we have a question in the Q&A already about the t-shirts. I don't know, Mark. Could we offer it in the EU, or is it just Americans based?
I think. I mean, you ordered them, so I'm assuming.
I think it's more for a shipping thing.
Yeah.
But, yeah.
I'm not sure. I'm going to contact them and find out.
We will find. So we will find out for you. They're very nice, mind. I do like these. But if you have already bought a t-shirt, we want to say thank you very, very much. We've used it to pay for the Zoom license for this event, basically. It's the only expense we have, really, other than hosting the website. So thank you so much if you've already bought a t-shirt. And now it's the awkward bit where we all sit here going, okay, maybe 15 minutes at the start of the event was a little bit too long.
Could have been 8.
I got to 8 minutes. I got over halfway. That's not bad.
No, you did.
I mean, this is basically where you could tell the story to everyone, where your Windows just booted you into default settings minutes before the event.
Oh, God, yeah. Don't muck around with the camera settings 10 minutes before a live conference. No, yeah. It froze my Zoom up, so I rebooted and it kicked me into the default Windows profile instead of my actual profile, which I've never seen it do before. So, yeah. I think I've just about stopped panicking from that.
Dear default salutation.
Yes, we've got a comment in the Slack channel saying, say thanks for posting the items in GMT instead of we used Eastern Standard Time for the first event, which I don't know why we did, Mark, but that just confused everyone.
Because that's the time zone I'm in.
So Andrew, how do people make donations to 8KB without buying a t-shirt?
We don't have a Patreon. We have talked about it before, but we don't want to just take cash, really. We'd like to give something back. So we're only offering the T-shirts at the moment because we have minimal costs. Really, it's just our Zoom license is the one thing. So thank you for the offer, but it's just.
I was going to say I do love the question though, because I mean this is really showing how this community is trying to get to give back, and I mean, even if lots of people only give lots of small amounts, it goes a very long way. So seeing questions like this, and also initiatives, not just like this conference, but was it 2 weeks? I think it was 2 weeks ago. There was this conference, MVPs for Croatia, where a couple of MVPs made a conference that was not free, unlike most online conferences. And all the proceeds were going to the victims of the earthquake that hit Croatia at the end of December. So seeing all that stuff there, this reminds me why I love this community so much.
No, it's absolutely fantastic. That was the community rallies around things like that. It makes you really proud to be part of it. Absolutely. Okay, we've got a lot of people jumping into the Slack channel, which is awesome.
I'm gonna have to put that on the big monitor because it's moving pretty fast, right?
No, yeah.
I turn the monitor up this way around.
Right.
Okie dokie.
Got lots of familiar faces in the Slack channel. So good to see you all out there.
And on Zoom.
What's that?
And
Zoom?
Not just on the Slack channel, but also on Zoom.
Thank you to anybody that is joining us where it is extremely early in the day.
Time zones are difficult. Yeah.
Yeah, or late. It's hard to schedule a conference at a time that makes sense for everybody. So thank you, everybody.
Hey Anthony, we got 3 minutes left. Do you want to give a TED talk on time zones?
TED talk on time zones. Well, I'll tell the story if you want to. Well, Ben and I were presenting our pre-con at Pass Summit this past year, and I had a spreadsheet up with all the time zones, and everything was fixed on Eastern time because that was what the conference had chosen. And so I present and I finish and I look at my clock and I'm like, cool, I'm right on time. And Ben's like, no, you're exactly 1 hour over because I presented against Central time and all the times on there were in Eastern time. So we had to do some creative rescheduling for the rest of the pre-con. I think we did okay. So
good work, Anthony. Victoria, I think that story completely explains why you should not put all of us into a pub to then give this amazing conference, because with time zones and alcohol, it would be a disaster.
I mean, basically what Victoria is describing is data grown.
Only the sun will make it to the end. That's definitely data grilling. So Ben, when is the next data grilling due to happen then?
Well, we canceled for this year, and due to a couple of constraints, venue and so on, there will not be anything later in the year. Also, I mean, late spring is just nice to have a nice barbecue out there. We're not planning for a winter grilling. So from what it looks like right now, May-ish 2022, also depending on that if or when that medieval festival will be happening, if they postpone it, if they eventually cancel it, because if they cancel it again this year, it will be, well, 2 years from now anyway, so because it's every 3 years. So yeah, we will see. All right, with 1 minute to go, shall we get Amit to share his screen?
Yep, Amit, do you want to grab sharing? Do you want to take? I'll stop sharing mine. If you want to grab everything.
There you go, it works.
There you go.
Excellent.
That looks fantastic. We'll give it another minute. Oh no, we're at quarter past.
It is
so
quarter past. So
Amit, take it away.
Thanks, Andrew. Hello, everyone. Welcome to another edition of 8KB Conference. It is such a great initiative by Mark, Andrew, and Anthony and truly excited and honored to be part of this conference and kickstarting this in the year 2021 with the first session. So welcome once again. Special thanks to Ben Weisman for helping me moderate this session. Basically, the organizers did not give him much choice, so he had to go with my session. My name is Amit Bansal, and I'm going to try melting your brain with SQL Server memory, internals, and troubleshooting for the next 60 minutes or so, maybe 75 minutes, including Q&A. So let's get started. You can find all the event and session resources, not only 8KB, but even past sessions that I've done on this URL, bit.ly/SQL Maestros resources. We have a small YouTube channel as well. YouTube is not small, but the channel is small, which is youtube.com/SQL Maestros. And you can connect with me here, bit.ly/connect with AB. I'm on Twitter, A_Bansal, in case you wish to tweet. Quickly about my work, some credentials from Microsoft, which is I'm an MCM for SQL Server, MVP for a couple of years, also regional director. I work for SQL Maestros, which is my full-time job, consulting, training, video courses, and stuff. And on community front, I work with Data Platform Geeks, SQL Server Geeks, and Data Platform Summit. That's about myself. Before we begin, quick warning. There are going to be a lot of demos in this session. Do not try these demos on your production boxes or on your stable machines. You may want to play around with all the scripts that I'm going to share on a VM, a throwaway VM or something like that. SQL Server memory is convoluted, and I say this with a lot of responsibility because I have been working and trying to investigate about SQL Server memory over so many years, and I know so many people from the community have been doing that. And what we have realized that it is, of course, complicated if you dive more deep into memory and trying to figure out every arithmetic, every number that you see flying in the DMVs is really not quite practical. So the warning here is that we'll go deep and try to satisfy your intellectual curiosity. But at the same time, we got to be practical. So what I have done in this session, in these 75 minutes, I'm going to definitely cover SQL Server architecture, the memory portion up to level 300, 400, and then focus a lot on practical demos, because that is what you really want. You want to take away something that you can apply in your production, just not theoretical stuff. So that's what I am going to be doing. So first up, we will not talk about all the architectural stuff. SQL Server memory internals is huge. It is absolutely very huge. All the possible memory scenarios. There could be a lot of different scenarios, internal memory pressures and external memory pressure. We are not going to cover everything, but I'm going to cover a few of them along with demos. And of course, bunch of perf mount counters and DMVs. And of course, these 75 minutes is not going to be enough to cover all of them. We'll cover important ones and important attributes from those DMVs. And of course, the Microsoft documentation is the place where you should go to figure out more scripts. What are we going to talk about? We're going to quickly cover NUMA, because NUMA knowledge is important before we dive deep into SQL Server memory architecture. Then, of course, I will cover, I have a slide where I have a lot of details about SQL Server memory architecture, and I'm going to give you a pictorial representation. We will look into memory usage tracking. How can you track where memory is being consumed inside SQL Server? That is a very common question that I see across all forums, that SQL Server is hitting up all the memory. It has hogged up all the memory that has been allocated to it. Where is it being allocated? And we'll try to figure that out. We're going to look at least 2 or 3 memory pressure examples. So without really devastating my VM, I'm going to create out of memory exceptions, and we will see how we can troubleshoot them. And of course, loads of demos. So what are your takeaways? Your takeaways are going to be better understanding of how SQL Server memory works and how to approach troubleshooting. Simple stuff. And we will do level 300, 400 stuff in a simplified way. So let's get started. And first, as we get started, let's get NUMA out of our way. Back in the days when we had symmetric multiprocessing systems, if you look at the diagram there, the illustration, we had a single memory controller. And when you are scaling beyond 2 to 4 CPUs, CPUs need memory. And when you had a single memory controller, all of these CPUs competed for this memory controller because they all needed memory. So there used to be huge amount of congestion at the memory controller. To elevate this contention at the memory controller, we have this architecture which is called as non-uniform memory access or non-uniform memory architecture, where the memory at physical layer, at the hardware level, is divided into NUMA pods. Yes, the word is pods or NUMA groups in simplified way. So if you look at the architecture here, there is a simple illustration of, let's say, a 32 GB box being divided into 16 GB memory NUMA pod 1 and another 16 GB memory controller 2. And then based on these NUMA pods, even the CPUs are bifurcated by NUMA. So it's just not the memory bifurcation, it is also the CPU bifurcation. And remember, this is not logical, this is physical. Now, CPUs in a specific pod have access to their own memory controller. So NUMA node, and we also call this as node, to be technically more clear. So in this diagram, you can see there is NUMA node 0 and NUMA node 1. So CPUs in node 0, let's say CPU 0 to 3, will access the memory controller of NUMA node 0, and CPU 4 to 7 will access the memory controller of NUMA node 1. With this, what happens is NUMA at bottom line is what is NUMA really helping with? Faster access to memory for the CPUs. At the core, this is what NUMA really helps with. And you can, of course, reconfigure it using soft NUMA, etc., which is beyond the scope of this session, but just calling this out. Now, what are the guiding principles about SQL Server memory architecture? First, dynamic acquisition and freeing of memory, mostly automatic. Now, SQL Server memory is designed to be automatic. You have a few knobs and switches, but mostly it is managed automatic, which is as you keep running workloads, as SQL Server is accepting more connections, requests, more queries, SQL Server will keep asking Windows for more and more memory. This is dynamic allocation. We are going to dive deep into this and explore more. But yeah, dynamic allocation is going to happen. And when at certain point, let's say if Windows is short on memory, it sends low memory notification to SQL Server, and SQL Server may start releasing memory back to Windows. So if you can see, this is dynamic allocation and dynamic deallocation, and mostly managed automatic. But you do have a few switches like min memory, max memory, and a couple of more settings that that can help you to control a bit, but then at very basic level. The second guiding principle is minimize physical I/O and maximize buffer pool. Buffer pool is one of the most important memory consumers in SQL Server. It has only one job, which is to ensure that there is enough data cache to load the data pages from disk into memory. We all know that physical I/O turns out to be quite expensive, and SQL Server will ensure that physical I/O is least so that everything is there in memory as much as, and that's one of the reasons why you see when you allocate more and more memory to SQL Server, it just eats up everything. And if you run some of the scripts that I'm going to show you, you will see that in most cases, buffer pool is one of the largest consumers of memory. So the objective of SQL Server memory controller here is to minimize physical I/O. But at the same time, if you look at point 3, to keep a check on buffer pool size to avoid system-wide memory pressure. So point 3 and point 2 is kind of contradictory in nature. This is where SQL Server tries to strike a fine balance between ensuring that buffer pool size is good enough, yet not so large so that it causes or puts pressure on other memory consumers. Remember, inside SQL Server, there are many components that ask for memory, and they do that via clerks. We will talk about that. And because buffer pool is one of the largest consumers, SQL Server needs to ensure that fair amount of memory is given to all other consumers and clerks. Lock pages in memory. You have heard that this is one of the best practices to kind of turn it on so that you run in locked pages memory model of SQL Server. But that was really a lot required in 32-bit systems. Today, I'm going to focus solely on 64-bit system. And in 64-bit, you may not turn it on because in 64-bit systems, by default, Windows does ensure that the memory addresses of SQL Server are locked in pages. But if you see those errors coming out in error logs, a significant part of SQL Server memory has been phased out, that typical popular message, then you may want to turn this on, lock pages in memory. Min and max memory settings has quite a bit of myths around. And let me just take a moment to quickly demystify a few things. First, about max. max memory starting from SQL Server 2012 onwards represents almost the max memory of SQL Server. Back in the days prior to SQL Server 2012, it used to represent only the max memory for the buffer pool. But then from 2012 onwards, there have been quite a few changes to SQL Server memory architecture and the memory controller, and max now means max, almost. I say almost because there are certain components that still are outside the purview of so-called SQL Server Max, which is they do direct Windows allocations via direct calls to VAS. For example, the thread stack, for example, common language runtime. And let's say if you have loaded a DLL in SQL Server process address space, then it is not going to come under the purview of Max. It is going to be a direct Windows allocation. So be careful about these things with max memory settings. And of course, min means that once you set up something with min, it is expected that SQL Server memory consumption will not go below it. With max also, I have seen questions in the forum where people say, I have set max to 32 GB for SQL Server, but it still eats up 34, 35, 36 GB. Well, that is a normal behavior. SQL Server can try to overcome it if required, but then it trims down or scales down below the max whenever there is an opportunity. So that's a normal behavior. Buffer pool, the caches and query workspace memory. These are some of the most important consumers. You know, buffer pool for the data pages. There are different caches in Clerks. For example, your cache for the plans, and in plans also you have object plans, you have ad hoc plans, and you have bound trees. So there are a bunch of these caches, and something that is known quite less, which is query workspace memory. When you run your queries, they also need memory. I'm not talking about the session memory. I'm talking about your queries when they do expensive operations like sorting or hashing or parallel queries, they require extra memory. So that memory is called as query workspace memory. Today, we're going to talk a bit about that as well. Memory is bifurcated by NUMA, which means that when you have multiple nodes on your system, on your hardware, even SQL Server memory is divided by those nodes. Simple example, if your hardware has 4 nodes, NUMA node 0, 1, 2, and 3, even SQL Server memory will see SQL Server, the SQL OS layer is going to create 4 NUMA nodes internally. And the memory that SQL Server has will also be divided with these NUMA nodes, which means you're going to have 4 lazy writers, 4 resource monitors, 1 clerk for each node, which means you will have 4 clerks for buffer pool. Everything is going to be bifurcated by NUMA. You can reconfigure this using soft NUMA, so you may keep that in mind. Memory pressures are of 2 types, internal and external. And don't try to compute every number. You will never get it because there's so many different flying numbers, committed, reserved, and trying to, if you run DBCC memory status, you will see all sorts of numbers. It just doesn't make so much sense. What is important is the practical way of troubleshooting SQL Server memory pressure. Last but not the least, when speakers talk about SQL Server memory, they sometimes say things that are wrong and their demos might not work. That is one of the guiding principles of this session. So welcome to the dungeon, SQL Server memory. And I say SQL Server memory equals to CCC, complicated, convoluted, and confusing. All right, so let's look at the architecture of SQL Server memory with this illustration. On the left-hand side, you have the physical RAM of the box, right? The Windows operating system. You can track how much RAM is there on the box or on the VM by using DMV, SysDMOS process memory, and SysDMOS sys memory. Then you have the NUMA nodes. Now, this is still at Windows level. We have not talked about SQL Server at all. And as I said in the beginning, assuming, and today most of your systems you know do have NUMA implemented at the hardware level. So let's say in this example, in this illustration, there are 4 NUMA nodes there. You can track these nodes using SysDMOS nodes. So what happens is when SQL Server EXE, the database engine, boots up, it reads the hardware information and it reads that there are 4 NUMA nodes, and SQL OS, the mini operating system inside SQL Server engine, will create 1 NUMA node, a logical NUMA node per physical NUMA node that is there on the system. And you can track that using SysDMOS nodes. Now that's up to That's very basic about the Windows physical RAM and the NUMA node. One thing, just to digress, when you really want to dive deeper into SQL Server memory, I spent quite a bit of time reading about Windows memory first, the concept about, back in the days with 32 bits, AWE /3G, boot.ini, and the virtual address space, the concept of VAS and the kernel allocation, the user mode, the kernel mode. So there's a lot of this background that might be very helpful if you really want to read a lot more about SQL Server memory. Anyway, let's proceed forward. And now comes the SQL Server portion. So as I said, when SQL Server boots up, it reads the NUMA information and it creates the memory node. So if you can see in the illustration, we have 4 memory nodes, 0, 1, 2, and 3. And you can track all the memory nodes using the DIM OS memory nodes. Remember, there's a difference between DIM OS nodes and DIM OS memory nodes, because OS nodes will give you OS level information and OS memory nodes will give you memory related information from SQL Server's perspective. That's important to note. Now, what happens is when SQL Server consumers, when I say consumers, I mean buffer pool or the plan cache or the query workspace, when they need memory, allocations are done via these nodes. They don't talk to Windows directly. And nodes in turn call the allocators, which we call as memory allocators via Windows APIs. And there are base allocators and structured allocators. Now, the end of the day, these are all Win32 APIs. And depending on how the allocation is being asked for, is the allocation happening in huge blocks or is it happening in fragments, the respective Win32 API is going to be called. In most cases, it is virtual alloc that happens because the allocation happens via the virtual address space. So these base allocators and structured allocators are being called. If you're really interested, shoot up WinDBG and just try to load up a big table, and you can see that the virtual alloc and virtual alloc X is going to be called in Win32 in WinDBG tool. Now let's move forward. I have talked about the OS memory nodes from a SQL Server perspective. And now as we gradually move into SQL Server memory architecture, it's fair and wise to say that SQL Server memory architecture is divided into 3 different layers, or it's like a 3-layered architecture. At the topmost layer, you have memory nodes that are talking to Windows directly via these allocators. And at the next layer, you have memory clerks. And at the bottommost layer, you have memory objects. You can track all the clerks using DIM OS memory clerks and all the objects using SysDIM OS memory objects. Let's talk about the clerks. Clerks by far are the most important piece of information in this entire diagram as far as I'm concerned, because I use DIM OS memory clerks so often to track memory consumption. Now, what are memory clerks? As mentioned before, SQL Server has memory consumers inside it. So like buffer pool, plan cache, query workspace, right? The parse tree, what we call as the boundaries, lock manager, the session memory, the connections. Each and every consumer needs memory. And what SQL Server architecture here does is there is a clerk for each of these consumers. So when these consumers need memory, they talk to their clerks, and clerks in turn will request memory via the nodes. So if there is one question that is there in your mind, can I track SQL Server memory consumption component-wise or consumer-wise? The answer is clerks. In the upcoming demos, you will see that I'm going to use this DIM OS clerks quite frequently to see where is my memory being consumed, not my memory, SQL Server's memory. Then comes the, one more part of the diagram there, general, object store, user store, and cache store. Typically, clerks are divided into these 4 categories: general, object store, user store, and cache store. What's important for us to know is about cache store, and I'll come to cache stores in a moment. Let's talk about memory objects. In the 3-layered architecture, at the lowest level, you have memory objects. Memory objects are simply memory allocations that are being done via the clerks. So in simple words, when clerks have to allocate memory, they create hundreds and thousands of memory objects. If you look at some of those comments there, memory objects could be variable size, it could be mark shrink type, or it could be fixed size, which means that memory objects can grow as needed, or they could be fixed in nature. For example, 8K memory object, and when you need, let's say, 800 MB for something, you will have those many memory objects being created. So memory objects are the most granular level of information that you can get from SQL Server memory internals. Now, do we really need to track memory objects to troubleshoot memory? Sometimes, and that is why in one of the examples today, I will show you that clerks did not give me enough information about where the memory was being consumed, and then I had to go to memory objects, and we can figure that out. You can track all the memory objects using sysdmos memory objects. Now let's go back to the cache store. So when you talk about the clerks, there are some types of clerks that are called as caches, and this is something that you know. I've named the popular cache stores out there, like object plans, ad hoc plans, boundaries, and extended procs. And those are the names, cache store underscore obj cp. Now, when allocations are required by these cache stores, there's another part of SQL Server memory architecture, which is called as the brokering system. And broker, as the name says, does the job of negotiating between these cache stores and between these clerks. It's not like a clerk wants memory, so it asks for, let's say, 20 GB for something, and SQL Server will just allocate it. No, the brokering system actually handles the demand supply algorithm and is responsible to ensure that how much memory is being allocated to a specific clerk, and if more memory is required, can it pressurize other clerks to release some memory, so on and so forth. So that is done by the memory brokers. Further deep, if we go into the cache store, the architecture, cache means there are cache entries. Let's take example of plan cache. And in a plan cache today, if you go to your production box and if you simply see how many plans you have using dim exec cache plans, you will see thousands of plans in the plan cache. These are called as cache entries. And what SQL Server really has to do is more cache objects keep coming in and the old ones need to get flushed out. There is an algorithm which we call as the clock hand system, which does that. You may get more low-level information about cache stores and cache entries using some of those DMVs, Demos, memory cache counters, cache entries, and cache plans. And then there is this all on the top right corner resource monitor, which is keeping a bird's eye view on what's really happening and sends memory notifications to Windows. You can track whether SQL Server is low on physical memory, so on and so forth. And you can get some information in this DMV sysdmos ring buffers. So that helps a bit. Now, when all this while we have been talking about SQL Server memory consumers asking for memory, and the memory that they get is from the SQL Server exe, the SQL Server process space. There are certain allocations that happen directly with Windows. Those are called as direct Windows allocations, or DWA. Let's take an example. You have created a DLL, for example, and you load that DLL in SQL Server process space. And let's say if that DLL is asking for memory, that is going to be a direct Windows allocation via the virtual address space. It's not going to be via this architecture of objects, clerks, and nodes. So just to call that out, and in the demo, I will show you a small example of that as well. Memory models. Well, all these are finer and granular details. At the topmost level, you have 3 memory models in which SQL Server can run: conventional, locked, and large. If you have a vanilla installation of SQL Server, it's a conventional model. You're not making any changes whatsoever. If you turn on locked pages in memory, if you turn that option on via the group policy, etc., and you turn on the user right assignments for locked pages in memory, then that becomes the locked memory model. And there is another memory model which is called as large memory model, that is to support Windows large page option. Not so frequently used, but you may read more about that on Microsoft documentation. You have to turn on trace flag 834. Your system needs to have more than 8 GB of physical RAM and has to have enterprise edition, etc. That will enable large memory option to take advantage of the Windows large mem option. But then it does have some side effects, because when SQL Server, let's say, boots up in large memory model, it's going to reserve all the memory upfront. Remember, we talked about the dynamic allocation and deallocation. That's not going to happen. It will reserve all the memory upfront, because mostly in, let's say, in cases where I've seen SQL Server escalation engineers recommending that, because maybe there are, memory intensive queries and huge plans that are running that may be helped with contiguous memory. When you need contiguous memory, you do need contiguous space, and that SQL Server can get using the large memory option. Well, with this, we come to an end of this illustration, and hope it was useful to just get a fair bit of idea about what SQL Server memory architecture looks like. It's time to jump to demos, and let me switch over to the VM. And maybe someone from the moderator or organizing team can confirm if the VM is showing up.
Yes, it is. And while I get you here, Amit, I got one quick question from the audience just in between. Will you also be sharing your scripts or only the slides?
Of course, I would be sharing all the scripts.
Okay, perfect.
Yeah, and in fact, as the session ends on the last slide, I have the URL, and it's also available with 8KB GitHub. I just made the organizers a few minutes back because I was making last-minute changes.
Excellent. All right, thank you.
Thank you, Ben. So friends, let's get started with the demos, and remember the guiding principle, right? When speakers talk about SQL Server memory, demos may not work, right? So with that guiding principle, let's begin with the demos. This is what the 8KB Jan 2021 folder looks like. And when you get the resources, you will have a similar structure. So I'm going to use this one for some internals demos. Then I'm going to use 3 examples of out of memory exception, out of which the first and second will really cause an OOM if the demos work. And the last one, 3_OM, will not cause, because that makes my VM unstable for some reason. So I changed that a bit and a few more things. So there is a perf mount counter already configured with some counters there, some objects. So we will keep coming back to perf mount and observe total server memory, target server memory. I might occasionally look into the workspace stuff, and we can see page life expectancy, etc. Now, things to note here before we begin the demo: look at buffer cache hit ratio. Very good, sitting at 100%. Look at PLE, 5771, pretty neat, and it's increasing. If you observe this, it will increase by 1 every second. So 803, 804, 805, so on and so forth. Because when there is memory pressure, you will see that they all reset back to 0. Talking about PLE, I mean, just to digress a bit, there are DMVs that give a whole lot of information, and we may sometimes not go and look into PLE, but I just brought this up in the perf mount counter because some of you might still be using many of these counters. Total server memory is 653 right now here, you can see. And let's go and look at the taskbar. If you see in the taskbar, again, about 650 MB is what SQL Server process is using. Now, I have opened up the task manager here and the perf mount counter. You can see the numbers up there. They're matching 650. And if you look at my helpers.sql and let's execute DimOS process memory, you can see about 700 MB being used there in the DMV. Now, the reason why I have all the 3 tools open, and these are native mechanisms of extracting memory information. You are most welcome to use a lot of different third-party tools out there, but I would like to stick to these 3 for the time being. And the reason why I have all 3 open is to show you that DMVs are the most authentic way of getting memory information or SQL Server internal information, and that will be evident to you in a while. Now, when you look at this, of course, I'm not using large page allocations or log pages. This is just a vanilla installation of SQL Server, and there is VAS reserved and VAS committed. Now, I'm trying to understand about virtual address space concept is beyond the scope of this session. That is really like memory 101. So I would really invite you to read a little more about Windows memory, and these concepts might get cleared off. So the memory is what it looks like, 692. Now let's go to the first file, 1_memory, and let's look at first layer, the nodes. Now, DemOS nodes. On my laptop right now, there is no physical NUMA configuration. So the default node is node 0. So which means that even if you do not have NUMA configured, you still have the default node 0, and node 64 is for DAC. Now, this is node information. This is very low level information about the physical node itself. But if you want at node level information about memory, which is memory nodes. So if you look at the DMV DemOS memory nodes, let's execute this. And you can see that target is about 7 GB. So that's the target memory allocated to this specific node. And if you look at the target server memory, that's also matching up with what you see in the DMV. So that's target server memory. The reserved GB is 25 and committed is about 638. Now VAS committed is similar to what you see in the total SQL Server memory consumption. So committed can never go below the actual consumption, and committed sometimes is slightly higher. Reserved is about 25 GB. Where that number comes from, let's discuss that some other time. So we talked about memory nodes, then you have the memory clerks. I will jump to the helper section here, and let's go and look at the clerks. Now, as I said, clerks are really important. They tell you how much memory is being consumed by each component inside SQL Server. Remember, most components have their own clerks, but some components do not have their clerks, and they get their memory allocation via the general clerk. And we'll see that in the example. Now, if you look at the clerks here, you can see PHDR, which is for boundaries, the SQL plans, for the ad hoc plans. These are all consuming about 70 MB, 68 MB, 60 MB, so on and so forth. Very limited use. It's a vanilla SQL Server installation, and I've just started it, so the memory consumptions are very low. Okay, so let's put this down and go back to objects. Now, if you look at memory objects, if you are running this DMV for the first time, all of this is not going to make sense to you. What are these object addresses? What are the different types of objects and the memory consumption, and so on and so forth. But now when I show you the demo, and you can see fixed memory objects, which mean they're always 8K, so on and so forth. So we are going to match this up with clerks using memory allocators, and then these numbers and these concepts will make sense. Now let's get started with the demos and try to understand the basic memory consumption. First up, the buffer pool. So if you see, I am trying to compute how much amount of memory is being consumed by the buffer pool, and I am filtering on my clerk type memory clerk buffer pool. So let's go and execute this, and you can see the buffer pool is only consuming about 99 MB, close to 100 MB. Now remember, starting from 2012 onwards, as I said before, buffer pool's only job is to ensure that there is a healthy data cache that it maintains, which is creating a buffer space for the data pages to be loaded from disk to memory. Now, 99 MB, where is this 99 MB being used? So using one of the DMOS buffer descriptors, you can actually get a bifurcation of all the databases and how much memory are they consuming, in sense, how much memory is being consumed by their data pages. This kind of queries are important because buffer pool tends to be one of the largest memory consumers, and it runs into hundreds of GBs. And that is the point where you may want to find out that out of hundreds of databases that you have on your production box, which database or which set of tables are consuming maximum memory. When I say tables consuming maximum memory, I mean the data pages for those tables are being loaded into memory. At this point, you can see that everything is sitting quite quiescent. You have the hidden resource DB with 23 MB, but nothing much up. Now, not only that much, for example, AdventureWorks 2016, let's say, let's take this database as an example. So for AdventureWorks 2016, which tables are consuming maximum amount of memory, or in other words, their data pages in the memory. And you can see, again, quite quiescent. Now let's run some queries. So in AdventureWorks, I'm just simply going to run select star from sales order header and sales order detail. The moment you fire these queries, the workloads, data pages are being read from disk into memory. And if we go back and try to first find out memory consumption database wise, you can see AdventureWorks 2016 pops up on top 3 and is consuming about 20 MB. And inside AdventureWorks 2016, which tables have their data pages in memory, in physical memory, that is about 9 MB and 5 MB for these two tables, sales order detail and sales order header. To take this one step further, if I have a big table here called transactions. So let's just run select star from transactions. And this has a few million rows. And as it loads pages from disk to memory, which means physical IO is happening, let's go and look into the helper. So there we execute, and you can keep an eye on the memory use, which is right now 796. And what I have done here is I am looking at the total physical memory consumption, and I'm also looking at the clerk sort by pages KB descending. So you can see buffer pool clerk comes on top right now, pages MB. So let's execute this once more. Keep an eye. So now we are consuming close to 900 MB total physical usage, and buffer pool is consuming about 255 MB. And you can see memory consumption keeps shooting up, keeps increasing as more and more data pages are being read from disk into memory. This helps because, as I said in forums, I see most questions, where is my memory being consumed? And I can see that cache stores, the cache stores for my plans, for my execution plans are quite low. It's the buffer pool that is turning out to be the largest memory consumer. Let's go and stop this for the time being and close this. And if we look into this bifurcation again, first let's look at the databases, and you will see now AdventureWorks 2016 should shoot up right on the top. This database has its pages worth 375 MB into the buffer pool. And which table, let's look at this, and you will see that transactions is what I ran, which is consuming about 355 MB out there. Sometimes a good indication of could they be good candidates for in-memory OLTP? Well, there are many other factors like latch contention, etc., that you need to see, but just not the amount of memory. Now let's close down. Just a second. All right, sorry for the interruption. And okay, what next we have? Okay, let's go one level down now and understand the memory clerks in more details. Now, we talked about the 3-layer memory architecture. So we looked into nodes, we looked into buffer pool as one of the clerks. So I will dive a little more deep now. There is a memory clerk called cache stored PHDR. Okay, this is for the bound trees. And if you can see, the pages KB is 85928. So keep that number in mind, 85928 kilobytes is what is being consumed. And if we look at, now I'm going to correlate memory clerks and memory objects. So if memory clerks cache stored PHDR is consuming 85928, what are the different memory objects the clerks, this particular clerk has created? And if I add up the size of all the memory objects created by clerk, I should expect probably 85928. So what I've done here is I am joining memory objects and memory clerks using the allocator address, which is the common attribute in both the DMVs. And I'm filtering on B type cache stored PHDR. Let's go and execute this. And you can see mem obj parse, and you can see the pages in bytes. Now remember, each object there, so we can see about 487. This is nothing in production boxes. This number will be very high. So mem obj parse is the object that is created by the clerk cache stored PHDR, and looks like this is a fixed sized object. Yes, it is page in size in bytes, as you can see, 8192. And if we add all this up now, if we sum up all the mem obj parse object, what does it come up to? 85872. So it's not 85928, it is 85872, which means there could be one root object. So let's just go and run this once more. And let's look up for the root object. There you go. This is our root object, as you can see. And then the rest of the memobj parse object. So what I can do is take up pages and bytes, this one here, and add up here, and then sum up all the pages and bytes, including this additional, and execute. And can I see 85976? So there is something that I might be missing. Well, this is what we are trying to dive is internals into SQL Server memory. So let me just check one more time. Is my pages and bytes? Okay, that's there. It's 85976. That's correct, not 928, which means it increased a bit. And when I add this up here with all the memory objects, you get 85976. So a quick summary, what did I try to do? I am trying to dive deep into the nodes, the clerks, and the memory objects. Remember, what are memory objects? Memory objects are memory allocations via clerks, which means the amount of memory the clerk is asking from the node. It breaks that memory consumption into these number of memory objects. So all I was trying to do is for cache store PHDR, which is a memory clerk, I'm trying to find out all the objects created by it, adding up their sizes and seeing is it equivalent to the clerk size. That's all. Okay. So that's a lot about the memory clerks. Now let's look into the direct Windows allocation. And we talked about direct Windows allocation. So let's open up DLL execution. Ben, I had a small interruption. Can I just have a minute, please?
Yes.
Sorry, folks, just a short break for a minute, please.
This is where I awkwardly interrupt and remind people to please, if you have any questions, put them in the Zoom Q&A. If you have feedback after the session, please go to 8kb.online/feedback. As we've already posted a couple of times and we'll keep posting over the course of this day, all the materials from all the 5 sessions will end up on the 8kb GitHub, and the recordings will end up on YouTube, though I understand this happening on YouTube depends on, may I quote here, Mark getting his stuff together? Is that what you said, Andrew?
Yeah, when Mark decides to get his act together and do some video editing.
My act is together just fine.
I'm just saying, Anthony was saying in the chat that being interrupted while presenting from home is such a 2021, what's the word? Occurrence?
On brand. Yeah.
On brand, that's the word, yeah.
Yeah, I have the same thing. My printer is in my office here, and the kids are at home doing online school. So periodically, I'll be on a video, and they'll just walk
I'm
in
back.
and grab a print job.
You're back, Amit. No worries.
All right. Good luck,
so,
sir.
Yeah, so
back over to you.
You and all the attendees should know. So I'm presenting this from a new office of mine, and I posted the picture some time back. And this is my first session from the new office, and the security guard came that you're sitting up late. Is everything all right? So probably that is what I've put the securities away. Now let's continue. Just have a drink of water. All right, friends. So we talked about the memory clerk allocations and memory objects. Let's look into direct Windows allocation. So on the slide, if you recollect, I talked about that direct Windows allocations do not go via this 3-layered architecture. So I have a DLL file here called heapleak.dll. So let's go and register this first. I'm executing in the master database. Okay, that's interesting. So let's go and do this. And we execute this, and this is done. And now let's open up the helpers, and we'll execute the helpers and see where do we stand with memory. So what you can see here is SQL Server memory currently in use is about 1100 MB, and we have the buffer pool 376, 71, for PHDR, so on and so forth. Keep these numbers in mind. And buffer pool is about 479 there. And we have, these are the cache stores there. Now, what I'm going to do is the DLL, I'm going to execute the DLL, which is going to consume some amount of memory. And you will see that this is not happening via the 3-layered architecture, which means you will not see consumption from any clerk or any memory object. At the same time, let's look up at these numbers. Total server memory is also about 1055 MB there, about 1000 MB. And if you look at the task manager there, it's also at about 1055. So all good there. Let's get started and let's go and execute the DLL. We will execute this DLL, let's say about 100 times. And mind you, the number is 1086 there. Let's go and execute heap lake DLL about 100 sites. So 100 executions have happened. Let's go and look at the memory consumption now. You can see that SQL Server memory consumption has increased by a good deal of about 300 MB there. Yes. Yeah, 1491. And look at the clerks, 376, 71. This is what the clerk status was before the execution. Same with the cache stores. They all remain the same, and the clerks. Now, if you go and look into the task bar there, SQL Server EXE, it is about 1471. So task manager shows up the direct Windows allocation. But when you go into the perfmon counter, look at this. This is going to be strange. Total server memory does not show up direct Windows allocation. And this is where I keep advising folks that while these counters make a lot of sense and you should definitely keep monitoring them, be aware that some of these counters do not show direct Windows allocation. But of course, the DMVs definitely show every bit of memory information. And that's what we tried to do with this direct Windows allocation. So let's close this one. Hope this was clear. Well, with internals, we did talk about, let's take another example of query workspace memory. So we talked about the clerks, the memory objects, direct Windows allocations, and now let's see the clerks. Now here is a simple query, and which is trying to do a cross join and multi-level sort, which means sort is going to be slightly expensive here. And when I execute this, while it is running, we go to the helpers and execute this. You will see now that memory clerk SQL reservations comes on top, and it's consuming about close to 700 to 800 megabytes of space. Now this is interesting. Now you can see suddenly SQL reservation shoots up on top much more than buffer pool. And when you stop this workload and go to the helper and execute this again, you can see SQL reservation just vanishes away. So this is like clerk allocation and deallocation happening very dynamically. This is something important to keep in mind, that while we troubleshoot SQL Server memory, there's nowhere this information is recorded, which means I can't go back in time and find out which clerk consumed what amount of memory. And this is where it gets a bit tricky to troubleshoot SQL Server memory. And that is the reason why what I typically do, and it's just an advice from me, we create baseline. In the baseline database, we have these memory tables, and periodically we read some of these memory information, like top 10 clerks or top 10 memory objects. And
sorry, Amit, I think your video is frozen, and so is your screen.
There we go.
Yep.
Fine? Yeah?
Screen's working fine now. Sorry. Yep. Just wanted to double check.
Yes, absolutely. Yeah. I'll try to turn on the video in a while, Andrew. Thanks. Right, and that is where it is important that you as a DBA developer, if you're really troubleshooting SQL Server memory, it is important that you maintain your own baseline so that you can go back in time and check this information. And this is a very classic example that I just showed you now. Like the moment the workload is stopped, SQL reservation clerk deallocates all the memory, and you have nowhere to track that. Okay, just a few seconds back, about 1 GB was being consumed by which clerk. Well, with this, let's close this one, and let's keep the helpers on, and I will close 1_memory, and let's cause an out of memory exception. So in this first example, and causing an OM exception is not a big deal, but as I said earlier, do not try to do this with your stable systems where you're working and practicing, maybe some dummy VMs. So first I will show advanced options and let's see how much memory is being consumed now, 1539. So I need to restart SQL Server here just to set it back to a low consumption. Okay, I've just switched on to the default camera of the laptop. Fair enough. Okay, so we turn on the advanced option. So setting max server memory is still an advanced option. And let's turn on the helper memory. So now you can see that SQL Server is consuming about 500 MB. What I am going to do as part of this demo is change this max memory to 700 MB. And there is a reason why I am doing that is to cause an out of memory exception. So right now the VM has about 16 GB and I just do not want to stress it so much up to 16 GB. So let's do this with 700 MB. That's what it is set with. Let's open the second file, troubleshoot SQL. And what we are going to do here is right now, if we run this, and I'm just showing you physical memory is about 465. I'm looking at all the memory objects now, DemOS memory objects, and order by total MB descending. So I'm trying to see all the memory objects. I am seeing all the memory clerks. And there is a reason why I'm running these queries, because as memory gets consumed and when I start getting OM exception, I want to track dynamically which clerk or which objects were causing issues. So when I run this, I can see everything is very quiescent right now, all good. 467 is where we are sitting at, and 700 is our target memory. So anything goes beyond 700, remember it can overcommit a bit, but maybe not more than 800 MB, and then we will start getting errors. Now, cause OOM is the batch file that I'm going to run, and it's actually going to cause om.sql. It's going to call this SQL file, which is doing something, and I will show that to you after the demo is done. And if you are recreating this, I have put the steps in readme.txt file. Okay, with this, friends, let's cause om.cmd. So we run this. And let's go back into troubleshooting and we'll see. Now you can see that physical memory is being consumed. And if I keep executing this, you will see memory is being increased 557. And you may also observe that a mem object type cursor execution eats up about 100 MB. So something is happening with the cursors there. And what's important to note here is that when you look at the clerk information, so you can see cache store SQL CP, which means that, of course, cursors, memory objects are being created by cache store SQL CP, which is the ad hoc plans, which means these objects, cursor objects, take up their memory or they request memory via cache store SQL CP clerk. Let's execute this. And then you start getting errors. So this says there is insufficient system memory and resource pool default to run this query. Well, this is fine. Let's go and look at what's happening here. And right here, you can see OM errors. And you can see there is insufficient system memory and resource pool default to run this query. So what exactly happened was that we set the max memory to 700 MB and the batch file was actually opening up cursors, but it wasn't closing it. So there were a lot of orphan cursors at one point crossing 700 MB, and then it hits OM exception. What is interesting to note here is that let's see this workload is now stopped. And when you run the troubleshooting DMB, you can see that physical memory is about 751. As I said, that the consumption could be It could be overcommit of more than 700 MB, which actually happened, 751. And what is important to note here is mem obj. So now there is no cursor information here at all. Now this is interesting. This is very similar to what you saw earlier with SQL reservations clerk. Allocations happen, but the moment the workload dies down or the session is closed, the clerks release the memory. Now this is what exactly happened here. And the reality is in real world, I mean, you may see a few things being printed in the error log and you will see complete DBCC memory status information, but it becomes very difficult to track down what exactly caused the memory error. So, and this is where the baseline really helps. Let's close this one and open up the next one now. And I will take up one more example of out of memory exception. And this one is going to be a little more interesting. In this one, I'm going to again use clerks and memory objects. So sorry, but for the purpose of the demo, I will have to restart SQL Server once more because all these demos, I need to just kind of reset them back and forth again. Okay, so while this is starting, let me see if I can fix my primary camera. Looks like Andrew's shoulders were rubbing. Even his camera didn't work in the beginning. Okay, now it works, looks like, okay.
Yep, all good here.
Okay, perfect. Thanks, Andrew. So let's look at the helpers DMB now. Where are we? We are at 360 MB, and this is much lesser because max memory is set to 700 MB already. And I'm not going to change this to 700. Let's put it to 600. So we are going to show advanced options. That's already turned on. Set max memory to 600 MB. We have done that. Now 600 MB is max, and we are going to cause another round of memory allocations error. And again, what I'm trying to do here is, again, I'm looking at memory objects and trying to filter, trying to sort on the max consumption of these memory objects and likewise the clerks. And let's go and execute this. Everything is very quiescent now. You can see physical memory consumption is less than 400 MB. All objects are sitting nice, clerks, all good. Let's cause the memory error using cause.om.sql. And let's execute this. And we'll come back and see what exactly these folks were doing. Okay, there you go. And while this script is running, we go to monitor mem. So what I've done for each demo, I've created a separate monitor mem.sql so that it's easy for you to check. Now, while this is running, look at physical memory consumption. Quite quickly, it will catch up with 600 MB and go slightly beyond. Look at memory object. So that you have a memory object MSXML with current total of 177 MB. And now you know that this is something to do with XML. What is interesting to see here is that XML, for XML allocations, for XML documents or XML fragments, there is no separate clerk. And that memory request happens via memory clerk SQL general. So let's go and execute this. And you can see SQL general is on top there, consuming about close to 200 plus MB, yeah, which is MSXML there. And at some point, we start getting errors. So you can see the OM errors. XML document could not be created because server memory is low. And this is what was expected. Now, friends, if you see, if I close this session, at least here it may be a bit of savior. If I execute this, you can see from 200 MB, the memory immediately gets truncated down and the objects are cleared off. And now the consumption is only 50 MB. But then you cannot rely on this. The point is in dynamic memory allocations and deallocations, the memory objects can be completely freed up, which means if this example, what I am showing you right now, it happens very similar to what you saw earlier, where when the workload dies off or the session closes, you have absolutely no information to rely on. And that is where your baseline is going to be very helpful, where you can go back in time and understand how memory allocations actually happened, which clerks were on top, which objects were on top, and probably you can correlate and get some information. Otherwise, it really becomes very difficult to troubleshoot SQL Server memory. So I am with about 60 minutes. So one more demo maybe, and then we can jump to questions. So if we go to the last one, 3OOM, and in this, I'm not really causing out of memory errors, but I'm just trying to show you the SQL reservation and the resource semaphore for the query workspace. That is something which is not very popularly known as. And again, a quick background about this. When you have workloads like these, for example, this is a very dummy workload where you are doing a multi-level sort. So expensive sort operations, hash operations, exchange spills in parallel operators, they require extra memory. And this memory is called as query workspace memory. And again, a percentage of the total memory is given to this specific clerk. And again, the memory broker would not just allocate anything and everything that your query plans are asking. You need to kind of go and investigate when there is a wait for memory allocations for these. For example, let's take up this workload. Let me close all of this now for the time being. And what do I do? Set max memory to, what's the current memory, which is 599, which is fine. And let's put this to 1000. Let's set this up here to 1000 for the purpose of demo and hope it works. And then what I am going to do is open up resource semaphore wait type. And let's close this. And we have the helpers. And I'm going to add 10 users by calling this workload. So let's get started. And let's go back there. And now you can see here, memory grants outstanding and memory grants pending. This means that 2 instances of the queries were actually were given memory, and there are 4 queries that are actually waiting. And if I run another instance of, so I say 10 users, but it's actually calling this 5 times. And now if you go here again, now you can see that grants pending has now turned to 10, which means memory grants are pending for this particular set of workloads. And if you run the waiting tasks DMV and filter on wait type resource semaphore, and let's only do this much, and another helper DMV called dim exec query memory grants, you will get some information. So now you can see that so many different workloads are waiting on resource semaphore. So when your query, which has all these expensive iterators that are asking for extra memory, are waiting on memory grant, they wait on type resource semaphore. And using the memory grant DMV, you can actually find out which sessions and whether they have been granted memory or are they waiting. So if they have been granted memory, they have a grant time, or else the value is null, which means they are waiting. And how much memory are they asking for? Each of these instances are asking close to 184 MB. That's what is really happening. And you can also track this using the perfmon counter, memory grant spending 10 and outstanding with 2, because only 2 instances have been granted memory. If you look at the helpers DMV now at this point, let's go and execute. We anyway cannot go beyond 1000 or so what we have allocated. And you can see memory clerk SQL reservations is sitting right at top. SQL reservations clerk triggers in to reserve an advanced amount of memory for this query workspace. And that's why this is called as reservations. If we close all the workloads now, let's stop all the workloads. And that's what we did earlier as well. And if we go back to the helpers DMV, and you can see we are back to the quasign mode. Reservations have deallocated the memory. If you go and look at the perfmon counter there now, you can see page life expectancy was something with like 5,000 numbers, but it got reset a couple of times when there were memory pressures and errors. And now memory grants outstanding and pending are all at 0. So this was dynamic memory allocations. At some point, what happens is if you have too many queries, again, waiting for resource semaphore, they may time out. But then I think the timeout value is 24 hours or something. Somewhere it's documented in internals. Well, big number there. That's how it is.
Speaking with this timeout values, I have to slowly take a look at the clock because we're already 5 minutes over.
Okay. That's With this, friends, I think
you've got until the next session is at quarter 4 UTC, and we've scheduled you in until 3:30. So you've got plenty of time.
That is correct, but Amit was mentioning that he wanted like 15 minutes for Q&A.
Yes, yeah, but I was just saying because we've had some interruptions, he's got plenty of time, so it's no problem.
Yeah, all good.
Right, thank you, gentlemen, for pitching in. Well, I guess I've completed all the demos. So we completed the internals, the out of memory error 1, 2, and 3. So I think we're all good. Maybe I can just go back and summarize, and I'm hoping for a lot of questions to come in. And now Ben and myself need to get active with the questions. So let me just share back the screen 3. There you go. With the slide. All right, friends. With With this, we come to an end of all the demos, and yeah, here is a quick summary. So the whole idea of this session was to kind of talk briefly about the architecture and show you how SQL Server Memory works and how to approach troubleshooting. Sorry for a bit of hiccups, but thankfully all the demos worked, and that was most important. If you have feedback, yes, Andrew shared the feedback link, which is 8KB online/feedback, if I'm not wrong. And we are on Twitter, _Bansal. I saw a few folks tagging 8KB as @8KB. It's not @8KB, it's @8KB conference, so CONF. So if you have feedback, please use our Twitter handles. Time for Q&A. So let's see, Ben, if we have questions and we can get started.
Yes, oh, we have a ton of questions from the Brain Fried audience. So first of all, thank you very much, Amit. First question is coming from Max. So his question is, how should we configure VMware guest SQL servers for optimal NUMA configuration? So even though the VM is configured to have 4 sockets, SQL only sees 1 NUMA node. Is there a guide for SQL servers for that?
This question is from Ben?
From Max.
Max. Hi, Max. I'm not a specialist on VMs per se, but I think memory architecture of SQL works exactly the same way in VMs as well. But what we need to take care of is hypervisor specific best practices, whether it is Hyper-V or VMware. And I know there are certain ballooning concepts, etc. Like in Hyper-V, I know that how you can show up sockets and NUMA nodes and how you can reconfigure it for SQL Server at the hypervisor layer. I'm not sure if there is any known white paper or Microsoft architectural guide around it, but there are some experts in the community like Joey who do a lot of work on VMs. Maybe they might be able to help. If you can post this question with #SQL help, I'll certainly follow this up.
Perfect. And our next question is from Sean. So Sean has a server where sysdm OS memory nodes lists 4 nodes, and virtual address space reserved KB is 1343 gigs, so 1.3 terabytes for 2 nodes and 0 for the other 2 nodes. What is the significance of this difference?
If you have 4 nodes being configured and for 2 of them it's showing up to like 1 plus TB for both of them, and the other 2 it shows up nothing, which means those NUMA nodes may not be in use or may not be configured, which means there could be a possibility that soft NUMA has been implemented to reconfigure NUMA nodes. That's what it means. 0 as a value would mean that those 2 NUMA nodes are not in use.
Excellent. And next question is coming from Arthur. Are there any rules that set priorities for one of the memory clerk over another when they compete for memory?
So memory broker does that job. I have never read or heard about memory clerks gaining priority one over the other. I think it's very dynamic algorithm, and the broker does the job of managing the demand supply. So to my best knowledge, I think the answer to this is no. I don't think that there's no prioritization here.
Okay. And next one is an easy one from Bjarke. I hope I'm saying that right. You were mentioning heap leak DLL. is heap leak DLL something you wrote? Is that something open sourced, or so basically the question is, can the source code of heap leak DLL be made available?
Yeah, of course I will make the source code. It's a simple C++ DLL with I think the new function and the malloc API to just kind of eat up Windows memory. Bad DLL, by the way.
When it comes to me, there's nothing like simple C++, but because C++ always is melting my brain. Roman has a question. How do you detect a potential memory leak, specifically with the case of creating a clustered column store index?
Come again, Ben, once more, please.
So with the special case when he's creating a clustered column store index, is there a way to detect potential memory leaks happening there?
No idea about clustered column store memory leaks. Sorry.
All right.
No answer to this one.
Then we have Fabiano. Is all memory reserved for a query allocated when the query is run, or is it reserved and only allocated as needed? So for example, you have a query that has a gigabyte of memory grant, but it only uses 10 megabytes. Will SQL Server allocate that gigabyte that it's been granted, or only those 10 megabytes that it reserved?
Okay, so the reservation happens upfront. That's what I have seen, which is when the query optimizer is actually compiling the plan and it has the plan with it, even before executing it, it knows the amount of memory it needs. That may not be always accurate. And that is why in latest versions of SQL Server like 19, we have these adjustments being made, right, in the second execution. So yes, the answer to that is the reservation will happen upfront, and it may be that it uses much lesser or much more, which it can recorrect in subsequent execution. But in first execution, it will use what was reserved.
Okay. Next question is coming from Rakesh, and it's about a specific weight type. So how would you troubleshoot the resource semaphore query compile weight?
Resource semaphore query compile weight does not pop up so often, but yeah, we just have to look at the query itself. It might be a pretty complicated query and is using a lot of compile time memory. That's what I can say. So if you really hit that up, we might have to just look into the T-SQL query there. It could be a complicated query.
Cool. Next question is coming from London DBA. So direct window memory allocation should be exceptional issues for most standard SQL servers. So maybe it's actually more a statement than a question from what it looks like. I'm going to and then maybe you could see if you agree or not. So so I'm reading the whole thing to you, sorry. Direct window memory allocation should be exceptional issue for most standard SQL servers, so ones that don't use extended stored procedures and other fringe SQL features. That's a statement that you would agree to, that direct window memory allocations should rather be the exception than the norm?
It's difficult to say whether it is a direct windows allocation is an exception, because it's not a best practice to actually run DLLs, out of process DLLs in SQL Server address space, but people do it. So it's not really an exception. Yeah.
Cool. Next question coming from Maria. Is memory governation in SQL Server done at a specific level of specific memory clerks? So can an individual memory clerk cause an out-of-memory exception?
Yeah, of course. See, the one specific clerk just does not cause it. You see, all clerks are competing for memory, because in some of these, I would say, engineered demos that I showed you, I was just running one specific type of workload to just cause an OM exception. But in real world, you will have all sorts of queries running and all sorts of clerks competing for memory. So, collectively, anything can just cause an OM exception. And it's like a bunch of things causing an exception, but others becoming a victim. So making a statement that one specific clerk is causing it is not really very realistic.
Okay. So we get a question coming over from the Slack channel from Jay. Can you provide a sample of a good monitor for capturing a baseline?
Yes, of course, I can do that. If someone can, follow up with me. If you can just drop me an email at amit.bansal@sqlmaestros.com. I have a script which I can share with all of you. Yeah, no problem.
Excellent. And while we're talking about baselines, what would you consider the bare minimum metrics that should be collected for baseline memory usage?
Well, that is a difficult question to answer. There are so many metrics out there. So I'll answer it in a different way. When we are thinking about baselining and capturing baseline metrics, I start with the problem. We do not go with a ready list that these are the things we need to capture, because it could be overwhelming. There are so many DMVs, so many numbers to capture. So we'll start with the problem and keep capturing whatever is relevant to fix that problem. And really, one customer's baseline is so different from another customer's baseline, because they might be facing different problems, and we just stop where we see that the problems are getting solved. But yeah, some numbers are common. I mean, of course, you want to capture total usage, and in OS ring buffers, you may want to capture, because that gives the notification for whether physical memory is low or is doing good. You may want to capture waiting tasks if the wait type is resource semaphore, for example. The other gentleman talked about resource semaphore query compile. You may want to capture that information. Memory grant information you may want to capture. I do capture top 10 clerks, top 10 memory objects, and some of these numbers. So yeah, a bit of these are common across any memory troubleshooting.
Cool. One little thing for our attendees: please do not use the Q&A as a chat substitution. I see a couple of people basically using questions, asking questions, so they pop up as answers to others. This makes it super hard to follow up along. So please use Slack for the chat. A question from Arthur. Again, is max server memory limit, is that divided equally among the NUMA nodes, and can actual workload change that allocation?
Ben, I lost you in between.
So you have max server memory set, you have a max server limit. Is that limit divided equally across the NUMA nodes, and can the workload basically change that allocation, or would they always have the same equal allocation of memory?
Yeah, that's equally divided, and workloads cannot change that. That is a decision which is taken during boot up.
Okay. Another wait type question on resource semaphore. So Brett is wondering, can I create an alert for resource semaphore waits, or would that alert also be waiting for the memory? So would that basically, would that alert never fire, because by the time the alert fires, there's no need for the alert anymore?
No, actually, the idea is creating alerts for resource semaphore may not be a good idea, because it keeps happening all the time on busy systems. When we have a heavy OLTP transactional system and all sorts of sorts and hashing going on, you may actually see a lot of such alerts, because these wait types are very, very short-lived, sometimes like just a few milliseconds. And that's fair, waiting for a few milliseconds to gain access to that extra memory and then you get it is fine. You may not want to be bothered at that time. But if you are asynchronously capturing it, and then from your later analysis, you may want to find out if a particular wait was more than, let's say, a few minutes or something, that is what you may want to go back and investigate.
Okay, Arthur has another question. I don't fully understand it, but maybe you do. Can query memory grant span the NUMA nodes? Arthur, maybe you can clarify that question.
No, I think it will not span the NUMA nodes. Think about this from a NUMA architecture. CPUs need memory. So the threads that are actually executing your workload, is executing your query, is requesting for memory from the specific node. And spanning is how it could actually happen is that if a specific node is choked up with memory, it does not have enough memory to allocate to the thread, it can actually go and ask the other node for memory. So there could be cross pod memory access. In that way, you could say like, it's spanning, but really if you see, it is at the hardware level, which is one node requesting memory from another node. This is called as foreign memory. I think that's the term, yes, foreign memory, when one node consumes memory from another node.
Cool. Another question by London DBA. So if I clear the buffer cache and then I run a select on a big table, would I expect to see high memory on one memory node and 0 on the others? Or would the memory spread equally across all memory nodes? So his guess is the connection is linked to one memory node, so only one memory node would show with the high value?
That is correct.
Okay, and another one from London DBA. So for out of memory for cursors, XML, etc., he'd argue that there's not enough built-in monitoring for such features. So you need to be. Okay, it's also more of a statement. And then there is I don't know if we have time for this and if that's something you can pull up that quick. Maybe otherwise you can refer Bjarke to something else here. So because Bjarke is asking for another quick demo. What happens if the host is, or maybe you can just answer it. If the host is under severe paging, what happens with the memory clerks?
If the host is under severe paging, what happens with the clerks? Well, what I think will happen is the SQL Server, overall SQL Server memory is going to get trimmed down in that particular case. So you will probably see that SQL Server is releasing memory back to Windows in case of low notifications being sent. We saw clerks getting trimmed down now as well when there was OM errors. Just for the attendees, on the screen, you have connect with ab@sqlmaestros.com in case there are more questions that we are not able to answer now. And if you want to shoot up a mail, connect with ab@sqlmaestros.com, or Twitter is also another way. I would be very happy to interact with you on Twitter there. And scripts are up there. And if you need scripts immediately, you can send a mail to connect with AB again. That's what you can do. Or the resources link there, you can bit.ly/SQL resources. They're all uploaded. And it's also there on 8KB GitHub. Can I request Andrew that I would resend? I will just correct, make a few final changes to readme.txt just so that people can execute these scripts better when they're trying. So please ignore the last zip file that I had sent, and I will resend another one.
That's no problem at all. We can get that changed for you. And I'm pretty sure we capture all the Q&A questions that are asked. So if there are any unanswered ones, we'll distribute them out to the speakers at the end of the event and they can get in touch.
Excellent. There's actually one more question for Mark. Alexei kept following up on because he asked when the videos would be on YouTube, and I'd say it will take a bit, and he asked me to define a bit, please. So maybe you can clarify that a bit.
That's one for you, Mark.
Over the course of this afternoon.
Oh, so actually, no, this is a good point to bring up. So right now, the live stream is happening on YouTube. When we're done for the day, we'll leave the live stream up of the whole conference until we get it chopped up into the individual videos. So you'll be able to access all of the content like immediately after this is done, but you might have to kind of scrub through it to find the exact thing you're looking for until we have a chance to get it all chopped up into individual videos.
Cool. Thank you for that, Mark. Thank you so much, Amit. Awesome session. Thank you so much to all the attendees for a whole bunch of questions. Oh, I see another friend showing up there, Mr. Argenis Fernandez.
We had some absolutely awesome questions being asked there. Absolutely fantastic stuff.
Well, you can tell that it's awesome questions if I don't even understand the question, let alone the answer given. So,
well, awesome session, Amit, as well. We said we wanted mind-melty content, and well, I think you delivered on that one.
Thank you, everyone. Thanks, attendees. Thanks, Ben, for being such a lovely moderator. I mean, sorry, Ben, they didn't give you any other choice, but otherwise you could have understood the question.
Okay, so I'm just going to share my screen here.
Yeah. Thanks, Andrew, Mark, and Anthony. Thank you.
Thank you very much.
Thanks, Amit. My pleasure.
Please give feedback on the Twitter and the URLs that Andrew posted. Goodbye, and have a great rest of the session. Some great sessions lined up now. Goodbye, friends. Thank you.
Thanks. Have a good evening, Amit.
Thank you, Ben.
So what's up? What's up?
How's it going,
What
Argenis?
up?
Hey, how's it going?
Hi, Sunshine. How are you?
What we doing?
How you doing?
They let you in here?
I know, right?
Keeping it professional, huh?
Somebody thought it was a great idea to give me a link to this. Oh.
Yeah, I was going to say.
Can somebody boot him?
Okay, can everyone see my screen now? There is the link for
Yes.
The QR
the
code.
feedback forms and a QR code. So thank you very much for attending the Amit session. Please leave him feedback. He wants to know what you liked, what you didn't like, and any general comments. So please go ahead to that link, click on Amit session, and give him some feedback, please.
Ooh, man, look at John and Bob's beautiful T-shirts.
Oh yeah.
Wait.
Am I
and
backwards?
Aaron, look at that.
Am I showing up backwards? Do I need to like flip my video?
No, you're not. You're
Oh,
showing
not?
up fine.
Okay.
John, are you growing a Muppet?
Wait, how'd you get a blue one, Bob?
I don't know. I just ordered one and it was blue.
I didn't have a blue option.
And just a note, Bob and I didn't plan this.
Oh dear. Oh, you're wearing that too? Nice.
Yeah. we didn't plan this.
Liars.
I mean, we didn't plan this. You are aware which event you're currently attending, right? Just a second.
I'm just saying. I'm just letting you know that we like great minds think alike. We didn't
There
plan
we go.
for it, so
Fools never
that has
differ.
nothing to do with anything, but
I'm not impressed.
you're still my favorite Ben, but come on.
Well, it looks like I missed some other fun here.
Okay, so we've got 5 minutes. Bob, do you want to get yourself set up? If I stop
Um,
sharing my screen?
I can share my title slide if you want.
Yeah, let's get that up and running. Make sure
Okay.
everything's
Let's
working.
make sure that works because nothing else is broken this morning at all.
Are you on your backup?
I am on my backup computer. I managed to get this thing set up and I had to literally install Office and Azure Data Studio and everything else in the last hour. And instead of being nice and set up here, I'm now sitting here with a tower PC between my legs. But that's okay because it's working. So
That might have been a little.
Right?
not family
It's
friendly.
like a space heater.
There we go.
It's a little.
well, good things happen to good people. I'm just going to leave that here without any additional comment.
Didn't this happen to Anthony like a month ago?
Yes. Well, maybe.
His caught on
What?
fire. Did yours catch on fire, Bob?
Not yet. I don't see any smoke. It's still turned on, but
Coincidentally, that was a DPS, which was a MITS conference. So yeah, full circle there.
maybe he brings a bad juju.
You guys are DBAs and pyromaniacs?
Hang on. That happened to you. So I may have mixed up that story because I was thinking about Past Summit where your notebook broke like 3 minutes before your session.
So that was remember when the root certificate or the intermediate CA for Apple expired, and so the app wouldn't launch, and so it would because it couldn't check like the signed certificate or whatever. I just figured it was just Zoom crashing, and so I was able to switch laptops, no issue there too.
Yeah,
So yeah, it was a stressful like 2-week stretch there.
Yeah, I mean, I keep hearing everything is better and easier with a Mac, and I totally get it.
Hey, I haven't had to install a driver in like 15 years, so it's all good.
Yeah.
Maybe it would be easier if you did.
Man.
Are we?
My Mac runs fine until I open Windows.
There we go.
You just pay $100 for a
Right.
charger is all.
Yes, John.
Are we clearing the Q&A from the previous session?
There should be no open questions right now.
Okay, but they're gonna the old questions are gonna stay in the answered.
Yeah.
Are you moderating this, John? Is that why you're
I
asking?
am.
Oh.
No, he's
Yeah, just again,
intensely
slight reminder
interested.
for the attendees: please do not use Q&A as a chat substitute, especially towards the end. It was making it slightly hard to keep up with what is a statement, what is just a hey, nice to see you, and what was an actual question.
Yep, there's a Slack channel for chatting.
Yep, please do jump into the Slack channel and get involved in the chat.
Yeah, and
everything-
there's like cool emojis and stuff in there too. You don't get that in Zoom.
There's emojis. If I had known that, I would have taken the Slack channel moderation. Damn
There
it.
we go.
I mean, you can still hang out there, Ben. It's fine.
Hey, I have a 100 level question for the panel.
Not allowed.
I'm
Not
working.
allowed.
It depends is the answer.
Is an agent job step its own SPID? So like if I create an agent attempt table in one job step, it will be gone in the next job step, correct?
Correct.
Okay, I thought so.
Every step is a different connection. So yeah.
One more great piece of content you get here at EightKB.
There we go.
Right, that's the stuff we're too embarrassed to ask on Twitter.
It was much faster to ask you than to ask all of you than to type that.
Yeah, it's just us and 363 friends.
Yeah.
In a circle.
Okay,
as we are right at quarter to the hour, I will mute myself and disable my camera.
Yes.
Thanks, so guys. So
Everyone
thanks so much
mute,
for having me. And
no,
Bob,
sorry,
best of
Ben.
luck.
No worries. I was going to say thank you very much. You did a fantastic job.
Thanks.
Okay, and we are good to go with Bob and the ins and outs of SQL Server data compression. Bob, take it away.
All right, thank you so very, very much. This is the ins and outs of SQL Server data compression, and I just said thank you, but I'm actually going to put up a thank you slide here now if PowerPoint cooperates. There we go. Just want to say thank you to the organizers who make this event happen and for having me and all you attendees out there who are watching this, because it's kind of hard to have a conference without people watching it. Also want to give a shout out to Mr. John Morehouse, who will be acting as my moderator today. So feel free to ask questions at any point. John will either try to answer them himself, or he will butt in at the end of each section, and we can have a little chat about that, and then we'll do even more at the end. So thank you so much. And finally, a little advertising note here. I would like to point out that there is official 8KB merchandise, these lovely Mixed Extents t-shirts promoting the Mixed Extents podcast, which is brought to you by the creators of 8KB. So if you want to be cool, well, if you want to be cool, first of all, don't do anything at all that I do. But if you'd like to be cool and help this event, check out their little store they got there, and they got these awesome shirts. And maybe someday they'll have like 8KB laptop stickers or something like that. Hint, hint, hint. All right, to briefly introduce myself, my name is Bob Pusateri, coming to you here from Chicago. As we like to say, Chicago, come for the deep dish pizza and the Italian beef sandwiches, and stay because you died of coronary artery disease. I've been active in the community for a while. I've run user groups. I help plan events in the Chicago area. I've been working with SQL Server since the Microsoft Certified Master Program was a thing, which is just a nice way to say I'm not a spring chicken anymore. And the next time I go job hunting, potential employers are probably going to be trying to see if they can find someone a little younger first. But seriously, the best thing on this slide is my contact information. So if you have any questions we can't get to at the end of this session, or if you're watching a video of this and would like to reach out later, find me on Twitter. It's got my email address on there, or you can go to my blog, bobpusateri.com, and I got a contact me page, which will also send me an email. So our agenda today, this morning, this afternoon, evening, night, depending on where you are, we're going to go through just some very basics of compression in general, just talking a little bit about the technology, and then we'll actually get into SQL Server specific topics. We'll talk about row and page compression, how those work, and then we'll talk about Columnstore and how that works as well. And then we have time for questions at the end, hopefully. All right, so why are we compressing? Disk space is pretty cheap, right? I mean, you can go to your local tech store and get 12 terabyte drives, or even larger at this point, for not a whole lot of money. But unfortunately, enterprise disk space, the disk you can really depend on, well, that's not cheap, right? Because you're paying for not only usually really good quality hardware, but you're also paying for support. And when you have a problem, there's someone there to pick up the phone and help you now. So disk space, it's gotten cheaper, but the disk space that you're depending on, not as much. And that's for very good reasons. So compression originally came out as a way to enable you to store more data in less space, and that's what was built in with SQL Server, right? Additionally, compression can help in terms of maintenance, right? You have maintenance processes like DBCC, CheckDB, and whatnot. They actually have to go through and read the entire database page by page, right? The more pages your database has, the longer these processes are going to take, and that might cause interruptions or issues depending on how you're set up and operating. So if you're using compression and you can fit more information in fewer pages, well, then maintenance shouldn't take as long either. Also memory, right? Memory is still today way more expensive than disk, and it's also faster than disk, right? Really, really fast disks are great, but the only thing faster than a really, really fast disk is not having to read from it in the beginning because the data is already in memory. So if you got the ability to store more data in memory, which some of these compression methods let you do, you can come out ahead that way. And if you're curious what you're looking at here, this is hand-woven ferrite core memory. This is a total of 18 bytes in the space of about 2 by 3 inches. So yeah, at least memory's come a long way, right? And finally, I/O, even with today's super awesome fast networks and everything else, I/O can still be a bottleneck, right? I've brought into so many clients over the years that have had, at the root of their problems, I/O bottlenecks. So if we have compression in place again, we don't have to worry about the amount of I/O we're doing, or we're doing less I/O to begin with, and that can help relieve some of these issues. All right, so first off, in our compression primer here, we're going to talk real briefly about lossy compression, right? And lossy compression has kind of weaseled its way into absolutely every aspect of our lives, right? On the right, we have the nice image there. Obviously, image compression has been around for quite a while, and it's been lossy. You have your JPEG formats or your newer HEIC encoding, which Apple tries to force upon the world and hasn't really worked that well yet. Music is a great source of lossy compression, right? MP3 is lossy compression. You lose some of the quality, but not enough to where it really makes a difference. And back in the old days, we had to install WinApp and occasionally listen to llamas get assaulted because, at least at the point when I was in college, Windows didn't have native MP3 support yet, right? So you were probably using something like this. And then finally, for a more modern approach, of course, we have streaming video, right? Which the entire world is usually watching these days. And there's a whole bunch of advances in the world of video compression, right? We have H.264 compression, H.265, which is even better. The official standard for H.266, the next generation, which will bring, hopefully more 4K content to streaming, was actually just approved last July. I was reading it a couple months ago. So lots going on in the world of lossy compression, where we shrink down the amount of data for minimum loss in quality, usually, or a variable amount of loss in quality. How much loss in quality can you tolerate? That's the idea behind lossy compression. And that's great for these things, but when we're talking about data, that's not so great, right? I don't want compression to affect the data that I'm storing, right? For that, I need lossless compression, because if compressing something changes when I'm storing to the point where I can't get my original values back, that's bad, right? And I have a picture here of, floppy disks, which probably nobody has touched in a whole bunch of years anyway, which is great. But the idea here is lossless compression is what we'll be talking about today. We want the data to take up less space, but be able to reconstitute it to exactly what it was before, so it makes no difference. Now, if we want to take a little academic sidebar here, I'm going to mention Huffman coding very briefly. This is an optimization for encoding more frequently used data with fewer numbers of bytes, right? And we'll talk about a little bit more about this later, but just to bring that up, that's one of the oldest forms of compression or optimization. It was like an MIT paper in the 1950s or so. Most of the compression methods we use today are more statistical in nature. So you got your LZ77 and 78, which were kind of the originals, which actually came out in 1977 and 78. And those have served as the basis for a lot of the more modern algorithms, LZW, LZMA, gzip. These all basically work around the idea of creating a dictionary of most commonly used patterns and then referencing them with pointers where they're appropriate. And lossless compression like this has worked its way into pretty much anything you can think of, even if you're not thinking about it. Microsoft Office files have used zip compression since 2007, I believe. So if you've never taken an XLSX or a docx or a PPTX file and changed the file extension to .zip, you can do that and actually browse it, and you'll see a bunch of XML documents and a folder structure in there. That's exactly what that file format is at this point. All right, so we have some great compression technologies, both lossy and lossless. So when we're trying to compress our database, how are we going to do that, right? Why not just zip or do something lossless compression to the MDF file and the LDF and just compress the heck out of these files? You can actually get pretty good compression by doing that, but it's going to fail on a whole bunch of other fronts because of how the database works, how SQL Server is working, right? So database I/O is usually very, very random, and it's usually pretty small, right? We're reading from the disk in units of extents or pages. And we're not needing the entire file at once. We usually need a very, very small part of it. Because of those needs and the addition of performance, right? If we have great compression, but it kills the performance of our database, then why even bother? The SQL Server team kind of had to, when designing the compression features, had to take in the balancing act of we need pretty good compression, but we also need it to be really, really fast. So that's what they ended up coming up with. And this is great for, great for the large amounts of data that databases have, especially today. And as an added bonus, this data is also compressed in memory. We'll see that on another slide. But when you're using compression like this, the data is compressed both in disk and on memory. Actually, it was on the next slide. So here I have a very brief diagram, very simple diagram of a database system, right? We have a user, they're using SQL Server. SQL Server has a section of code called access methods, which basically translate the data from bytes on disk and in memory to tables and objects you can actually work with. And the access methods are actually where the compression occurs. So as I said, data is compressed both in disk and also in memory, which is great because we can not only fit more data on disk, we can fit more data in memory at any point in time. That's the upside. The downside of this is that because the data is compressed in memory, it is never cached in an uncompressed state. So if I'm selecting the same group of rows from a table 10,000 times, then guess what? SQL Server is decompressing that data 10,000 times as well. Right, so you're paying for this in terms of CPU load, very, very small CPU load. Back when this feature came out initially in SQL Server 2008, it was like 5% CPU load. Now it's got to be even lower, assuming you're using better hardware than you had in 2008, but it is CPU work nonetheless. So the three types of compression we're going to talk about today, here demonstrated by the most complex PowerPoint animations I've ever done. We have row compression, we have page compression, and then we'll also dive into Columnstore as well and talk about the algorithms that Columnstore is using to help achieve what it achieves. So first off here, let's talk about row compression. Row compression, some people might even say it's not really compression, it's an optimization, but what it is it's only use the space you need compression. So the first thing it does is it takes any fixed length numeric data and makes it variable length only using the necessary bytes. So if I have a column that's an int, right, and an int is 4 bytes and can store a value up to 2.7 billion or whatever, but I'm only storing the value 5 in that particular row, well, I don't need 4 bytes to store the value 5. I can actually do that with a tiny int, which only takes 1 byte. So if you're using row compression behind the scenes, what it's actually doing is storing that value in the amount of bytes it needs. And we'll actually take a look and see how that happens in the demos in just a tiny bit. So it's only based on the value it needs, or that's being stored, that's exactly what is being stored on disk, and it's saving all that space. Similarly, if you have fixed length character data, so if you have like a char 100 and you're storing someone's name and their name is Stu, and that's only 3 letters, that only needs 3 bytes, not the 100 that it would normally take if you weren't using row compression. Similarly, null and 0 values have been optimized away. They need no space at all. And if you have the metadata for variable length data, which is always there, the overhead for that is also reduced because there's a different record structure being used. So while normally if you had a variable length column, so let's say you had like a varchar 50, that of course would take up to 50 bytes depending on what you're storing in the column, but there's also 2 bytes that are added on to that as overhead, which actually store the length of what's being stored in that column. So if you had a varchar 50 and you had something that was 50 characters long being stored in it, it would take up 52 bytes on disk. This has been optimized away, so instead of taking up 2 bytes per column, it now takes only 4 bits per column. And this is done via what are called column descriptors, which again, we'll look at very shortly. Row compression does not have any effect on the smallest of the data types. So if you have something stored in a tiny int, well, it's going to stay a tiny int or small date or time. It does help bit columns though. It optimizes that a little bit as well. So if you have normally if you have a table and you have to put a column in that table of type bit, right, which only takes up 1 bit because it's storing a true or a false, well, behind the scenes, SQL Server would actually allocate an entire byte for that, so 8 bits. And then if you had more than 1 bit column, or you added one later, those would share that same byte. However, this has been shrunk with row compression, so now you only need 4 bits instead of 8. So that's kind of cool. And then finally, if you have Unicode character data in your table that you're applying row compression to, that may be compressed. It will try using what's called the SCSU algorithm or standard compression scheme for Unicode. If that provides an advantage, it will go ahead and do that for you. Otherwise, if there's no advantage, it will not. So enough words. Let's try to just see this in action through something graphical here. So I have a table with 3 rows. I'm storing an ID, which is of type small int, which is 2 bytes, and I'm storing some first names of character 8, right? So those will take up 8 bytes. And normally without compression applied, this is how exactly it would look on disk. So Sam's name, even though it takes only 3 characters, well, guess what? It's taking up 8 on disk because it's a character type. It's a fixed width type. Now, if we apply row compression to this, it's going to shrink all this down as much as it can. So Sam's ID, which is 92, well, that can fit in a single byte. So instead of that small int taking up 2 bytes, now it takes up 1. Sam's name only takes up 3. And we save the rest. Similarly for Nick, well, his ID is larger, so it would take up 2 bytes, but his name doesn't need all 8 bytes, it only needs 4. So you end up with 60% savings on the first row, 40% on the second row, 10% on the third row. As I said, though, what this is doing now is the fixed width types are not fixed width anymore. So now we actually have to go ahead and read some metadata before we read each row, right, called a column descriptor, so we know exactly how much space that's going to take up and where these values are now with compression in place. So with that in mind, we're going to move to our first demo here. And I have a notebook and all this data and the notebooks are available for download here, and I'll also have them up on the 8KB page as well, or 8KB GitHub repo rather. So the data I'm using today, this is parking tickets data from the city of Chicago. They released this a while back. So I have literally all the parking tickets that the city of Chicago wrote from the years 2003 to 2016. It's like 39 million rows. So just so you can see here kind of what data we're dealing with, we have some tickets, we have license plates, type of car, make of car, when it happened, where they got the violation, what it was for, what they paid, who wrote the ticket, what happened to it in court, etc. So we have all this data here. And we're going to start off just by taking a subset of this data, right? I have 39 million rows, and while I definitely could compress it all, it would take some time, and I don't want to sit here and make small talk while we're waiting for things to run. So I'm going to take a 100,000 row subset of that and put it into a different table called Parking Tickets Mini, right? And that takes a fraction of a second, which is great. This is really fast to work with. So we have 100,000 parking tickets in our table, and if we want to see how big that table is in its current state, just without any compression at all, I'm going to run this query. It's going to join partitions and allocation units and a couple things together here. And we'll see that we have the table called DBO Parking Tickets Mini. It's got 100,000 rows in it, and it's using a little over 12 megabytes for all this data. Great. So now I'm going to go ahead and apply the row compression, right? This is an alter table statement because I'm doing it on the table, not on an index. Rebuild with data compression equals row, and that should be nice and fast. There we go. Again, fraction of a second for 100,000 rows. So now let's run that same query again and see how that affected our size. So we took it down from a little over 12 megabytes to a little under 11. So we saved about a megabyte on 100,000 rows, doing some very, very trivial compression compared to other methods we have at our disposal, right? So this is the simplest, and we saved, you know, almost 10% just by getting rid of white space and fixing more or less data types by changing them behind the scenes to more appropriate data typing. So now we're going to list out the pages that make up this table. And you used to do this with dbcc-ind. However, now we have this sysdm database page allocations function that we can call. So I'm going to call that on this particular table, list out the pages, and I just want to find the first page of the table. I'm filtering them out here. We don't have them all, but I need a page number. So there's our page number. And now I'm going to open a separate window, and we're going to run dbcc page and actually look at the contents of this page. I love Azure Data Studio and I love notebooks, but based on a whole bunch of experimentation by yours truly, it looks like DBCC page does not play very nice with a notebook, probably due to the amount of text it spits back at you. So, and I can't blame them for that because DBCC page isn't supported to begin with. So we're just going to run it in a normal query window instead of a notebook. We have to enable trace flag 3604 if you've never run DBCC page, and then we specify our database name, the file number, the page number we want to look at, and how we want to view that page. So we're saying option number 3, which is show the full details of that page. We're going to run it, and it's going to spit back a whole bunch of information here of the contents of that page. We have buffer information. We have the page header, which has a whole bunch of information just about this page, what page number it is, what page is before it, which one is after, what object is this, etc. We get allocation information, so GAM, SGAM information, and then we get down to the records themselves. And I'll zoom in here. I realize this might be hard to look at on the video. The first thing we have here that we're going to see as I zoom in is we have what says CD array, right? This is that column descriptor array I told you about. And there's one of these for every row. And what it does is it describes the length of each of the columns in this row. So column number 1 is a 4-byte short. Column number 2 is a 7-byte short. It's showing the length of these because remember, we can't trust on the fixed width nature of the data typing anymore because we've applied compression to it. So we have this column descriptor array that gets added for each row. And then if we scroll down a little bit more here, we'll see we have the actual contents of the record itself, right? Just the flat out memory dump of the record. And you can actually read in text what's in here, what's in this record. And then below that is where we actually break out each column of the record and let you see what is stored for each. So we're going to look at our first column here, which is this. It's a ticket number. It's a ticket number 36566-295. This column 1 is a big int data type, right? So huge number of range it can store. It takes up 8 bytes of fixed width normally, but the value we're storing here right now doesn't need 8 bytes of fixed width. It only needs 4, which is why it says length 8, but length physical is 4, right? So we get a 4-byte savings on this value just by getting rid of the unused space. Similarly, we can go down and see other columns that work the same way. Some compress better than others, some maybe not at all. We have the state here. It's a Chicago ticket, so it was written in Illinois. You can see that the length of that column is 2, and the length is 2 because it's filling up the whole space. Some of these down here have some slight savings. The price has a length of 5 and a physical length of 2. We're saving a byte here, a byte there. Sometimes the savings is great, sometimes the savings is not so great, but you're trimming off that unused space. So if you run DBCC page on a compressed column, or on a compressed object, you can see this, right? So here's the next row, another column descriptor array, and more of the same. And you can just read through the whole page this way using DBCC page if you really want to geek out and see what's being written to disk. So that is row compression in a nutshell. John, do we have any questions at this point?
We do. We have a couple.
Okay.
The first one comes from, and if you ask a question, I butcher your name, I sincerely apologize. Lori, how will row compression affect text searches?
How will row compression affect text searches? And by text searches, I'm assuming you mean just standard where text column equals something something. Right? If you're talking about full text searching, that's a completely different setup, and that's not covered here. But for any query or text comparison, this will work the same way. So there's nothing you need to do. In fact, this is pretty transparent to end users or applications that you can compress things behind the scenes, and it would not be apparent to the queries they're writing.
Okay. Another one from London DBA. Any benefits on the transaction log from using compression? Thinking less space used for the logging data modifications, and he says row compression data.
So I am not exactly sure. I don't believe the contents of the log are compressed. I guess if the compressed output might be what's actually physically written to the log. I'm not exactly sure on that, so you may see some savings.
We have another question from Michael Thomas. What is the downside of row compression?
What is the downside of row compression? I would argue there isn't much of one other than it's a little more work, right? I used to, back in the day, I used to advocate for, as long as you weren't bumming your CPU up against 100% constantly, you should probably enable row compression because it will likely help you. If you can prove it provides no benefit, I wouldn't use it. We'll talk about how compression used to be an Enterprise Edition only feature, so that would have been a potential downside, but otherwise, I would argue there isn't really much of one.
Okay, next one is from Lars. Actually, we're getting a ton of questions now, so
oh
at
boy,
some point
all right.
I'll cap them. And
I would say, yeah, we get a couple more and then we got to move on so we don't run out of time.
So the next one from Lars, does index compression mitigate poor fill factor settings?
Does index compression mitigate poor fill factor settings? I mean, you can fit more onto a page, and that can't, but it's still going to count the page as full when it reaches your fill factor setting, right? So I would argue no, other than you get the benefit of storing more data per page to begin with.
Okay, so how about two more?
Sure.
The next one's from Roman. Is there a way to compress data in TempDB?
Is there a way to compress data in TempDB? Not that I am aware. These compression settings we're talking about here do not work on system databases.
And one more from...
Oh, wait a minute. No. Well, system objects in system databases does not work for. If you want to create a temp table with compression, I believe that will work. But I haven't tried it. Sorry.
No, you're fine. Yeah. One final one, then we'll move on. Ajun asks, does row compression lead to more page splits? If yes, how can we avoid?
Would it lead to more page splits? If you have a pattern where you're constantly overwriting data and your data is taking up different amounts of space. So if I have, like my first record that's on the screen here for Sam, and then I overwrite Sam and put a longer name, all right? If I was using fixed width, that wouldn't be a problem, and it definitely wouldn't cause a page split. Whereas if I'm overwriting something and the record no longer fits there, that might cause a page split. So I guess it might cause more page splitting. Not sure if that would really be a huge issue or not. Maybe if it was in your particular environment.
Okay, so I'll go ahead and document the rest of the questions.
Awesome.
For the audience, make sure you put it in the Q&A, and I will capture them, and I'll make sure to get Bob the list of questions.
Very good. Thank you so
Thanks,
much,
Bob.
John. All right, thanks for the great questions. I'm glad people are enjoying this. All right, so we're going to move on now because row compression's cool, but page compression is even cooler, right? So page compression takes row compression and kind of kicks it up a notch. It actually has three components of what it's doing. So first thing page compression does is row compression out the boot. So if you put page compression on something, you're automatically having row compression take place. And then beyond that, you have what's called column prefix compression and column dictionary compression. And we'll talk about what those mean here in just a moment. In addition to the column descriptors, you now have what's called a CI, or a compression information structure, that is added to each page, which contains what's called an anchor row and the dictionary of the data that's in that page. Page compression may not be applied to every page, so SQL Server is actually doing some work behind the scenes to determine if space can actually be saved by page compression. And if the data that's on your page is not going to see any benefit from it, it will not apply page compression to that page. And then finally, page compression only applies to the leaf level pages. So in the picture on the screen here, where we have our index structure, the leaf level is the bottom row, 4, 5, 6, and 7 in the lighter green. The upper levels of the index, which generally just contain pointers to other pages that have the actual data on them, those do not get page compressed. So first thing we'll talk about is prefix compression. It will try to find a prefix for each value in terms of byte values. So it'll be type agnostic, right? Whether you have a numeric value or an integer or text or a character or whatever, it will just be working with the bytes here. So it doesn't care about the types. And it will try to find the largest, most common prefix for all the records in that column on that page, and will determine that prefix to be what's called the anchor record. It will store it there. And then row values are translated to be in terms of that anchor value. So if I had two values here in bytes, as I do on the screen, and I'm looking for my most common prefix, well, 0, 1, 2, 3, 6 is my common prefix there. They both start with that. After they differ, even if they're the same after only one byte, doesn't matter. We're looking for the most common continuous starting prefix. So we have a database page here, and this page contains information about 3 rows, each with 3 rows with 3 columns. And we have our page, we have a page header, and we have that CI, that compression information structure. And we're going to go ahead and perform page compression on the values in this page. So the first thing we're going to do is create that anchor row that I talked about and try to determine what is the most common prefix for that column, and then we'll put it in the anchor row. So for the first column, the most common value with the most common prefix is AABBC. So that's going to be our anchor value. Similarly, for the second one, the longest one with the most common prefix is the first one, AACCBF. That's our anchor. And for the third one, it's BCDFA. Once we have our anchor row, we then go ahead and we transform the data to be in terms of that anchor row. And I'll show you what that means. So for our first row and our first column here, the value is AABB and our anchor is AABBC. So what we need is we need the first 4 values for first 4 bytes of that anchor column to be stored. So that's what we're going to store. Instead of storing AABBC, we're going to store 4. And that means just go to the anchor row and get the first 4. Okay, hopefully that makes sense. For the second one, now we have CAB. Well, that doesn't match, right? Because this starts with C and our first value in the anchor column is A. So that doesn't match at all. So what we store then is we store 0 CAB, which means go to the first 0 values of the anchor column and then put CAB after that. Now I'll point out this does not save space. This actually costs a little more space, right? Before we were just storing CAB, now we're actually storing a 0 in front of it. So we had to expand it because it didn't match the anchor column. The third one is AABBC, which is the anchor value. So we're going to store null. And it's not really null, but a special type of null that means point back and just display the anchor instead. So that's what we're storing here for this first column. We translated it to be in terms of that anchor record. Similarly, for the second column here, we have the first value is the anchor, so that gets a null. The second one is AACC, that is the first 4. The third one, AACCDE, well, that's AACDE. That's the first 3 of the anchor row followed by DE. And then the third one, third column, null again, BCB, which means 2, get the first 2, and then put a B after that. And the third one is CAB, which is not the anchor column at all. So we have to say 0 CAB. So this at the end here, this is what prefix compression looks like. And hopefully this makes sense. But again, we're taking this anchor row, this anchor value for each column, and taking the rest of the data on the page and putting it in terms of that anchor value. And we saved a decent amount of space here. But that's not all that page compression is doing, right? So then we're going to actually go ahead and do dictionary compression, which is then going to deduplicate on top of this. So it's going to look for common byte values across all the columns on the page and create a dictionary and store these entries as a 0-based array. And then that's stored in the compression information structure after the anchor row. And entries in the dictionary are only created if a value is repeated in 2 or more columns. So we're going to go back here to our page, how we left it last time, and now we're going to apply this dictionary compression to it. So we're going to create our dictionary here in the compression information structure. And the first thing we're going to do is find, well, the value 4 is in more than one column, and it's twice. So we could actually put 4 in the dictionary. And instead of storing 4 multiple times, now we're just going to put a pointer, in this case, array 0, into that dictionary saying, hey, go to the dictionary, get the value from the dictionary, and then apply that dictionary value to the anchor value to translate back into the value that was being stored beyond that. So we saved even more space by deduplicating now. Second thing, we can do the same thing with 0 CAB because that's stored multiple times in more than one column. So now we can say, hey, that's dictionary entry number 1. So there we have it. We took this page and we actually compressed it down using both header or prefix and dictionary compression. And now that I did that, we're going to go back here and we'll move to the rest of our demo on that. Okay, so I'm going to use the same data I did last time, but now I'm going to take our mini table with 100,000 rows and I'm going to rebuild it with page compression instead of row compression. And that'll be pretty quick again. And now let's see what page compression did to the size. Remember, we were originally at a little over 12 megabytes, and then we got down to a little under 11, and now we're at 5.25. Right, so we shrunk this over 50% from the original uncompressed size using page compression, right, by deduplicating and building these dictionaries and whatnot. So that's awesome. Now, if we want to see, again, like what's this actually physically looking like via DBCC page, we're going to go and get the first page of the table again because it changed when we rebuilt it. We're going to grab that page value here and move back to our other window, plug that page value in and run DBCC page and see what our data looks like now. So we're looking at our page again. We still have a page header and allocation information, but now we have the interesting stuff. We have, and I'll zoom in here, you can see we have compression info, right? This is the compression information part of the page, right? And it's going to spit out the raw bytes for us. And if we scroll down, we'll start to see a bunch of the data from our data set that's pretty repetitive. For example, we have all the makes and models of cars in here, right? Buick, Dodge, Ford, Honda, Hyundai, lots of those in that data set. So those are being put in the dictionary along with a whole bunch of other information that's repetitive. We also have information I'll show you real quick in here. We have page modification count that's kept track of, and we'll explain why on the next slide when we're done with this demo. We have some header flags showing, yes, this CI has both a dictionary and an anchor record. And then we move down into our column descriptor array, because again, this does contain the row compression before the page compression. So we have the row compression information again, and then we have the actual memory dump. If we scroll down a little further here, we have entries pointing to that. And let's get down to where we can actually see, this is the dictionary it's going through here. We can actually see a record. So here's a record, a real record. We'll take a look at this. We have our column descriptor array, but let's get down and see the actual columns themselves. So, right, column 1, whereas it was a physical length of 8 and a length of 4 before, it's actually 3 now. It was able to shrink it a little more with the page compression. Some of these actually went down to 0, right? We have the state, which is Illinois, again, Chicago tickets. So we'd see a lot of records from Illinois. So Illinois is actually in the dictionary at this point, which means the physical length being stored is nothing, right? So length 2, physical length 0, same for passenger vehicle below it. So now we're getting much more compression out of this dictionary and deduplication that's taking place. And because of that, we were able to save over 50%, right? So that is that. I will point out very quickly, if you'd like to find out how things are compressed with row or page compression, that is, it's at the partition level. You can actually compress things differently per partition. So I have some queries here where you can run and see all your partitions and see how they're compressed, right? So the main table is not compressed at all. The second one is in page compression. I have some other demo queries here. For the interest of time, I'm going to gloss over these, but you can see what features are being used by the database that are enterprise or used to be enterprise. Compression is no longer an enterprise feature as of SQL Server 2016 Service Pack 1, but it still shows up in DB persisted SKU features. So you'll see it here listed. And then there is a compression savings stored procedure you can run that will actually go and simulate for a data set how much space can be saved. Okay. So with that, I'm going to drop this table really quick and we'll move back to our slides here. As I said here, we'll talk about this a little bit more. Compression information structure that we went that contains that dictionary and that header row, that is rebuilt on an all or nothing basis. And it's not rebuilt every time you update a page. So if you just update a single row, it's probably not going to trigger a rebuild. I showed you how page modifications are actually tracked in that compression information structure. And the way it works is if the page is modified more than 25 times, or if the more than 25% of the number of rows on the page are modified, then it's going to try to rebuild the compression information structure, but it's only going to actually do it if the rebuild creates enough space for 5 or 25% more of the rows. All right, briefly, I'll gloss over the syntax, but this is done at create or rebuild time. You set the data compression value to none, row or page. You can do this on tables. You can do this on indexes. You can also do it on individual partitions. So you can change your compression up and say, I'm going to partition this index where, partition number 1 is row compressed and partitions, all the others are page compressed. You can actually do that with the compression syntax. You can rebuild individuals and decompress. If you compress the clustered index of a table, your non-clustered indexes do not inherit out of your compression settings. They are completely separate. And if a clustered index is created or dropped, the result will inherit the compression setting that the heap or the index had. So it's not going to just change the compression because you created or dropped a clustered index, is what that's going to do. Common questions I get, big one is data compression and TDE. How does that work? Do they play nicely? Actually, they do. If we go back to this diagram I had here where I talked about how the access methods was where compression takes place. So everything in memory and on disk is compressed. Well, TDE encrypts everything on disk, right? So at this point, we are encrypting data that has already been compressed. That will work absolutely fine. If they were switched around, if we were compressing data that was already encrypted, that would probably not work very well for us, because remember, compression is trying to find patterns and eliminate duplication, whereas encryption is taking something that has patterns and duplication and making it look more or less completely random, whereas most compression algorithms probably would not get you very far at that point. This is not backup compression. This is shrinking the data in the database in hopes of fitting more data on a page, whereas backup compression is another proprietary algorithm that's compressing the backup stream for sole benefit of making the backup files smaller. You can use backup compression on a database that's using row or page compression. Your backup compression will not compress quite as much. You won't get the same compression percentage than if you were compressing data that was not row or page compressed, but they will play nice together and they will work. There's nothing that says you won't. If you're trying to deduplicate your backups or something, generally you'll get farther with deduplication if you don't have row or page compression enabled, but this is something you would need to test in your environment with your hardware. So what can't be compressed? I know we had with these methods, I know we had a question about that earlier. You can't compress system tables, and you can't compress anything that's not on a data or an index page. So if you have like binary or lob data or file streams or nvarchar max, those will not compress with this method. How much space do you save? Well, it really depends. It depends on the data you're trying to compress. So if you have proper data typing to begin with, you're probably not going to save a whole lot in the way of row compression. And if you have not a whole lot of repeating data, you might not get very far with page compression. But again, you can use SP estimate data compression savings to try to estimate that. That's going to go ahead and reads like 5% of the data into TempDB, basically goes and reads every 20th page, and then we'll try to compress that data and extrapolate the results for you. And finally, about compatibility here, row and page compression that we talked about were introduced in SQL Server 2008, and it was Enterprise Edition only at that point, but then in SQL Server 2016 Service Pack 1, they removed it from Enterprise Edition, so you can use it in Standard Edition now. Also, if you are using sparse columns, you can't use row or page compression. In all my years, I've never come across an environment that was actually using sparse columns, but because sparse columns is a different type of row storage technology, it does not play well with the compression features. And if you want to know when to use it, it's most effective on tables with a really high number of scans, or data that's seldom accessed is great too. Should you use compression all the time? You can if you have the CPU to burn. It's got some intelligence in it to where it's not going to compress things where it knows it can't actually save space, so it has that working for it. I'm not a huge fan of the environments when I come into sometimes, and there is an edict from on high, all tables will be created with page compression. Why? Because we said so. Based on what? So that's kind of where I don't think you should blanket use it, but if you do, it's not a terrible thing, especially with the power of the CPUs that we have now. Remember, this was like a 5% CPU hit back in 2008 when this feature came out. Hopefully you're using way better hardware than that these days. What if my storage array does compression? Sorry, I'm trying to preemptively ask questions here. If your storage array does compression, if you got a new hot storage array, test it out, try it. Your storage array probably has big honking CPUs that can dedicate a lot more time to a lot better compression than SQL Server, which is trying to compress and decompress this data and service all your queries and everything else that's going on. So you'll probably get better compression from a storage array, and you're not using the database CPUs to do this work. One of the bigger downsides is your data will not be compressed in memory anymore. But again, if your space saving on disk is worth it, that might be worth it for your environment. But this is something you really need to test. John, I'm sure we have more questions.
We have a whole slew of questions.
Oh dear.
I've been typing nonstop. So.
Oh God. Okay.
and I'm going to try to pick out some questions that are related specifically to like page compression, since that was the subject you're on.
Okay.
So Tim Brown asks, is the prefix a set size / list of sizes, or is it arbitrary?
It is, as far as I know, it's arbitrary. That compression information structure is not a set size. So I think it's, if you have a varchar 1000, I don't think that's going to end up being your prefix, but I do not know of a maximum if there is one.
Okay, so Frank asks, is the anchor row always the longest value in the column?
It is the longest value with the most common prefix in the column. So it might not necessarily be the longest value. It might have been that in my my demo, they also happen to be the longest, but it's the longest value with the most common prefix.
And there's Frank's, okay. London DBA asks, for a high OLTP table, would you recommend using row compression over page compression?
I would recommend testing and seeing. I think page compression could also work well for a high OLTP table. Row compression will be a lower hit, right? Nothing's free, so every time we do a little something, we're using more resources to do it. Row compression would definitely be less of a hit, but I bet you the hit for page compression would also be trivial, at which point you might want to try that if it saves you more space.
Okay. Blake asks, would you recommend page compression on a table that has a high number of inserts, updates, deletes, or would that just cause it to rebuild too often?
I would recommend testing. This is one of those things where you need to see how it performs in your environment on your hardware with your data, is what I would say. I do not shy away from saying you should at least try page compression, but try it in dev, try it with a real workload on some real data if you can, and see if it makes a difference or not.
So I've got, how about three more? Can we do
Sure.
3 more?
Yep.
And you got about 15 minutes, I think, time-wise.
Yep.
Tim Brown asks, can you compress table variables?
Can you compress table variables? I do not believe so. I'm not 100% sure, but not that I'm aware of. Let's put it that way.
Okay. 2 more. Andrew Jackson asks, how does each compression type influence index seeks? I'm guessing that the compression only applies to the table data and not the indexes.
So the compression, well, it applies to, if you compress the index, it'll apply to the index as well. It doesn't apply to the upper rows of the index, but it will apply to the index itself. So what was the question again? Does it apply? Was that it?
How does each compression type influence index seeks?
It doesn't influence them, other than it's a bit more work to decompress the value as it's looking it up, would be my thought.
Okay, and we have a question from, and I apologize, I'm a horrible American. I'm gonna mispronounce the name. Marcy, what happens when we have row compression and we update a value from int? He says int to int, but I'm guessing he's going from a tiny int to an int.
From a tiny int to an int, so it won't stop you. I believe what's actually happening behind the scenes, because it's compressed, I believe it's a metadata operation at that point, is my first thought, at least. There's members of the product team here who are telling me I'm wrong. I'd love to hear your answer, but I don't believe it would cause an issue to do that. That'd be my thought.
I've never tried.
Yeah, I haven't either. Hopefully.
Okay, so,
Argenis says, yeah, he's all right. So maybe that means I'm right. Maybe he's talking about someone else. Probably someone else.
I think he's commenting about my horrible American, because
there we go. All right. So cool. All right. Thank you. I'm glad we're getting good questions. I'm glad people are enjoying this. All right. We're going to keep moving on here. We're going to talk now about Columnstore, right? Which is an awesome technology that I could probably spend a few hours on, but we're going to try to boil down Columnstore a little bit. And Columnstore has changed over the last, 9 years now. It was first introduced in SQL Server 2012. So just briefly, if you are aware or not aware, Columnstore was introduced in SQL Server 2012. At that point, it was for non-clustered indexes only. It was read only, and it only worked in Enterprise Edition. So if you built a Columnstore index and you wanted to update the value, you had to drop and rebuild that index, right? It was kind of horrible. It was there, but it wasn't incredibly useful at that point. There were a lot of people, including yours truly, going, okay, how do I make use of this in a useful way? But they kept getting better, right? In SQL Server 2014, they added updatable clustered Columnstore indexes. So now you can have your data stored in a clustered Columnstore index. It was still Enterprise Edition only. And you could not have any secondary indexes on data that was stored in a clustered Columnstore index. 2016, things got way better because they added non-clustered column store indexes that were updatable now, so the data could be updated. You could also create secondary B tree indexes on that, and big thing, they made it available in standard edition, which was awesome. You needed 2016 Service Pack 1, same thing as the row and the page compression. And in 2017, they added adaptive query processing for tables that had column store indexes on it, so that it could automatically choose like the physical table join type based on rows and other information it has, and you could add computed columns to clustered column store indexes. And then in 2019, they gave us online building and rebuilding of clustered column store indexes. Now, if you're not familiar with how column store indexes like physically work, graphically, we'll just very briefly go in here. If this is a regular relational table with your rows and your columns, a column store index would look something a little more like this. We have the data that is broken up into groups called row groups. And then within a row group, data is compressed on a per column basis. Okay, a row group is usually 1,000,000 rows. It's actually 1,048,576 rows. One row per byte. That's in a megabyte, actually, is how that works out to 2 to the 10th power. So we have our row groups, we have columns. Each one of these boxes here in the column store is called a segment. So a row group consists of one segment per column. For all that, we also have what's called the delta store, and there are delta row groups. There can be multiple delta row groups per column store index, maybe not necessarily one per row group, but you can have more than one. And then collectively, this is usually referred to as the delta store. And what this is each delta row group is essentially a B tree index, just like a non-column store index or a row store index, we can also call it. And this has information about what has changed. So if you insert rows into a column store index, they don't get added to the actual column store immediately. They get added to a relational table or relational structure in the delta store. Similarly, if you delete rows from a column store index, the delta store gets modified there. And when the column store is read, the delta stores are checked and then changed. The output is changed based on the contents of them. And then as delta stores get larger, the column store row groups may need to get rebuilt behind the scenes. This is done by a process called a tuple mover that handles that for you in the background. So column store compression algorithms, there's actually a whole bunch of them. I just talked to you about how row and page compression works. Column store has a barrage of algorithms it can use, and you don't get to pick. When you say put a column store index on this data, the engine is going to go through, profile that data, try to figure out what's best, and then build based on that. So we're going to talk about what some of these are. Column store indexes are still kind of a black box, so I don't know all of the ones that are involved, but here's some of the ones that I do know exist. One of the simpler ones is called value-based encoding or value scale, and this is trying to create a mathematical relationship between values and what we're storing. This works only for numeric and integer types. So let's say we have a column here with some integer values in it, and we profile this column and we see our minimum value is 1105, our max is 1122, and because of those values, we need 11 bits to store these values for each row. Okay, if we're doing value-based encoding of that, well, we can just simply subtract the minimum, right? And now our minimum is 0 and our max is 17, and that only requires 5 bits per row to store. It will create what's called the base value, which in this case is 1105, which is the minimum, and subtract that, and now it takes a whole lot less space to store this information and to read it back. While we take the values we're storing, we add our base back to it, and there we go. And this doesn't just have to be subtraction. This can be other mathematical operations that are more complex, but subtraction is great to show for demonstration purposes. So that's value-based encoding or value scale encoding you can do. There's called a bit array version where it will take and make a bit column for each distinct value found. So if we're working with a column here that contains blood group information, that's pretty distinct. There's only 4 different major blood groups, right? So what it would actually do is create a column for each of those and then set the bits for whichever one the value is in. This can speed up things like predicate search, right? We don't have to scan the information to see what values are in there. We can just read the column headers. We know it that way. If we're doing joins, we can actually join against a bit mask that we have here and get our results that way. So this is, if you have a very small number of distinct values, this might be something that's chosen. We also have dictionary encoding, right? Dictionaries are great for compression. We've been talking about them this whole time. So let's say we have our parking ticket information again and vehicle make, right? So we have some Chevys, some Ford, Audis, Teslas, etc. We encode these, we can create a dictionary, And now we're storing a numeric ID, which takes a lot less space than all those strings, right? And if you think about it, what this dictionary kind of is like creating a lookup table in a relational database, right? So we have our lookup table, which is the dictionary, and now we're just storing the value or the ID for that. So the number of bits for ID is much lower, and this also kind of makes it data type agnostic at that point, because our dictionary can have whatever in it, and we're just working with numeric values. Touch on Huffman coding again briefly, just to talk about how, as I said before, it's an optimal prefix algorithm, and what basically it will try to do is determine which values are most common and represent those with fewer bits. So if I have information about cars again, you know, Chevy is one of the major brands, at least here in America. So you're most likely to find like a Chevy or a Ford, as opposed to a Bugatti, right? They make very expensive cars. They don't make a whole lot of them to begin with. So we would give that a higher ID that requires more bytes to store. And that actually saves us space in the long run, because the most common values take the least amount of bytes to store, right? It would take 1 bit to store a 0 or a 1, 2 bits for a couple values beyond that, etc. So we can use the frequency and the probability of the occurrence to actually determine what gets stored there. There's also another one here, is called run length encoding. This is where we can avoid repetition by grouping values together. This depends on the repetition pattern of the data, and your efficiency will come from that. So if we have a color column and we're storing red and blue, and we have 105 reds in a row and 92 blues in a row, we can actually just store the count, right? And we know that the first 105 rows have a value of red, and the second 92, the blue ones have 92. So we can save a ton of space, right? We're not even storing every row individually anymore. We're just having a summary of this, basically, is what we're storing. Get great compression out of it. But it depends on the ordering of your data. If your data is ordered differently, and now we're alternating between red and blue, well, now it becomes less efficient. We need to alternate our run length data set at that point. So depending on your ordering, it may or may not use it. Can also combine run length encoding with dictionary encoding. So we'd have a dictionary we'd create, whereas now we have numbers, and now our run length values being stored are all numeric instead of containing text, and we can save some space that way as well. And now with that, I'm going to move to, very briefly, my Columnstore demo here. We're going to go back, and I should have had this building in the background. Dang it. Okay, I'm going to kick off this build of this Columnstore index. I'm going to build a Columnstore index on the entire data set, which is going to take about 1 minute and 10 seconds. So while that's running, I'm going to work through a couple more slides here real quick. Columnstore compression syntax is basically, it's create clustered Columnstore index or create Columnstore index with data compression equals, and you get a choice. You get Columnstore or Columnstore archive. Columnstore is the default. If you don't specify anything, that's what you'll get. Columnstore archive basically takes the Columnstore structure and compresses it again on top of it using something probably like LZ77 in some modified form. But what it's doing is it will get you even more space savings at the cost of even more CPU effort to retrieve it. But if this is data you need in a Columnstore and you're not going to look at very often, that is exactly what they put it there for. All right. When should Columnstore be used? Well, if we have queries that scan really large amounts of data, especially on really large tables, if we have data sets with really repetitive values, we have any kind of data warehousing workloads, if we're doing real-time analysis on OLTP workloads, these are great use cases for Columnstore data. My thing is still building, but it should be done any moment now. When should Columnstore be avoided? Small tables, and I use small in quotes, tables under 1 million rows, they won't really benefit because it won't build a segment until it has about 1 million rows to work with. So at that point, you'd have a Columnstore, but everything would really be in your Delta store and a B-tree structure, and it'd be no different. If you have columns containing lots of very unique information, Columnstore might not be able to help you with its compression. If you have lots of queries that just scan an entire table and return all the rows or are frequently updated, Columnstore isn't going to be a panacea for you and solve everything there either. I've seen so many environments I've come into where I'm doing performance tuning, and they'll be like, you know, well, I put a Columnstore index on it and that still didn't help it. Well, Columnstore indexes won't fix everything. Okay, back to our demo really quickly here. We built a Columnstore index on about 5 columns in this table: ticket number, license plate, license type. We can query some of the metadata. So I'm going to query sys Columnstore row groups, and it's actually going to show us the row groups that were created. We have about 37 million rows in this table, and you'll notice that it actually created 36 row groups. So there we go. Most row groups, I'll zoom in just to show you, have that maximum number, 1048,576 rows, and the couple at the end have a few less. But that's how it does the row groups. If you want to see what happens if we add a row to a table, here I'm just going to insert another row into my table, and then we'll come back and we'll run that query again just to look. Now we have another row group that was added at the end, but you'll notice here, and I'll zoom in, this one says open, and it has a hopped ID for a table structure for that Delta store that contains that open row, because that row we inserted is not actually in the column store index yet. If you want to look at the segments that are in the column store index, you can run this query and see the various segments. There are lots of them because there's 37 row groups and times 5 columns. So a whole bunch of segments that get returned there. If we want to do some additional querying here, I know I'm just about out of time. I'm going to grab a hopped ID and I'm going to show you the dictionaries, and then we'll go for the big kahuna here. We're going to open in a separate window. I'm going to run a different undocumented command. You may have heard of this, you may not. It's called dbcc cs index, right? This is like dbcc page, but it will display for you graphically the contents of a column store index. So we can look at that again really, really quickly here. Yoink. And see for column number 3, which is license type information. Uh-oh, incorrect number of parameters. What did I screw up? I've done this before, I promise. Hang on. I wasn't even typing, I was copying and pasting. Try this once more, and if it doesn't work, we'll nuke it, but I promise you this is a command that works. dbcc cs index parking tickets, grab the hopped ID that I need, and plug it in there. And it is failing. I don't know what exactly happened here. Why it's not doing that. Okay, we're going to abort this demo, my bad. Anyway, if you use dbcc cx index, you can actually unlock the contents of a column store index and see what is in there, how things are being stored. It'll actually show you in the column store segments column what type of compression is being used. I broke something good here, didn't I? Oh, because I have that hopped ID that I can't use. If you plug that in. Anyway, we're just about out of time, and I want to leave time for questions. So first, I will point you, if you have any questions, I would like to see further resources on this information. Here's some. There's even more at my website or on the 8KB page. I'll have the list there as well. If you go to bobpusateri.com/r/compression, you can see all that. John, do we have any questions we can follow up with quickly here?
Do we have questions? You're going to get a small booklet of questions I have listed.
Awesome.
So first up is, and again for the attendees, if I don't get to your question, I have them all documented. I will make sure Bob gets to them. Hugo asks, are we able to see which column store algorithm was used in a certain table, like dbcc page?
You are able to see it from that that demo code I had up there. It will actually show you, where is it here? Encoding type. So it will actually display, you don't even need dbcc page to see this. If you go to sys.columnstore-segments, that will show you the type of the encoding that's being used on the segment, right? So not at the table level, not at the column level, but the particular row group for that column, which is the segment. You can actually see what type of encoding is being used there.
Excellent. Max asks, is clustered column store applicable on per partition basis, just like other compression?
Is clustered column store applicable on a per partition basis? My first thought is no, because it's clustered and it has to contain all the data, but I haven't tried that. Someone can correct me if they're wrong.
Okay. Arthur asks, how can we monitor actual compression overhead? Are there any perfmon counters or weight types associated with that?
I do not know. I will have to look that up. I'm pretty sure there's perfmon counters for column store indexes. I do not know if there are specific weight types for that, though there probably are.
London DBA asks, any DMVs that show us the contents of info for the Delta store tables?
Not that I am aware of, though you could definitely look it up with the hopped ID via dbcc page and see what's in there if you wanted. But yeah, not sure.
Okay. Thank you very much. Matt asks, how does table partitioning affect, oh wait, we might have already asked that question. Anyway, how does table partitioning affect column store indexes? I think that was asked and answered already.
Okay.
Looks like, already asked that question. Sunho asks, if two partitions on a table are compressed differently, row, page, column store, what happens to the compression when you merge the two partitions?
That's a really good question. I've never tried that. I assume you're
tried
either going to get an error or it's going to pick one. But yeah, I should have made this a little bit longer session. I apologize.
And I do have a follow-up that earlier in the earlier question segment from Marcy about we thought it was going from a tiny int to an int.
Okay.
Really, they clarified the question about if that column has a small value like the 5, and then you went from, and you have row compression, but you updated that column value from a 5 to that, 2 million and change, or 2 billion and change, what happens?
What happens at that point is the row will grow in length, right? Because we need more bytes to store that value. So that'll be a matter of, can the row fit on this page still? Does it have to move somewhere else? Do we have to split pages or whatever? And the column descriptor information will change to show that this is that this is now a wider column and it needs more bits to store.
If they don't have any room on the page, then it would split the page and move it, right?
That would be my first guess. Would be that's how that's going to happen at that point.
Okay. And so there was another, I think, related question. What happens if we change from tiny int to like a big int?
If you change the type of the data, the data type of the column. So at that point, I'm not sure if it actually needs to rebuild the table or not, because in theory, it could be a metadata operation because everything's being stored in a state where it's using the least amount of bits that it needs anyway. So it might just be a metadata update, but I'm not exactly sure. I should probably write a blog post about this and find out.
And there was a question from Antonio, but I don't know if Argenis had answered that or not. How much regarding percentage of DTU in Azure could penalty page compression in an Azure SQL database?
I don't have any idea on exact numbers, but my first thought it will be a minimum impact, just like it's going to be a minimal CPU impact in general if you're not even running in Azure.
Couple more. I don't know what's our time limit.
I think our next person is starting in 9 minutes, I believe.
All right. So how about two more? I think that'll wrap everything else. So I think everything else got answered somewhere. Iowa asks about Columnstore. We had an issue with Columnstore and always on sync availability groups. At some point, the sync process would get overwhelmed and the queue of updates would shoot up. The process on the sync database would block any select statements from relevant tables, defeating the purpose of the secondary replica.
Wow.
And so there's an issue with ETL that was deleting latest day's data and reinserting it. Have you ever experienced anything like that? And if so, what advice would you have?
I have not experienced that. That almost sounds like something I would maybe consider contacting support about, just asking, is it supposed to happen like this or not? Because that seems kind of like it shouldn't block at that point, but not totally sure. And it never hurts to ask support.
Okay, so one more from Goran. When I look, it seems the numbers sized used in the database file and the actual size of the backup file follow each other. Is that just accidentally so, meaning the compression is just removing white space?
The size of the data file and the size of the backup file follow each other. Is this for a compressed backup or just for the data compression? Because
they don't clarify. They just
forget compression, right? The backup file is going to contain the data that's in the data file plus the active portion of the transaction log. So I would generally expect the file sizes to follow each other. Similarly, if you have data compression, if you apply data compression by itself, your data file is not going to shrink at all. It just might have more empty space in it. And then your backup of that would be only the portion of the data files that you're using. So I would expect your backup size to perhaps be smaller at that point when compression is involved, just because there might be extra space in your data files.
So they did clarify that it's for a compressed backup.
Okay, so if there's a compressed backup, then it's not might even be linear, but either way, it's going to be writing, it should be smaller than at that point than your data file sizes.
Okay. I think we have almost everything asked and answered.
All right.
So I know we're about out of time, but I do have all the questions captured for you, and I will make sure to send you that list that I have.
Awesome.
And I assume that people can email you or contact you with further questions and follow-ups.
They can reach me out to me and contact me. I will write a blog post answering the questions that John sends to me. And thank you all so much for watching. I hope you enjoyed it. Sounds like we had a lot of questions at least. And let's get out of the way here so Gail can get ready for her session.
I will tell you that my mind is kind of between handling all your questions, and that was just capturing the questions, but mind melting content. It was great. Great job.
Thank you so much.
Absolutely fantastic session there, Bob. Huge discussions going on in the Slack channel as well. Yep. So you've got loads of questions, loads of discussion going on. We need a prize, Anthony, for the first person to mention DBCC page in 8KB.
Right.
So fantastic, cool. And a new command as well that I didn't know about mentioned as well. So fantastic.
I agreed. I didn't know about that one either.
Kind of sad it didn't work. It works, I promise, but I'll figure out why it didn't work in my demo there. But yeah,
I'm pretty sure very that's good. The best compression presentation that I've ever seen in my life.
Yes.
Yeah. Well done. I'm gonna grab the screen.
All right. Yeah. Please feel free. Thank you so much, everyone. I really enjoyed it.
I really liked the Winamp reference, which I know Anthony mentioned on Twitter, but
really kicks the lemons.
Awesome.
I saw that and I was like, ooh, nice.
Yep. So please leave Bob feedback. If you go to the 8kb.online/feedback, click on his link session. Please let him know what was good, what was great, what was fantastic, and any other comments as well. And we'll be sending out all the feedback to the speakers after the event. So I'll leave that on the slide there for a little bit. And then next up, we have Gail.
Woohoo. Yeah, I think the combination of the Winamp references and pictures of core memory. It's really digging deep.
Yeah, Bob, I think I'm in that data set too from when I lived in Chicago.
Oh, the tickets?
Yeah.
So when I would present that in Chicago, we would have people give us their license plates and we'd look them up.
That's a fun data set. I've never seen anybody present with data quite like that. So that's pretty cool.
So there is a question about the conference or the session being recorded. I'm going to point them to the YouTube channel.
Yeah.
Right.
Yep. Absolutely.
Yeah, go to 8kb.online/streaming. It'll take you right to our YouTube channel.
Yeah, and or Mark mentioned earlier, the whole conference will be available immediately, and then over the next couple of days, we'll break it up into the individual sessions in the channel for you.
Yeah.
Last time we even had somebody, just a random YouTube watcher, put time markers on the video for us so you could skip around.
So, fantastic.
Thank you, community.
Yeah.
And it's SQLcommunity.slack.com. That's the Slack channel.
That's the Slack channel, yeah. If you want to sign up, you need to go to dbatools.io/Slack, and that'll take you to a sign-up page, because for some reason, the login page and the sign-up page for Slack are two completely different things.
Of course, because that makes sense.
Mm-hmm. Okay, so have we got Gail online?
Oh, she's there.
I've seen her typing.
I see her video.
I think she's frantically looking for a way to talk.
Oh, yeah, cool. Yeah, usual Zoom issues that can occur. We've all had, me and Bob have had a couple of those this morning, so.
Just a few.
Yeah.
Couldn't even tell you were on your backup computer, Bob. That was pretty awesome.
Yeah, that really saved my bacon.
And kept you warm, right? Because, you know.
That's true, actually, yes.
You said it was between your legs. Were you literally on your backup computer? Were you sitting on it?
I didn't have the room to put it in the right spot between my desks, so it's literally just sitting in the middle here.
So Bob, your question, you had the question about, Joey helped clarify. It was if you could create a filtered index, right, on a non-clustered column store. That was one.
That one I have.
That might have
I
been
will
the
have to
Slack
look.
channel.
That I did look for you. You can, because I didn't
Okay.
know.
Oh,
Yeah,
awesome.
you
Okay.
you can.
Cool.
I don't know when, right? Joey and I were like, when would you do that? But
Yeah. So there's this mysterious use case that Microsoft Marketing talks about that I've rarely run into called hybrid transactional and analytical processing. In the example they always use is like ticket sales. So where like you would want to be able to have really fast inserts on a regular table and then report like from like an hour ago. But you kind of have to constantly be rebuilding the index. So like
that sounds messy.
It's not a scenario I've encountered in the real world.
Yeah.
And then Bob, the two other questions I think that you weren't sure about were partitions. Partitions have to be the same compression type in sys partitions to be able to be merged.
Okay. Makes
and
sense.
I think there was a transaction log question, and all compression shows up as row compression in the transaction log in terms of page and row. I don't remember about column store.
Cool. Thank you.
So I don't know what else you guys are doing in the background today, but I'm working with bulk loads and format files. Does anybody want to change?
Actually, Aaron, do you want to swap? I'm marking grad homework.
Yes, I would love to mark grad homework. That sounds fabulous.
Well, there we go. There's Gail. Gail, you can grab the screen off me anytime.
Okay. So the problem with the microphone was the volume. The Zoom's automatic adjust the gain on the microphone doesn't work when you've got gains at 3 other places as well.
Yes.
That's what I get for using the Rode. Just to clarify, is this loud enough? Is this acceptable? Or do you want me to turn something up somewhere?
Yeah, you sound great.
You sound great.
Because I'm working with the big mic tonight. I don't normally use this thing. Yeah, Aaron, if you saw the quality of some of the stuff I'm marking, you might take that back.
I just remember being in grad school and getting papers back with like red. Susan would just put red all over. And I'm like, oh.
The last team whose work I just marked, my comment to them was, did you read the question? How did you test your code? Did you test your code? This doesn't even run.
Would anybody want to take a class from Gail? What do you guys think?
Oh, hell no.
Oh,
come on.
I refuse.
Not that bad.
I would view it as a challenge. So, yeah.
No,
That's the right approach.
Yeah, I'm going to stop sharing my screen. There we go.
Thank you. I'll grab that. This is my my company's graduate training program. So this was not an advanced class. This started with, this is how you write a select statement, and got as advanced as cross-apply and procedures. This is basics. We assume they can't write code. We usually write. Anyway, I think I'm supposed to get started, so let's get straight into this. Good evening, everybody. Actually, do I have a moderator around here? Joey.
Yeah, it's me, Joey.
Okay.
Yeah, I'm here.
Okay. So I introduce myself. Nobody does that for me.
Yeah, go ahead.
Okay, cool. I'm
really sorry. That was my bad. I was going to let you. No, please. Yes, sorry, I'm dropping the ball here, Gail. I do apologize. Now we have Gail Shaw with Intelligent Query Processing.
Sweet, thank you. Now I can actually get started. So not digging Andrew, stuff slips. And Aaron and I were kind of making a nuisance of ourselves. So moving right on. This, I hope, is an advanced enough session for this conference, because it wasn't written for this conference. This was written for actually past Summit, 4 or 5 years ago, and I've updated as we go along. So what I'm going to be talking about tonight was what was introduced in SQL Server 2017. That would make it 3 years ago past Summit, because it couldn't have been 4 years ago. Time flies these days. what was originally called adaptive query processing, but was quickly changed afterwards to be called intelligent query processing. This is the ability of the query processor, in some cases the query optimizer, to identify particularly problematic portions of queries and to treat them specially. So let's start with the problems. The problems, and these are very familiar to anybody that's done query tuning for SQL Server. The problems are that bad row estimates cause incorrect row estimates, bad row estimates, cause bad performance. Horrible problem. We've probably seen this multiple times. The second problem is that multi-statement table-valued functions and table variables cause bad performance, to the point that I will often suggest to somebody, if they've got a performance problem with a piece of code that uses table variables, try replacing it with a temp table and see if that makes it better. And if it does, great, we're done. If it doesn't, then we'll actually dig into what caused the problem. Third one, inadequate memory estimations cause bad performance. And this is another quite problematic one. Adam Mechanic's got a whole pile of very interesting presentations and tricks on this one. But for most of us, once your query is getting incorrect memory estimates, you've got bad performance and there's not much else you can do about it. And then lastly, scalar functions cause bad performance. I affectionately refer to scalar functions as developer pit traps, because I've seen so many developers run into them at high speed, not realizing that there's a problem, and get really, really, really badly burned and hurt as a result. So those are our problems. You can ignore what I'm keeping on screen. Those are our problems. And all of these are ones that adaptive query processing, intelligent query processing, in its 2019 version, address. Most of these were addressed in 2017 as well, not all of them. It took as long as 2019. All right, so let's go into this. Before we go into the details of the various options, why? Until SQL 2017, the optimize execute process was linear. A query was optimized, then a query was executed. And there was no ability for the query processor to go, I don't like this plan, it's slow, redo it. There were recompiles. There was something called a recompile, but this only happened in two cases. This happened if the statistics had changed prior to, if the statistics used in the generation of the plan changed after the plan was generated, but before it executed. Or if the schema had changed after the plan was created, before it was executed. Those were the only two times where the plan would be thrown out as invalid and regenerated. But even if that happened, those recompiles started before those recompiles occurred before the execution started. The process was fetch the plan from cache, validate it, and that validation is checking statistics changes, schema changes. If the plan is valid, run it. The query processor had no ability to, partway through execution, go, this nested loop was estimated to run 10 times. I've so far run it 10,000. This plan's wrong. The query processor had no ability to decide what to do. It took the plan, it executed the plan. If that plan was invalid for any particular reason, if that plan was inefficient for any particular reason, too bad, sucks to be you. I hope you enjoy waiting 20 minutes for this query to execute, because the query processor will simply run it. Because the optimizer decides, the optimizer estimates the rows, the optimizer chooses a join, the optimizer estimates the memory, and then the execution engine requests the memory, executes a plan, that's it. And it's that that's changed with intelligent query processing. Not completely, not 100%, but in some places. So there are 4 aspects to intelligent query processing that I'm going to be talking about tonight. And they are adaptive joins, interleaved execution, memory grant feedback, and my favorite 2019 feature, inline scalar functions. Favorite for a couple of reasons. One being that it blows up quite badly in some cases. Let's start with the first of those, the oldest one, adaptive joins. Let me go back. Traditionally, if we looked at an execution plan, it had a nested loop join, a merge join, or a hash join. And which join it was chosen by the query optimizer based on the estimated number of rows in the outer table. And a few other things, indexes on the tables. There is more to it than just the row count, but the row count was one of the main ones. If the row count on the outer table was low, you got a nested loop join. If it was high, you got a hash join. And merge joins came in somewhere in the middle if you had the appropriate indexes or sort wasn't expensive or a bunch of other things. I'm going to leave merge joins out of this conversation because they actually don't feature in adaptive joins. Adaptive joins is about the hash and the merge. Sorry, the hash and the loop. Hash and the loop. I just said merge joins aren't part of this. With adaptive joins, and this, by the way, let me be clear about this. This is a SQL 2017 feature that is available in databases of 2017 compatibility level or higher. If you're running your SQL 2019 database in compat mode, and a 140, whatever is the compat modes these days, you are not going to see this. You will only see it on the higher compatibility levels. What an adaptive join does is defer the choice of join to after execution starts. The query processor, sorry, the query optimizer does not choose whether to do a loop join or a hash join. Instead, it puts in a placeholder and lets the query execution engine decide. And this is absolutely fantastic because what it means is that if the query plan was generated with 10 rows in the outer table, in the first input, that would be a loop join. If it ran later on 10 million, well, loop joins on 10 million rows aren't pretty because we're looping over 10 million rows. In this case, we haven't chosen the join type. So the query plan is generated with a placeholder in. If the first execution is 10 rows, it gets a loop join. If the second execution is 10 million rows, it gets a hash join. The query processor is allowed to decide which to use. And this is what it looks like. And I've seen some people really confused by this because this is the first time that we have ever seen a join operator in an execution plan that takes 3 inputs. Because joins in the SQL Server query processor and the query optimizer are two table joins. If you're joining 3 tables together, you get 2 joins, not 1. So in a SQL Server query plan, you only ever see 2 inputs going into a join. With adaptive joins, you see 3. So I'm not going to talk the limitations right now. I'm going to go and try and find my demo. I have it around here somewhere. Not that database. That database. All right, let's hope this actually works because this demo is a little bit finicky. I have here a store procedure. And this particular join here between these 2 tables is one where I could get a lot of rows or I could get not very many rows. So let me just do some quick queries against my shipments table to make sure I know what I'm talking about. And I apologize, I should have done this in advance. I'll blame the work meeting that ran till 6:30. I want client ID and I want no schema qualified tables. Oh, I'm sorry. Nitpicky, nitpicky, nitpicky people. I hope we're happy now. Okay, so client 64 is apparently a very busy shipper because 7,006 shipments. And way down at the bottom, I have number 240 that's only got one. I'm not going to use 240. So 64 or 56. One of these days, I'm going to actually save the version of this demo that has all the numbers in it. Anyway, plan's been generated. Store procedure's been created. Let me execute this. It would help if I turn the execution plan on. So running this with 56, I get a grand total of 746 rows back. And thank heaven, I've got an adaptive join. It would be a great start for the presentation if it didn't go adaptive. It would probably be a bad compatibility level. Actually, on that point, let me show you how this works in old compatibility levels. So go here. You should know how to do this, but I can't remember. This is somewhere. All right, so compatibility level, I'm going to switch this back to 130. Script this out so I can do it again. All right, so let me switch this back to 130. Wipe all my plans and find my adaptive joins again. All right, so I've cleared my plan cache. In old SQL, 2016 and before, client 56 gets a nested loop join. Nested loop join, actual number of rows on all executions, 746. Estimated number of rows was somewhere in here. Why can I not even see that? Let's go off this one, it's easier. Actual number of rows, 31. Estimated number of rows, 31. The loop join estimated to execute once. Yep, it executes. That's fine. This index seek was estimated to execute 31 times, actually executed 31 times. So this is actually correct. This loop join is going to loop over 31 rows. This is efficient. This is not so efficient. My index scan down here has estimated, hey, hash join. Why did you go to hash join? That's not right. Oh, what the hell? No. This is not behaving itself. I do not like demos that don't behave themselves. It's supposed to be 56. And this should have been that's a nested loop join, yes. So this should have gone. That looks more like it because it's slow as hell. Nope, gone to hash. Okay, this is fun. I do love a demo that doesn't work, and I don't know why. That's fine. Okay, so this is going to be fun if I can't keep a plan in cache for more than one query. Okay, I've got memory pressure. No, I've got memory pressure. Let me go kill some things. Not PowerPoint, that would be dumb. Close Word. Apparently I did not make the requisite sacrifices before I started tonight. Okay. Hopefully that'll clear my memory up a bit. This is weird though. This machine's got 32 gigs of memory. It shouldn't be having memory pressure problems. Yes, okay. All right, the memory pressure on the plan cache is fixed. No, Forrest, I had worse. I had Firefox. All right, so now I've actually got a plan that's stable in cache. So this index seek, estimated number of executions 31, actual number of executions 7,006. That's a problem. That's not fantastic. That's going to be causing problems. 7,000 rows, not so much. But if this was 7 million, this would be unpleasant and slow. All right, so now let's switch back to 160. I used to know these combat levels off the top of my head. Emphasis used to. 150 for 2019, all right. All right, so back to compat level for 2019. Now let me run this again. Right, and so we've got an adaptive join here. We've got our join, we've got our 3 inputs. Right, the way this works, the top one is the first input. That is the input that is read always before the join type is decided on. For those who are awed that I could fix this, I've had this problem before, so it's not a case of I was guessing. I've had that problem before in this presentation with this demo. This input is read. This input is read, and then the query processor decides which join we're picking based on this input. So 31 rows are read. Estimated number of rows 31, actual number of rows 31. If we hover over the adaptive join, you will see actual join type nested loops. Nested loops, multiple of them. The decision was made by the query processor that based on 31 rows in the input table, we are doing a loop join. The second input you see is the one that is executed if a hash join is used. This input is not always run. This input is run when a hash join occurs. So if we look at the properties of this one, actual number of rows is 0. This input was not executed because we're doing a loop join. This index seek here, the third of the inputs, is the one that is executed if the loop type of nested loop is chosen. So this input, this seek, number of rows read, 746, that's the number of rows in the detail table. This operator was executed because we do indeed have a loop join. You can see that with the size of the arrows as well. No data flowed up that one. Data flowed up that one. So the key for a loop join, yeah, Hugo, shush. The input for a adaptive join, the key to understanding an adaptive join is that one of these is executed, not both, never both. And yes, Hugo's entirely correct. Look at the number of executions. This one is showing 0 executions. It was not run. This one should be showing 31 executions. 31 executions. This one was run. All right, so let's go and pick my other client. That's the 64, the one with lots and lots of rows. And I run this one. We have got exactly the same plan. We've got an adaptive join. 7,000 rows in this one, one execution. And if you look this time, the second input is the one that's been executed. It's been executed once. It's a scan. It will only be executed once. It should only be executed multiple times if I've gone parallel. The index seek has got 0 executions. It's not getting run. And then if we look at our join type here, actual join type, hash match. I've got a hash join here, and I notice I'm still getting recompiles. I shouldn't be, but I am. So that's going to make the rest of these demos quite amusing. But you can have a look at this. You can now see this has done a hash join. It has not done a loop join. I'm not entirely sure where the input stores those rows. It probably is in the spool somewhere. But yeah, so the downside of this is that this input has to be read entirely before the join type can be chosen. So what we've got here is actually a blocking operator. Nested loop joins normally are not blocking operators, but adaptive joins are. I'll take that over waiting 3 hours for a query to execute because we got the wrong bloody join type. All right, let me move that out of the way. So requirements, there are requirements. Move that out of the way as well. This doesn't work in every case. Adaptive joins cannot be used on every single query. The limitations requirements. So batch mode, it requires batch mode. You may have noticed, I've got column stores here. I use column stores intentionally. This demo is from these demos were initially written for SQL 2017, where you could only get batch mode if you were using a column store. So I still use a column store, but if you look, I am actually running in batch mode. So the query, this requires batch mode or no adaptive joins. The query must be executable with an indexed nested loop join and a hash join. In other words, no unindexed nested loop joins. We're not going to be doing scans and spools or any other weirdnesses that you can do with nested loops. We are not doing merge joins. If a join is chosen as a merge join, it is not adaptive. It will not be adaptive. And the query plan shape must look identical for loop and hash joins. So going back to my 130, if I ran these two, so my plan on 130 was an index scan, ignore the filter because it can get pushed down into the scan. Hash match, it's a particular shape. And if I switch this to 56, I intentionally want recompiles this time. It's the same plan shape. So that's another requirement. The plan shapes must be identical other than the type of join. So that is adaptive joins.
Hey, Gail, we have one question on adaptive joins that I don't know the answer to off the top of my head, and it is, adaptive joins make sense for data with non-uniform distributions. Are there query criteria where the query optimizer chooses not to do an adaptive join? And I think you kind of covered that,
absolutely.
But yeah.
Well, other than the restrictions, which are an obvious one, I mean, if it doesn't match these, no join, no adaptive join. Other than those, I don't know, to be honest. I'd actually have to go and bug Joe Sack on this one because I don't know. The thing is, this doesn't just work well with non-uniform data. This works really well when data is changing. So the biggest problems I've seen in the past with the wrong join type being chosen was on the older ascending key problem, where the data was loop join, loop join, loop join, loop join, too big for a loop join, but we've got the same plan. Oh, hell. The data wasn't non-uniform. It was perfectly uniform. It was just growing over time, and we got the wrong plan as a result.
And then we have one more question. Does this mean that it matters for adaptive query? Wait, does this mean that it matters for adaptive queries on which side the table is placed when using it?
No, it doesn't. Again, order of tables in the query has got nothing to do with the order that the query optimizer puts them in. It doesn't care. The query by the time the query reaches a QO, that's gone anyway. It's been parsed out. So no, absolutely not. Fortunately, let's not do that. Okay, cool. So let's move on to interleaved execution. Cool. It took me half an hour to do the first one. So how many hours do I have? I'm kidding. I'm kidding. These are actually faster. All right, interleaved execution. Multi-statement table-valued functions are a problem, or were a problem, because we couldn't get an accurate row estimation of them. So that was where the estimate of 100 rows came from. We estimate 100 rows because how many rows? Absolutely no bloody way to tell. None whatsoever. Because the table function hadn't run at the time that the query optimizer optimized the query. And hence it can't get the row count estimate because there isn't one. And so we get that silly 1 row, 100 row table variable estimate, one row in the old CE, 100 rows in the new CE. That was how it used to work. With adaptive query processing, intelligent query processing, what happens is that the execution of these two is split. Instead of parse, bind, optimize, execute, it becomes parse, bind, optimize, execute, optimize, execute. We optimize the table-valued function first, the contents of the function. That then gets executed. The results of the table-valued function get put into a table variable. Once the function is complete, the outer query is optimized. It hasn't got a plan yet. It now gets its plan. At this point, we know exactly how many rows were returned from that table-valued function because we've already run it. And so we can generate a plan based on the actual row count, not a 100-row estimate. So let's have a quick look at how that one works. So the question quickly on Slack, I'm kind of keeping an eye on Slack, you've probably guessed. Adaptive query processing actually wasn't fine because a lot of the newer features are not adaptive at all. There's nothing adaptive about them. Adaptive was great when it was things like the adaptive join, but intelligent query processing is a larger category, to be honest. All right, so functions, interleaved execution. Where are my functions? Sorry, wrong database again. All right, so I have a really weird little function here. Oh, no, don't tell me oh, crap. I did a demo last week and I dropped a table and I forgot to restore my database after that. So I'm just going to have to apologize and do a quick restore and talk through it. Talk through something so you don't notice me restoring databases in the background. I promise I was prepared for this, really. All right, while that's running. Let me talk about deferred compilation and then I'll demo the two of them together. I've put these in a single section of this slide deck because they are kind of the same thing. So to be clear, interleaved execution, SQL 2017. This was added in 2017. In 2019, they also added what's called deferred compilation for table variables. And they're kind of the same thing. The whole idea here is that we don't optimize and then execute a query that uses a multi-statement function or a table variable until we know how many rows will be returned by that multi-statement function or table variable. So when we've got a multi-statement table valued function, we split the execution, interleaved execution. We execute the function first, dump the results into a table variable, then compile, optimize the query that uses that function to and execute it. With a table variable, we defer the compilation of the query that uses the table variable until after the table variable has been created and populated. In other words, right before that query executes, which means we now know exactly how many rows are in that table variable because it already exists. And so we don't have that 1 row estimate. And by the way, this slide's actually wrong. The 100 row estimate never happened for table variables. That was for functions. Please, pretty please be finished. Not quite. Yeah, I hate these. All right. So to be honest, if you look at the plan, there's nothing particularly interesting. You can't see that you've got interleaved execution if you look at the execution plan. Not easily anyway. Please be finished, not finished. Oh boy. Because I can't exactly run a query that uses a transaction table if the transaction table doesn't exist. By the way, I was demoing SQL injection, and I very intentionally dropped my transaction table as part of my demo of SQL injection. I will let you know that my demo of SQL injection was very effective. I just forgot to restore the damn database afterwards. Anyway, let me talk you through what this looks like. So we've got a function, that shipment total, and this function will look a little weird to those of you familiar with multi-statement functions. But yeah, so it returns a table. There's my table definition, all my stuff here, and here's the query that uses it. Now, why I say this looks a little weird is because this isn't on apply. This is joined. I'm joining this function in. This is definitely an odder use for a table value function. And when I finally get a database back, I'll explain why. So my second, all right. I probably should not have done that. All right. Let me talk about limitations while I'm waiting for this backup to slowly restore. Is this a case of the watched kettle never boils, the watched restore never finishes? Requirements.
We do have one question I can ask you while we're waiting.
Okay. Yeah.
If we have to stream all the records to the adaptive join in order for the execution engine to know what join to select, does that mean it requires a memory grant, which could be huge, which would be strange for a loop join?
Yep, it does actually require a memory grant. As Hugo noted earlier, and thank you, that was the perfectly timed question. It's a hash table. It's literally a hash table in memory. Yes, it does indeed require a memory grant, and with all the caveats of that. So yeah, adaptive joins are not as fast as a nested loop join would be. They're not as fast as a hash join would be. Their benefit is they're adaptable. Yay. Okay. Whew. Now it's working. Okay, let me set my compat mode back firstly. If I run this is running in compat mode 130. This is SQL 2016. If I go and look for my table valued function, and please ignore my missing indexes. I know they're missing. I don't care. My table variable, my function is somewhere around here. Estimated number of rows to be read, 100. This is a table valued function. 100 rows estimated, because how many rows is it going to return? At compile time, we don't have this vaguest clue. Let me switch this back to 150. And we'll note the massively, incredibly different plan. No, it's exactly the same plan. Honestly, there's nothing you can see in the plan that's different, with the exception of estimated number of rows to be read, 2,627. We don't have that 100 row estimate anymore because we knew exactly how many rows the function was going to return, because we ran it before we generated the plan for that query. Now, one of the limitations of this is according to the documentation. Firstly, read-only statements, select only. If you're planning to use a multi-statement function in an update or delete, I'm sorry, firstly. Secondly, you're not going to get interleaved execution. It's only for selects. Secondly, the documentation states that it may not be used on the inside of a cross-apply. Okay, cool. So here's another demo. Here's a function. Oh, come on, crap. Would help if I actually highlighted the whole thing. And I have a cross-apply to my function. This is on the inside of a cross-apply. So according to the documentation, this does not get an adaptive join. Execution plans are useful. But if we go and have a look here, actual number of estimated number of rows. Is that right? Is that right? Well, yes, it is, because duh. Well, of course it's going to be 100 rows because I put 100 rows in here. So let's try something a little larger. Estimated number of rows to be read, 1,000. This is an interleaved execution because it doesn't have the 1,000 rows. So the 100 rows. We make that even clearer. This is an interleaved execution. It's also on the inside of a cross-apply. So is the documentation wrong? Actually, yes, it is. The number of executions must be determinable at optimization time and deterministic. If the documentation has changed, I'll have to fix my slides. What it means is that the optimizer must be able to work out how many times this function runs. And it must be able to work that out at optimization time. And it must always be the same. So if I did this, which is weird, but it'll work. This is now no longer interleaved, and my estimated number of rows per execution is back to 100. So I've lost my interleaved execution. I don't have a demo for table variables, but it's pretty trivial. So what I could do here is no, not values. Not values, not values, not values. Kind of weird, but it works. And if you look at this, I should have here estimated number of rows to be read 265, not the one that you would expect and the one that you would get on earlier versions. I switch back to 130 compatibility level and run exactly the same thing again. My estimated number of rows, that one. Estimated number of rows to be read, 1. That's your table variable estimation. On 150, we had 256. Well, that's not going to work, is it? Because of the deferred compilation for table variables. If I run that now, this is back on 190. Sorry, on 2019 compatibility. My estimated number of rows to be read from my table variable are 265, not 1. Okay, so any questions on deferred compilation or interleaved execution? And by the way, I glossed over deferred compilation, but I did put 2 posts on my blog quite recently, this year, in fact. Actually, no, last year. One was last year, on deferred compilation and table variables. So you can go and have a look at those if you need. Joe, any questions? I hear silence, so apparently no questions.
It's because I was muted. We had one on recompilation, and I just answered it live.
Cool. That's a nice thing about having a moderator that knows your topic. All right, moving on. Memory grant feedback. This one is complicated. This one, oh boy. All right. Queries that use hash tables, that's a hash join or a hash aggregate, spools, a bunch of other query operators need memory grants. It's a piece of working memory, a piece of memory that is used for the query. This is not the buffer pool. This is not the plan cache. This is a little bit of memory that the query needs in order to do stuff, interim results. The memory grant needed is calculated by the query optimizer. How? It guesses. Look, it guesses pretty well because it's based on row counts, estimated row size, a whole bunch of heuristics, and any one of us who have been optimizing queries for a long time knows that it gets it right a good amount of the time, but when it gets it wrong, oh damn, does it get it wrong. And the problem is there's no way you can hint a query to say more memory, please, less memory, please. I mean, you could do some complicated tricks. Adam's got some astoundingly weird query constructs that you cross-apply a whole pile of stuff into a query that returns no rows or no columns, but convinces the optimizer to estimate like 2 or 3 gigs of memory. It's impressive, I must say, but it's really a hack. Now, if the query requests too much memory, then you're reducing concurrency because there's only so much working set memory. And queries that request a lot of memory often have to wait to get that memory. If anyone's ever seen resource semaphore waits, that's a query waiting to get a memory grant. Queries that request too little memory spill to disk. So yes, there's a hint max grant percent. Yeah, kind of, not really. You can encourage it. It's not, you can't tell the optimizer twice the memory that you think it should need. It doesn't unfortunately work that way. So yeah, 2 queries that request too little memory, spill to tempdb. Potentially spill multiple times. I recall, I think it was Paul Randall, had a particularly pathological query once that he had written that spilled to tempdb like 60 times during its execution. It was horrible. It was horrible. Look, he wrote it to be horrible, but it still was horrible. So both of these are problematic. Both of these are actually really annoyingly hard to fix. Until we got to 2017. This one, so the previous intelligent query processing features have all been on the same query. Adaptive joins lets the processor choose which query it's going, which join type it's going to use. Interleaved executions, we split the optimize execute in pieces. Memory grant feedback, however, applies across the executions, across multiple executions. And this is why I'm hoping my plans stay in cache, because if they don't, these demos are going to break horribly. So what happens here? Actually, let me demo this. It's easier to demo this, and hopefully my demos work. Please, demos work. Please, please, please work. All right, so I've got a really weird query here. If you're wondering why you'd ever write a store procedure like this, you wouldn't probably. But I've got a filter on priority. Priority in this database is a number between 1 and 3. And if I'm not mistaken, this works. So, yeah, 150. Okay, so if I run this the first time, it's going to return no rows. That's fine, because there's no priorities that are less than 0. So this database doesn't have any. And I've got a warning on my select, on my query plan. Warning, the query memory grant detected excessive grant, which may impact the reliability. Grant size initially 67,000 megabytes. That's a pretty large grant. So what's that, 67 megs? Yeah, 68 megs of memory. It used less than 1 meg. Now, if this was SQL 2016 or earlier, the next time I ran this query, it would request 67 megs of memory, and the third time it would request 67 megs of memory, and the fourth time and so on and so on and so on. Right, let's hope that everything's working. Everything's not working. There we go. Okay, so something's still flushing my plan cache, so I need to run these things quickly after each other. The second time I ran it, let me actually do that again so you can see. Actually, what the hell is running on my machine? Oh, come on, seriously? That can go. This is ridiculous. Well, less than 30% of my memory use is in use and SQL's dying. Okay, fine. Maybe that'll fix it. All right, let me try this again. So the first time I run it, we've got a memory grant, excessive memory grant warning, excessive grant. Second time I run it, it's gone. Let me show you the difference. Let's switch back to 130. And SQL prompt. All right, this is 130, so this is compat mode 1 for SQL 2016. Excessive memory grant, excessive memory grant. Oh, that's not nice. Excessive memory grant dead. Excessive memory grant. Oh, the query had to wait 5 seconds for memory grant during execution. I did say I've got a memory problem. This is 2016 compat level. If I switch back to 190 to 2019, sorry, not 190. Memory grant excessive, second execution. Memory grant on the second execution was 2 megs. As part of query execution, the amount of memory that was actually needed is recorded. Not the amount granted, but the amount that was actually needed. After the query completes execution, if the memory grant was too high, it is adjusted down. If it was too low, it's adjusted up. And that adjusted memory grant is saved with the query plan in cache. So no, memory grant feedback is not just 2019, it's 2017 and 19. I'm just switching back and forth between 16 and 19 compat mode because I've got a 2019 instance here. But this works in SQL 2017 as well. So it'll work in compat mode 140 and higher. Note the caveat here, saved with the query plan in cache. If you restart SQL Server, it's gone. If you clear the plan cache, it's gone. If you run out of memory like I'm doing, it's gone. It's saved with the plan. It's not saved anywhere persistent. It's not saved with query store. It's purely in cache. Right. So this is what you see in the execution plan. You'll see warnings on the first query, and you'll see the warnings go away in the next execution. Okay. Let me see if I can break this. I can definitely break this. So let me just try and force this. This should be now granting 2 megs of memory. Okay, cool. Let me go and change this parameter so that it's a stupid amount of memory needed. Ah, yes, I love slow queries. All right, this is showing me warnings left, right, center, and everywhere else. Warning, spill to tempdb. We wrote 132 pages to tempdb. The sort also wrote to tempdb, writing 244. If this was 2016, that would be there on the next execution. On 2019, second time I run it, it's gone. So this was a demo of too low, and then, sorry, too high, and then too low. Now, there is a problem with this, and it's something I wrote a blog post on. If you've got a particular query pattern, or particular pattern of querying your database, where you run a particular query with a parameter that returns only a few rows, and then a lot of rows, then a few rows, then a lot of rows, memory grant feedback will always be right behind where it needs to be, and will always be generating the wrong estimates. So the first estimate on this one was 4 megs, and it needed a stupid amount more because it's written a whole pile to tempdb. Second time I run this, it'll go away. Yep, you'll notice the second execution, we've got 8 megs. But if I switch this back to 0 and then ran it, don't have the excessive grant, but I've still got too much. So do watch out for this particularly ugly case where you intermix queries that need lots of memory and little bits of memory. If you do have something like this, it's honestly better to split it into multiple store procedures, and because otherwise memory grant feedback will just always produce the wrong results. So caveats on this: plan cache. If you run your query option recompile, it doesn't go into the plan cache, so no memory grant feedback for you. If you've got somebody from last century that puts with recompile on their stored procedures, that's not cached, no memory grant feedback for you. If you flush your plan cache every 5 minutes, I'm sorry, no memory grant feedback for you because it's gone with the plan cache. So it's very much dependent on a stable plan cache and a fairly stable querying pattern for it to work well. Okay, so requirements. Batch mode or SQL 2019? This adaptive memory grants works on SQL 2017, but only if the query is running in batch mode. 2019 removed that requirement. It now does row mode as well. The over or under allocate must be by 50% or more. So you saw that in the last example I did. This, no, not that one. I'm selecting, what, 70 megs of memory. That's a lot. If I switch this around quickly and see if I can get it to misbehave some more. Yeah, slow queries. All right, so we know that this particular parameter only needs less than a meg of memory, but in this case, it's been granted 8 and it's actually fine with that. It's not adapting. So there is a threshold. I'm starting to wonder if that 50% has been changed in a recent patch, because 8 megs off 1 meg is more than 50%. But there's definitely a threshold where it won't bother adapting. And in tests I've done, it will adapt 32 times, I think it is, and then stop. Because if it's adapting backwards and forwards 32 times, the query processor decides that this is an oscillating case where low memory, high memory, low memory, high memory requirements, and it's just going to stop adapting at some point and sit with whatever the last query had, which might not be ideal. So that is also a limitation. These numbers are not set in stone, the 32, the 50%. These are very much dev team reserves the right to adapt and change as they feel like it with patches. These actually may be wrong already on my demo, on my slides.
Gail, we have 2 questions here. Are there DMVs that show queries with frequent memory grant changes? Should we do anything about such queries?
Are there any DMVs? Yes, there are some DMVs that show the memory grant adaptations. If you do see those, yeah, you want to break them into multiple store procedures or in such a way that they get different plans. That way they can adapt their memories individually. So in my case, if I was frequently running this with 0 or 4, that is that oscillating memory requirement. One requires low, one requires high. What I probably want to do is split this into 2 store procedures, shipment totals by station priority 0 and shipment totals by station priority higher. That way they both get tuned on their memory grants. If they're important to you. If they're not, who cares? Yeah, you'd split the main query to 2 procedures. Yeah, because the memory grant adaptation's at the query level, not even the procedure level. So it's on this plan for this query. So two sub procedures would work perfectly, yes. Okay, yes, I'm reading the questions. I probably shouldn't be. Any other questions on memory grant feedback? Oh, no, I didn't want to restart Firefox. I'd go and look for the DMVs, but I don't want to restart Firefox at this point. So
yeah,
the documentation.
There's sysdm exec query memory grants per Elko. It's mainly the X event as far as I know from monitoring that.
Oh, yes, yes. So, sorry, that's right. The DMV is just the memory grant. It's the extended event that tracks the memory grant feedback. Thank you. Yeah, I got that wrong. Is there a reason it doesn't use query store to persist the feedback? The dev team didn't do it that way. Feel free to log a user voice and ask for that. I mean, I've only been asking for it for, what, 3 years? They were thinking about it last time I heard. Okay, I think I have 15 minutes to talk about inline scalar functions. So, inline scalar functions. This is a 2019 feature. Everything else I've shown tonight has been 17 and 19, with the exception of the deferred compilation for table variables. But this one is entirely, absolutely only SQL 2019, inline scalar valued functions. So, in previous versions, scalar functions are, well, they're not inline, quite simply. A lot of people think they are because that's how front-end languages work. They're not. When you've got a scalar function in a query that is a call out to a different scope, different execution, return to the previous one, the function is run for every single row of the query that it's present in. This is horrible. This is absolutely vile. If you've got a slow function, it's horrible. It's absolutely horrible. I think I'm ranting about these things now. But seriously, I've had multiple cases where I've looked at client systems where they've said, we've got performance problems. I look at their code and go, yeah, I'm not surprised. Because they're either abusing scalar functions everywhere, or they're abusing multi-statement table valued functions everywhere. We've already seen the table value functions. They're horrible, can be. Scalar functions, horrible. How do we fix this, says the client? Strip out all your scalar functions. But that's work, they say. So yeah, that's work. Well, these days I can say upgrade to SQL 2019 and your problems will mostly be solved. Mostly. 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 I need to emphasize that. Mostly. So, scalar functions. I have a nice, simple little scalar function here. It's called date only. It strips the time off a date. I mean, how many of us use that kind of thing? Because converting to dates is hard. I actually need an extended event for this just to show how bad this gets. I swear I know where extended events are. I do not. Oh, look, I've got an extended event for scalar functions. Fancy that. I wonder why that's there. All right. I am in 150. Oh, I'm in 150. That's a problem. I can switch it to 140 at this point as well. This does not work. This inline does not work on 2017 either. So statistics time on, because I want an idea how long these run. There's a few thousand rows in the transaction table, like 30,000 of the things. Without the scalar function, 0 milliseconds of CPU time, 300 milliseconds elapsed time. With the function, 234 milliseconds of CPU time. So this has spent 234 milliseconds on the CPU doing, well, exactly the same thing, just the external call. And if we go and look at what, oh boy. Oh boy. Oh boy. I mean, they only run in like 3, what's that, milliseconds, microseconds? I don't know. I can't remember what the unit here is. I think it's milliseconds. But this thing ran 34,000 times. Must be microseconds. Ow. Okay, it's in microseconds. So these things ran maximum 17 microseconds. But the problem is they ran 34,431 times. Yeah, I hope you didn't want this result quickly. I mean, there's only 34,431 rows in that table. This gets really, really bad on larger tables. All right. Then we have this one. Oh boy, yeah. This is not just a scalar function. This is one that returns data. Oh boy. So I promise you these two queries do exactly the same thing. This subquery here for total shipment mass is exactly what this scalar data accessing user-defined function is doing. All right. So I've turned stats IO and time on. I need to clear the filter there as well. Clear filters and clear the data as well. Let's see how bad this gets. Shipments only has a few thousand rows in it, so this should be fine. Executing, yeah, okay. That wasn't too bad. Note the orders that they've come back in is different, but that's just the query processor being the query processor. So for the first one, shipments, 1 scan, 254 reads, blah, blah, blah. Shipment details, scan 1, 2,955 logical reads, blah, blah, blah. 312 milliseconds of CPU time and 729 milliseconds of elapsed time. Yeah, that's not half bad. There are, how many? There are 34,000 rows in the shipments table. That's about right. Second one. So, does anybody see what's wrong with the IO stats here? This is when I love doing this in front of a live audience. People actually looking and go, wait, where? Where? Where's shipment details? Because I did read from shipment details. I mean, this shipment mass queries from shipment details. The problem here is that the function is not in this scope. The function is running somewhere else. And so its results from stats IO are not there. So if you aren't familiar with this, if you don't realize this and you're looking at your execution stats, well, there's only 91 reads from the shipment table. This is a nice, efficient query. No, it's not. It's not at all efficient. Firstly, because we've gone from 300 milliseconds of CPU time to 2 seconds to do exactly the same thing. Just, whoops. Secondly, this one, unfortunately, does not, module end does not have the reads in it. So let me do this again and modify this particular extended event session. I want properties. What I want here is SP statement completed is the one I want. That'll do. So I'm going to clear that and I'm going to run this again. Okay, nice and efficient, still running, and now it's done. So let me filter by that one. Yep. We'll put the, that one. We'll put the statement into the table and we'll look at the logical reads. That's not actually too bad. Oh, that's right, I put an index on this table. This is doing 3 logical reads. Let me filter by that value as well. So the query against shipment details is doing 3 or 4 logical reads per query, 34,000 times. How many reads against shipment details? Well, let's say the average is 3 times 34,000, 431. Yep. Copy that number. So this actually implicitly didn't say 34,431. So that's what it should have said. That's ugly. And that's just 34,000 rows and a query that had an index on it. I did a demo, sorry, I did some tests for a blog post a couple of years ago, left the function running while I went to get coffee, came back, looked at it, only one had finished. I was running it 25 times, went, watched some TV, had a shower, came back, only 2 more had run, went to bed, got up the next morning and 25 executions had only just finished. And the query without the scalar function, the absolutely equivalent query without the scalar function, had run in something like 5 seconds. 5 seconds to about 16 hours, just by moving a subquery into a scalar function. So now I've made very clear how horrible these are. 150. Clear that. I want to remove all the filters as well. Right, scalar function 1, run both. 31 milliseconds of CPU time, 0. How many times did the function run? It didn't. Onto my data accessing one. 0 seconds, sorry, 1 second instead of 3. Note, shipment details is returned to my stats IO output. 600 milliseconds of CPU versus 300. How many times did the function run? It didn't. Inline scalar functions. The query optimizer, processor, one of the two, I actually don't know where this one is done, takes the contents of that scalar function and puts it into the query as a single object and executes the whole thing. This, the parser, thank you, Hugo. So it's done by the parser, the query optimizer. So it's like a view. The query processor, the query optimizer never sees the scalar function. The query processor never sees the scalar function. As far as they're concerned, it's just one piece of query. So fantastic. All right, here are the caveats. The list, okay, if anybody thought that indexed views had a long list of requirements, go and look at the requirements for inline scalar functions. Last time I checked, it was 1.5 pages long on my screens. It's also getting extended in every patch because the dev team keeps finding little things that they didn't realize. We've been getting this patched in every CU of SQL 2019. This will not be as fast as if the function was never there. And you can see that on this one, not that one, that one. The query without the scalar function was 300 milliseconds of CPU. The query with it was 625. It's still a long way from the 2 seconds that this was running in compat mode 130, but it's not going to be as good as not having the function at all. However, if you've got a customer that's got scalar functions all over the place, take them to 19 and up the compatible mode, and a lot of the problems will go away. This isn't obviously going to solve the fact that functions on columns are not saggable. That's, well, no, probably not. I haven't checked, but it's not going to fix it, but it seriously makes the problem a whole lot nicer. So 2019, compat mode 150, inline scalar valued functions. Okay, so that's adaptive query processing. That is intelligent query processing in SQL 2017 and 2019. I think I've got 3 minutes left on my time, if my guess on the time is right.
You do.
Questions?
We have one right now that's in the queue. What is in the X event in the scalar function that you should?
Oh, that one. Originally, it was just module end. That doesn't double click, does it? So originally what was there was just module end. Nothing fancy. I had no predicates on it. I hadn't put any globals on it. It was just the stock standard module end, i.e. This look at store procedure completions, function completions. What I added to it to show you the logical IOs was the SP statement completed. This will fire for each statement that completes within a store procedure or function.
Not a tongue-in-cheek question from NZO. Is there anywhere you would actively recommend using user-defined functions in any form?
Sure, I actually love them for certain things. Don't do this with them. And think twice before you do this with them. But for something like
my favorite demo of this doesn't complete in 130 and runs in like 5 seconds in 150.
Yeah, I've got one of those. This is fine. This is fine. This is fine. Whatever. It runs once. Who cares if there's a little bit of overhead to it? It's when you put them into a query, into the select, into the where, heaven forbid, into the join of a query that you start getting problems, because that overhead of calling the functions happens again and again and again and again and again, once for each row in the query. If all you're doing is using it to calculate a variable in your store procedures, by all means, watch out for putting them in queries though. But if your query returns 5 rows and will only ever return 5 rows, again, who cares? The overhead's not huge. 5,000 rows, 5 million rows, yeah, you've got a problem then. It's a lot, same with a lot of things in SQL. They have their place. When you put them in somewhere that is not their place, you get problems. Performance problems, typically in this case. Other questions before I annoy the organizers and go over time?
That's all we have for right now, I think.
Awesome. Cool. Let me kill the slide screen share. Well, thank you very much, guys. I hope everyone enjoyed that. I hope that was up to the level 400 expectations.
Yes.
Yeah, definitely.
I laughed a lot, Gail. You make me laugh when you talk. I love it. I mean, I learned something too, but like your sense of humor is great.
As long as you're laughing at my jokes and not at me, that's
yes, for sure.
Well, if you enjoyed that session, please, well, either way, I guess I should say that. If you like, thanks for coming to that session. Please fill out the feedback form. I'm not good at this.
You're doing a good job there, Anthony. Keep going. Go on.
You know, I was really looking for you to take over, Mr. Attenborough, but I couldn't see you out there.
I have to turn my video. Oh no, yeah, I'm not orange anymore.
There you go.
No, fantastic. I think some of the comments in there. I think Gail pausing. Let me just go and kill things. As one thing I particularly liked. So we have. Please leave your feedback. We have 8kb.online/feedback. Please leave. We got a session there we got a link there for the entire event, and we have the individual sessions as well. So please go ahead and leave feedback. And next up we have Klaus with Latches, Spinlocks, and lock-free data structures.
See, you were a lot better at that than I was. It's nice work there, sir.
You need to practice more, Anthony.
I'm just going to turn my camera off in shame.
Hello, can you hear me?
Yes, we can. Yep. Hey, how you doing?
Fine, thanks. And you?
Yeah, all good. Thank you, fella. Absolutely fantastic.
We're doing just fine. It's just a little pandemic going on out there. No big deal.
No.
Is that your flight sim setup behind you there, Klaus?
Only a small one. Only a small one.
How's the Raspberry Pis, man?
Sorry?
How's your Raspberry Pi cluster?
Oh, it's very, very well. It's just behind me.
Awesome.
And here in the behind, I have a small flight simulator, but only a small one.
Okay, well, we're getting some absolutely fantastic engagement going on in the Slack channel. Everyone posting links, asking questions, answering each other. It's absolutely brilliant.
Yeah, thank you to everybody that's in the Slack channel answering questions too.
Yeah.
It's super helpful.
People dropping in answering questions there. It's absolutely brilliant.
Hey, Klaus, it's Angela.
Hello.
Hey, so how do you want to handle your questions? Do you want to interrupt you? Do you have breaks built in? Do you want to just...
You can interrupt me, no problem.
Okay.
Yeah.
All right.
Hey, Angela, sorry, I didn't see you jump in there. How you doing?
I'm well. How are you, Andrew?
Yeah, all good, thanks. Yeah, we've been going, what is it, four and a bit hours now. We've got around about 3 hours to go. So
I thought it was a 3-hour session. Sorry.
Your session could be as long as you'd like.
We may stop the webinar, but you can keep going.
That must be a bonus for having the last one on the day.
Absolutely. Yep, you can just keep going. We probably will cut you off at 9:30 UTC.
And you have 2 Austrian accents in a row, so that's also, people will be used to understanding me once.
That's a good point.
We tried to do the session in order of time zones that people were popping in and out of, because time zones, as Anthony will tell you, are very hard to do.
Yep. Yes. Yeah. I don't even bother anymore. I just like, you know what? It's like 1/2 something wherever you are, right?
Well, the first time we did this event, for some reason, we posted all the session times in Eastern Standard Time.
I greatly appreciated that.
Yeah, so did I. That worked great for me.
There was like 20 people who were like, "That's fantastic," and everyone else was going, "What?"
Just the 20 of
time is already hard. DC time is already hard.
Yep. Luckily, I double checked because first I've scheduled my session at 8 p.m. Eastern. And I'm like, yeah, I have no problem. Don't have to take the day off, nothing. And then,
well, I also had to Google in the morning which UTC time we have in Vienna. Just to be sure.
The nice thing about UTC is nobody has that on their clock. Everybody has to do the math.
Hi. Living in an island.
You don't count.
But, yeah.
Until it transitions to IST, and then I have to do math. Yeah, absolutely.
The other half of the year, you don't.
Yeah, that's it. Yeah.
I hope that stops at some point because it's useless. The daylight savings. Nobody saves anything. It just millions of lines of code.
It's a little waste of time.
Yep.
Especially when you have kids. They don't understand.
Well, when you have cats, they don't understand.
Well, cats are on their own time zone.
Not that they don't understand, they just don't care.
Yeah, cats just they understand, they just don't care. Okay, everyone getting involved on Twitter as well. Absolutely. The awesome website that is Twitter, but
it's free.
It's free.
There we go.
Argenis, did we talk about Cheetos today yet?
Erin, I'm on a diet, so can we not start, please?
That's fine, because I've been eating healthy for the past 2 days as well, so I feel I got you. You're all good.
Let's just try to support each other then.
Got it. I had, how many vegetables did you have yesterday?
No.
Wait, let me ask you this.
That cookies, Thomas, no.
How many vegetables did you all have yesterday?
What's a vegetable?
Does corn and Cheetos count as a vegetable?
No,
Oh,
Beer is officially a vegetable. So
no, no beer.
yes, it
Well,
is.
I live in the South and they count macaroni and cheese as a vegetable.
No.
Right.
Well, I mean, yeah,
So if I
anything
had
on
it-
the side.
I
My
have,
So you're
burrito
saying how
chilies
many?
in it.
I have pizza
many
with veggies
servings?
on it.
How many servings or how many different vegetables did you have yesterday? I actually had spinach, I had carrots, and I had green beans. I don't know the last time I had 3 vegetables in a day.
Aaron, what's wrong with you?
I'm trying to eat healthy, Argenis.
I had 4, but they came all out of the same can. So I don't know if that counts.
Or in the South, we can get the vegetable fry plate. You know, get like 3 vegetables that are just all fried.
I don't think that counts either, Anthony.
Anders is wondering if cheese is a vegetable. Yes, it is, Anders.
Yes, if it has.
Oh wait, I had an avocado's a fruit, isn't it? Because it has a seed.
Maybe.
Yeah.
technically it's a fruit, I believe. Yes.
Right, Bob. I thought you would know that.
I love the way everyone went. Yes.
So Bob, what's a banana?
Fruit.
Banana. What?
It's a measuring device.
Is it a fruit? Is it a herb? Is it?
That's how we measure the stock
banana
market
has
right now.
seeds in it.
Bananas.
If it has seeds in it, it's technically the ovary of the plant, which makes it a fruit then, right?
Think of
Is that right?
I thought that's how you did it.
it's a
Yeah,
fruit.
you are. Yeah.
I don't like the innuendo in this conversation.
Yeah, I know. Where are you going with this, Rob?
It's one of those. It's one of the ones that live outside of the box because it can be defined. It can fall under the definition of fruit, of vegetable, of herb, of nut. I think in some ways as well. It's a really odd one.
I'm reading.
Someone out there fact check Rob.
Everybody's now googling.
Yeah, everybody's working on it.
It is. It's considered a berry.
Yeah, berry. That was the one.
There we go.
So, yeah, a berry.
It has high sugar. I've learned a lot about sugar and fruit lately.
Aren't bananas slightly radioactive as well? I remember reading that somewhere.
Probably depends on where you get them, Andrew.
Well, I'm googling that.
So Andrew, you were saying about how amazing it is, all this high level learning that we're doing.
Yes.
Bananas are already up.
We have to have
You'll
something
shoot laser
to,
beams from your eyes.
cleanse the palate and in between sessions here. So we'll just
Bananas are slightly radioactive due to the presence of a natural isotope of potassium. Thank you.
I wonder if
There we
you
go.
actually gonna mark this videos afterwards as like, warning. Nutrition facts presented by this group are not accurate.
No facts here.
We have to put markers in saying like between this time period and this time period, please ignore all
Yes.
information given. But between the actual sessions, yes, but that is fact.
One of the best parts of this conference, in between sessions. I gotta say, this one has been particularly interactive on Slack and on Twitter. It's been really nice to see.
Yeah.
Yeah, absolutely.
Hey, Klaus, how long is your session again?
I have no idea.
Organizers. How long
We
is
have you down
Klaus's
as
session?
75.
75
I
minutes.
think I have 75 minutes.
Okay.
I think.
Okay, I'm going to stop sharing my screen and you can take over, Klaus.
Just give me a second.
No problem.
Do you see my screen?
We do.
Perfect.
There we go. Yeah, we'll give it a few more minutes and you can get started. Well, we've started a food conversation in the Slack channel. Fantastic.
See that? Well, I need you all to be healthy. I need you to think about that, okay?
I do like Victoria's comment of no one heard of a salad.
I know. I had one yesterday, actually, and I'm about to have second. Well, I don't know. It's not really lunch. Second lunch?
Taco cheese salad.
Not a cheese salad, no.
Taco cheese.
No. Taco. What's
Macaroni with cheese, taco, all, and they sell it as a salad. It only has about 8,000 calories. It's an awesome thing.
Wait. What is in this?
It's a restaurant that literally sells you the most unhealthiest food, but they call it a salad. So you're fine when you talk to your doctor. You're not lying.
I got it.
Raised blood pressure makes my blood pump more freely.
Yeah.
Increases the velocity.
But not the viscosity.
Right, just trying. Well, no way to come back from that.
Yes, radioactive banana man.
Yeah, fair enough.
Well, actually, we've got an early question for Klaus. What is the most common vegetable in Austria?
Beer.
Beer.
Yeah.
I have no idea.
Okay, there's a discussion about a bacon fest in Des Moines, which I have to mention because I grew up in Iowa. If you're going to have a bacon fest in Des Moines, you have to have like the butter cow too, right? Does anybody know about the butter cow? No.
No, what's the butter cow?
That's at the Bob, you could chime in. You might know this one. At the Iowa State Fair, there's a person who like sculpts out of butter and she makes a cow.
Yeah, we have a butter livestock at the Illinois State Fair as well. So I am definitely familiar with that. And I believe one year in Iowa, they did a butter Shawn Johnson edition.
Oh, because she's from Iowa.
Yeah, Olympic gymnast from Iowa. So
that's just how we party in the United States.
You can fry it.
Okay, it's 6:30 UTC. Klaus, take it away, fella.
Thank you. Hello. And welcome everyone to my session about latches, spinlocks, and lock-free data structures. A few words about my person. My name is Klaus Aschenbrenner. I come from Vienna in Austria. Means in my time zone it's already 7:30 p.m. in the evening. So already very, very late. Not that late, but still late. I provide with my company SQL Passion, SQL Server consultancy and training services across Europe. I'm speaking a lot about SQL Server. I also regularly blog about SQL Server. I'm also a Microsoft Certified Master for SQL Server, which was the highest technical certification that you can achieve on SQL Server. I have also written the book Pro SQL Server 2008 Service Broker, which was published in the year 2008 by Aprils, so already a very, very long time ago. Service Broker is an asynchronous messaging framework that Microsoft first introduced us back with SQL Server 2005. And with Service Broker, you are able to write and implement message-based asynchronous database applications. You can also follow me on Twitter, and you can find further information about my person, my services that I offer on my website at sqlpassion.ad, where I also provide a free performance tuning newsletter, a lot of different training videos to explore. So just check out my website. Let's talk now about the agenda. Today, I want to dive a little bit more in details into SQL Server, and I want to talk about latches, spinlocks, and lock-free data structures. When you know me, my person, you already know that I'm somehow a strange person. And one of my specialities in SQL Server is mainly performance tuning, performance troubleshooting, and I'm also concentrating a lot on locking, blocking, deadlocking, and all those things. And tonight, I want to dig a little bit more in detail into SQL Server, and I just want to show you what happens underneath the covers when we, for example, acquire locks. So we will explore so-called latches in SQL Server. We will also talk about Spinlocks, and if the time permits, I also want to talk about so-called lock-free data structures, which are also used within memory OLTP in SQL Server, which was also introduced back, I think it was SQL Server 2014, so also already a very, very long time ago. Let's start now by talking about latches. I assume that every one of you already knows what a lock is. Every time when we read and when we write records in SQL Server has to acquire locks. On a very high level, SQL Server has two different kinds of locks. We have so-called shared locks. Those locks are acquired when we are reading records, and we have so-called exclusive locks, which are acquired by SQL Server when we change records. And both locks are just incompatible to each other, means when you're reading a record, you can't change that record at the same point in time. And when you're changing a record, maybe with an insert update delete statement, you can't read that record at the same point in time, because those shared locks and exclusive locks are just incompatible to each other. So that's the 101 about locking and blocking in SQL Server. But underneath the concept of locks, SQL Server also has so-called latches. And a latch is just a light-wide synchronization object, which is used internally by SQL Server for performing its thread synchronization. Imagine you have an internal data structure in SQL Server, for example, a page, which is always 8 kilobytes large. And every time when we access such a page from the buffer pool in SQL Server also has to latch that page. For example, when you want to read something from the page header, or when you make some modifications to the page header itself is not protected by a lock. Locks are placed on individual records. They can be also placed on a page, and they can be also placed, for example, on a table or even on a database level, or maybe on a partition level. But the page header itself has no locks. Means when you want to access that page header, you need some synchronization overhead, some synchronization object. Imagine someone wants to change and read the page header across multiple queries, across multiple threads in a thread-safe manner. This can't work. That's one of the reasons why we have latches in SQL Server. Latches were introduced, I think, with SQL Server 7.0, because SQL Server 7.0 also introduced a row-level locking. Prior to SQL Server 7.0, we had only a page-level locking, and with a page-level locking, you don't have all those problems that we have since the introduction of a row-level locking. And the terrible thing for us is that we as developers and even as administrators, we can't control those latches in any way. So there is nothing in SQL Server like a latch isolation level. Just think about it. So you have no control over those latches directly, just indirectly. What it means to have an indirect control over latches, you will see it in a few minutes. So when we compare locks to latches, they are working on different levels. As you can see, for example, a lock always controls something in the context of a transaction. A latch, on the other hand, protects something for a thread, like a data structure that you want to access in a safe manner. As you can also see on the fourth row, we have multiple modes for locks. As I've already said, we have shared locks, we have exclusive locks, but there are also much more lock types in SQL Server, like update locks, intention locks, and so on. Even latches have also different modes. We have a so-called keep mode, a shared mode, an update mode, exclusive mode, and even a so-called destroy mode. Deadlocks. As we all know, SQL Server implements a deadlock detection mechanism in SQL Server, and SQL Server can also resolve deadlocks on its own through the deadlock monitor, which just rolls back one of those transactions which are just locking each other and blocking each other. On the other hand, a latch can also have a so-called deadlock. That's a so-called dead latch. But a dead latch is more or less just a bug within the code base of SQL Server. So in that case, the developers of Microsoft, they have to make sure that they are not running into a so-called dead latch. Just think about it. Locks, for example, are also stored in memory in the so-called lock manager's hash table. On the other hand, a latch itself is just kept in the data structure that it protects. So as you can see from that slide, there are some differences between locks and latches in SQL Server. What types of latches do we have in SQL Server? On a high-level view, we have three different types of latches in SQL Server. We have so-called buffer latches, we have so-called I/O latches, and we have so-called non-buffer latches. A buffer latch, as the name already implies, protects all the pages that we are accessing from the buffer pool in SQL Server. Every one of you knows already what a page is. A page is the unit in which SQL Server structures and stores our data. And every page in SQL Server has a predefined size of 8 kilobytes. Within that page, with a page header, which is 96 bytes long, and after that page header comes the payload where we are storing our individual records. Means the smaller your records are, the more records we can store on one page of 8 kilobytes. And every time when we read a page from the buffer pool, SQL Server has to protect that page with a so-called shared latch during that reading operation. Means during that reading operation, nobody else can change that same page in the buffer pool, because when you want to change a page in the buffer pool, SQL Server has to acquire a so-called exclusive latch. And guess what? A shared latch and exclusive latch is again just incompatible to each other. The same that I have described previously with locks in SQL Server. All those different buffer latches, they can be retrieved through our weight statistics. So the weight statistics in SysTM/OS weight stats, they are telling us how long we are waiting on a specific latch. Means when you can't acquire a latch in SQL Server puts that query into the suspended state, and the query has to wait until that latch can be acquired. Then the scheduler of SQL Server moves that query from the suspended state into the runnable state. And in the runnable state, we just have to wait until SQL Server can schedule that query on a CPU. And finally, SQL Server moves that query from the runnable state into the running state. As you can already see or hear from this description, as soon as you're waiting on a latch, it takes a lot of time until SQL Server can resume, until SQL Server can continue that query, because the query has to go through the query life cycle, which consists of those states: running, suspended, runnable, running. This is already very, very important to know, because when we talk later about Spinlocks, we will come back to that specific problem. So waiting on a latch is a very, very expensive operation because we have to deschedule that query and the query goes into the suspended state. We have also so-called I/O latches. I assume that almost every one of you has already heard about them, have already seen them in action in your environments. Every time when we have outstanding I/O operations against the pages in the buffer pool, we have so-called I/O latches. Means every time when you read a page from your storage subsystem, SQL Server acquires a so-called page I/O latch shared. A page I/O latch shared in the wait stats just means that you are waiting until a record is read from your storage subsystem into the buffer pool, into main memory. Every time when we are writing pages from the buffer pool back to our storage subsystem, for example, through the checkpoint process, SQL Server also acquires a so-called I/O latch. In that case, SQL Server acquires a so-called page I/O latch EX exclusive, because we are writing those 30 pages from the buffer pool back to our storage subsystem. So when you're looking into the wait stats in System OS wait stats, you can identify quite nicely how long you are waiting on your storage subsystem for reading data and how long you are waiting on your storage subsystem for writing data through those I/O latches. And in addition, we also have so-called non-buffer latches. As the name already implies, those non-buffer latches are used in SQL Server when you access other data structures in main memory, which are not part of the buffer pool. And those non-buffer latches can be seen also in the wait stats. This is the screenshot that I've taken from the wait stats. So as you can see, those non-buffer latches, they are starting with latch underline and then the latch type. And in addition, you have a so-called detailed breakdown in another dynamic management view in System OS latch stats. So every record that is returned in that dynamic management view tells you how long SQL Server waits until it can access other in-memory data structures. And one prominent data structure that we will also see later is our transaction log. The transaction log in SQL Server is also protected by a latch. For example, when you perform autograph operations on your transaction log, which are very, very expensive, SQL Server acquires a latch on the transaction log. And in the meantime, nobody else can access the transaction log, because every other transaction has to wait until that latch is released. Means when you have an autograph operation, nobody else can do anything with your transaction log until that autograph operation is finished. So let's switch over to SQL Server, and I want to show you now how we can explore latches in SQL Server. As I've already said previously, we can review and retrieve our buffer latches through the dynamic management view System OS wait stats. So as you can see, I have here the non-buffer latches. I have just restarted SQL Server, and as you can see, I have here almost no wait times. This will change later when I show you some specific problems which are introduced with latches in SQL Server. We have our I/O latches. As I've said previously, those I/O latches are always acquired when we are reading and writing from our storage subsystem. So as you can see here, we have the page I/O latch shared. And since my last restart of SQL Server, which is just a few hours ago, I had to wait 794 times for reading from my storage subsystem. And I also had to wait a few times for writing data from the buffer pool back to my storage subsystem. Imagine now the following. Let's assume we are reading now data. We have here 794 waits for page IO latch shared. So what I'm doing now, I'm clearing the buffer pool with a dbcc to up clean buffers. Never ever do that in production. Trust me, you will have later performance problems. And now let's just read some records from a large table. I'm just doing a very inefficient count star. Takes a few seconds. In that table, we have millions of rows. And because the buffer pool was empty, we had to retrieve all those pages from the storage subsystem. And now, when we check the IO latches again, you see we have page IO latch shared of 1,677. So during that IO operation, SQL Server has to wait multiple times until we have retrieved those pages from the storage subsystem. Means in that case, the query was going into the suspended state. We have waited until we got those pages from our storage subsystem. Then the query was moved into the runnable state. And then we were waiting in the runnable state until the scheduler can move that query back onto a CPU for further execution. And finally, we have our non-buffer latches. And as I've already said previously, those non-buffer latches are just protecting other data structures in SQL Server which are accessed concurrently across multiple worker threads. So as you can see, we have here those non-buffer latches, and they are not telling you that much because this is just a summation of all the waits that have occurred across all non-buffer latches in SQL Server. But the great thing is we have another dynamic management view called SysTMOS Latch Stats, which is showing us a detailed breakdown of all the non-buffer latches in SQL Server. So as you can see here, we have here 171 records returned. I'm running here SQL Server 2019, latest, greatest release. Means SQL Server 2019 has 171 shared data structures which are protected by a non-buffer latch. Non-buffer latches, for example, are used in parallel execution plans. They are used, for example, when we access our transaction log for autogrowth operations. As you can see, we have here non-buffer latches for backup operations, CLR, which nobody else on earth is using anymore, dbcc, checkdb. When we go here down, full text, database mirroring, the query optimizer, service broker. Nobody on earth is using service broker. Almost nobody, except me. Trace, for example, which we should also not use anymore because we have extended events. But as you can see, there are so many different data structures in SQL Server which have to be protected somehow. And for those data structures, SQL Server is using non-buffer latches. So by now, we know how we can explore latches in SQL Server. Let's talk now about a few specific problems which are introduced by latches. One most prominent example of a so-called latch contention is the so-called last page insert latch contention. As we all know, when we are designing our tables, they should have a primary key. And of course, that primary key should be an ever-increasing number. Because with an ever-increasing number, like an integer or a big integer, we introduce no index fragmentation, you have no page splits, you have less overhead in your transaction log, and everything is fine. That's great, yeah, but from a performance perspective, it can be really, really terrible, because an ever-increasing clustered key value, like an int identity column, introduces that last page insert latch contention problem. The problem is the B-tree data structure that SQL Server uses internally to represent a clustered or non-clustered index. So that problem is not specific to SQL Server itself. That problem is just specific to the B-tree data structure that is used by SQL Server. So even other databases have the same problem. The problem is that all inserts with an ever-increasing clustered key value are just going to the same last page in our clustered index. So imagine you are inserting a new record. Let's say we have an integer value of 1000. Means when we make that insert, we have to change that page. As I've said previously, when you are changing a page, you have to acquire an exclusive latch. Means the whole page is exclusively latched in the buffer pool. Nobody else can access that page anymore in the buffer pool. Not for reads, not for writes. It's exclusively latched. It's the same when you're going to the toilet and you're locking the toilet. You are on your own. And it's the same here with that page. That page is exclusively latched in the buffer pool. When you have done that insert, that latch is released. Means the next query can acquire that latch again and make the next insert on the same page, because we have an ever-increasing clustered key value.
Hey, Klaus.
Yes?
I've got a question for you.
Go ahead.
So do non-buffer latches from the DMOS wait stats reconcile to latch details in DM latches? It seems that the numbers were different.
Let me check that. So we have the overview information in the wait stats, SysDMOS wait stats, where I've restricted on the non-buffer latches, and the detailed breakdown is in SysDMOS latch stats. So it's just a breakdown.
Thank you.
You're welcome. The great thing about online sessions is that I don't have to repeat the question because everyone has already heard that question. So the problem is now you are making with an ever increasing clustered key value single threaded inserts on the last page of that index. Just think about it. This is great, for example, for order tables. But imagine you have tables where you have a high write throughput, logging tables, out-hitting tables. That's crazy, because you're making single threaded inserts, one insert after the next one. Let's have a look on a concrete example and how you can solve those problems. What are the solutions for that last page insert latch contention problem? You can use a random clustered key value. I'm making here terrible recommendations. I'm telling you, just use a unique identifier. The most terrible clustered key type that you can use. But for that specific problem, it is extremely fast, because with a random clustered key value like a unique identifier, we are distributing the inserts in that table, in that index, across the whole leaf level. Just think about it. But as we know, there are a lot of side effects. You have larger lookup values in non-clustered indexes. We are introducing index fragmentation. We have a huge amount of page splits, causes an overhead in the transaction log. So there are also some other side effects that you have to be aware of. Another thing is that you're using hash partitioning. And beginning with SQL Server 2014, which is already a very, very long time ago, we have also in-memory OLTP. in-memory OLTP is in that specific scenario also a valid solution, because within memory OLTP, as I've said already previously, we have, or SQL Server uses internally, so-called lock and latch-free data structures. Means within memory OLTP, there are no locks and there are also no latches. Means in memory OLTP would be also a valid solution to overcome that last page insert latch contention problem. So let's have a look on those various solutions and how we can troubleshoot latch contention in SQL Server. I create here a new database, and now let's create a table with a perfect primary key value. As you see, I'm using here primary key clustered, means the primary key is enforced internally with a unique clustered index, and I'm using an int identity column, an ever increasing clustered key value. You have no index fragmentation, you have no problems with page splits, and you have also no concurrency when you're doing concurrent inserts into that table. Just think about it. Everyone is telling you int identity as primary key value is an amazing thing. It depends. When you're just doing a few inserts across a few sessions, it's fine. But when you're thinking about logging, auditing tables, you should think one more time if an int identity column is a great thing. So we have created that table. And now let's create a new stored procedure. And what I'm doing in that stored procedure is quite easy. In a while loop, I'm just inserting 10,000 records into that table.
Hey,
quite
Klaus,
simple. Yes?
I've got another question for you. It says, so how does the optimize for sequential key compare?
The question is how they optimize for sequential key compare. I have to check that. I don't have it currently in my head in my buffer pool. I have to check that later.
Okay, thank you.
Some amazing blog posts by someone, I think it's Milos from Austria. Just Google for him, milossql.com or something. And I think he has also written a lot of different things about that comparison. I will check that later.
Great, thanks, Klaus.
You're welcome. So in that stored procedure, we're just inserting in a while loop 10,000 records, as simple as possible. Let's reset our wait stats. I just want to show you how slow that workload is and how many waits we have during that workload. And what I'm doing now, I'm using here the tool ostress.exe, which is part of the RML utilities that you can download for free from Microsoft. And what I'm doing, I'm just running that stored procedure that we have created previously, and I'm running it with 100 parallel users. So 100 parallel users are trying to insert records at the last page, at the same last page in that clustered index. And trust me, we will have a lot of problems and a lot of time to talk. So let's start that workload. Let's open Activity Monitor. I like those graphs here. Waiting tasks, almost 100. Almost everyone is waiting. One query makes an insert. All the other queries are just waiting because they try to acquire a latch. But they can't acquire that latch because someone else has already an incompatible exclusive latch. We can also see that quite nicely. Let's go to system exec requests. And as you can see, we have here a lot of page latches EX. We are waiting on an exclusive latch. And as you can see, the wait resource is always the same. That page 3687 is Currently, at that point in time when we have done that query, it was the last page in that clustered index. Means one query has an exclusive latch, and all the other queries, they are just waiting in the suspended state. Just think about it. All those queries are just waiting on the same wait resource, on the last page in that clustered index. It was in the meantime finished. And as you can see, that whole workload took 57 seconds. Oh my God. I'm running here SQL Server 2019 Developer Edition, which is Enterprise Edition, very, very expensive, and SQL Server can only insert 1 million of records in 57 seconds. Oh my God. Let's run that again. It doesn't get faster, but I want to show you something else. Let's go to that machine. Let's have a look on the CPU utilization. We have almost no CPU utilization. I have a huge machine, 16 core, 128 gigabytes of RAM, and we have a utilization, CPU utilization of around 11-12%. Because all those queries are just waiting on main memory access, because accessing those pages in the buffer pool just means we are waiting on main memory access. Normally, main memory access is measured in nanoseconds. A nanosecond is almost nothing. It's almost nothing, but here, as we will see, we are waiting milliseconds for accessing pages in the buffer pool in main memory. Just think about it. We have a huge machine, and we can utilize that machine because we have introduced that last page insert latch contention. And again, 56 seconds. It doesn't get faster.
Hey, Klaus, I got another question for you.
Yes.
So what about sequence object to reduce the LPI? I can't say it. LPI contention.
Yeah, sequence. I also have to check that. The problem is I have tried that some time ago, already years ago, in combination with in-memory OLTP, and in that case, the sequence generator itself became a bottleneck. Because the sequence generator itself also has to hand out sequences. Means you are dealing again with a shared data structure, and that shared data structure is again protected by a latch. Means in that case, I have triggered a latch contention problem just in the sequence generator.
Okay, I've got another question for you. Or do you want to keep going?
No.
Okay. So is there any relation between lock and latches, such as usually a lock is a hold on a parent level object, for example, a table, before the latch is acquired on a child, for example, a page?
At the first step, SQL Server acquires locks because locks are acquired on a logical level, like a record, a page, a table, a database. And after those logical locks are acquired, SQL Server acquires the physical latches. Means the physical latches are acquired as soon as you're reading something from the buffer pool, or as soon as you want to change something in the buffer pool. As I've said previously, it's just a light-wide synchronization object employed by the engine of SQL Server.
Great, thanks.
So as you see, we have here now 2 million of records because we were running that workload 2 times. So SQL Server is currently very, very slow. We can also check now those page latch weights on the object level through the dynamic management function systemdb index operational stats. So what I'm doing here, I'm just calculating the average waiting time in milliseconds. In milliseconds, just think about it. We have here now an average waiting time of 2 milliseconds. Means we're waiting on average for 2 milliseconds to acquire a latch on a page in the buffer pool. which is stored in main memory. So we are waiting for main memory access for 2 milliseconds. As I've said previously a few minutes ago, normally main memory access is measured in nanoseconds. Just think about it, nanoseconds. Here we are talking about milliseconds. So this is a huge difference. Normally milliseconds are used to measure the access to our slow storage subsystem. And here I have a latency time of 2 milliseconds when I try to read or write pages from the buffer pool. Just think about it. And we can also check those page latch weights in the weight stats. And as you see, we have a lot of page latch shared weights when we wanted to read a page from the buffer pool. And we have also page latch exclusives when we wanted finally to change those pages in the buffer pool. So let's try to solve that problem with the sledgehammer. Let's recreate that table. And now I'm doing terrible things. I'm using again a primary key cluster, but instead of using an int identity column, I'm using now a unique identifier. Everyone, well, almost everyone in our universe is telling you, never ever use a unique identifier for a primary key value because it's just insane, crazy, and you are getting serious performance problems. You introduce index fragmentation, you have a huge overhead in the transaction log because you have all those nasty page splits, and so on, and so on, and so on. But a random clustered key value, like a unique identifier, scales in a much better way when you have that last page insert latch contention problem. Because as I've said previously, we are now distributing those inserts across the whole leaf level. So when we go back to PowerPoint, when we go back to that slide, instead of making those inserts just on the last page, in that clustered index, we are making one insert here on that page, one insert here, one insert here, and one insert there. Means you are dealing with multiple different pages, and those different pages can be latched simultaneously in the buffer pool. And that overcomes the last page insert latch contention problem. So let's create that table. A terrible table, but that terrible table scales quite well. Let's create another stored procedure. And now we are just generating that primary key value with the new ID function, which gives us an ugly 16-byte long unique value. And again, we are just doing 10,000 inserts. So we are doing the same workload as previously. Let's clear the weight stats. Well, let's copy those weight stats out just so that we see the differences. So let's do that. Let's copy them out. And now let's clear them. And now we are running that workload again. Whoops, wrong OS. CLS not clear. And now let's run that workload again. Let's see how long that workload, whoops, it's already finished. 4 seconds, just think about it. I haven't yet finished my sentence, and we are already finished inserting 1 million of records into a table. Just think about it. Instead of 56, 57 seconds, we are making those inserts now in 4 seconds. Because we are distributing those inserts across the whole leaf level of that clustered index. So we have no single hotspot at the very end of that index anymore. We are making one insert here, and one insert there. Yes?
So we've got a question. Wouldn't it be more efficient to use identity and its checksum checksum first, of course. This way you have the same random key, but it's 8 bytes and not 16.
Yeah, the goal is just to generate a random key. So there are multiple different solutions. I'm always showing the solution with a unique identifier value, but you can also employ other solutions. It's up to you how you generate that random clustered key value.
Okay.
As I said previously, the unique identifier solution is just quick and ugly. I just want to show you also that the unique identifier value doesn't mean that it's always bad. It's very, very often bad, but in that specific case, the unique identifier value is great. So
That's awesome. That's awesome. And there is a follow-up on that. So what about the table fragmentation side effect of that?
Of course, the table is fully fragmented, but we have a write throughput. So you also have to think, if you want to tune that table for reads or for writes, you can't have both. You can't have a great read performance and at the same point in time, a great write performance. So currently we have a bad read performance because we have a huge index fragmentation of nearly 99%. Those pages are not full at 100%. So a lot of different side effects for reads. But on the other hand, our writes, as we have seen, are very, very fast.
Okay, I have one more follow-up question here.
Yeah.
So to maximize the CPU, would it be good to use randomizing based on, say, mod by CPU count?
As I've said previously, yes, there are different ways how to generate that unique value. There are different, that random clustered key value. There are different approaches. It's up to you which approach you are using.
Great, thanks.
And even when we run that workload again, and we are going to our machine, you can also see we have a much higher CPU utilization. Previously, we had a CPU utilization of around 10 to 12%, and now all our 16 cores were going up to around 65 to 70%. So we also had a much higher CPU utilization because we were not waiting anymore, or almost not waiting anymore for accessing main memory, for accessing those pages in the buffer pool. So 3 to 4 seconds, but we are not yet finished.
So Klaus, I have several other kind of follow-on questions that are kind of are trailing off of this conversation. So what about the write log impact by the increased number of log records using GUIDs and a clustered primary key?
Of course, the impact for the transaction log is higher, yes. So you have more write log wait types, but on the other hand, you have fewer waits for the buffer latches. Again, it's a trade-off. So you have to measure it for your concrete example, for your environment.
Sure. And then what about if you remove the begin commit tran, will it be faster or not as fast when you split it across pages?
I have to check that. No idea on that one. I have to check that. But with the scripts, you can try it afterwards on your own, which approaches are faster than the other ones.
Okay, great, thanks.
You're welcome. Let's talk now about in-memory OLTP. I'm not really a big fan of in-memory OLTP because it has a huge amount of limitations, restrictions, and very, very rare use cases where in-memory OLTP really makes sense. But this is my own opinion. But I just want to show you how fast in-memory OLTP can be with the last page insert latch contention problem. As I've said previously, with in-memory OLTP, SQL Server is using internally lock and latch-free data structures. Means when you're working with in-memory OLTP, you have no waits for locks. you have no deadlocks, you have no waits for latches, because there are no locks and latches anymore within memory OLTP. In memory OLTP is just using internally other data structures, and those other data structures, they don't need locks and latches anymore. And therefore you can overcome all those various problems. First of all, when you want to use in-memory OLTP, you have to add a new file group to your database which contains memory optimized data. By the way, as a side effect, when you have added that file group, you can't remove that file group from your database anymore. As I've said, in-memory OLTP has some scary restrictions. So just be aware of that. As soon as you have added that file group, you can't remove it anymore. And then we are just adding a so-called in-memory OLTP container into that file group, and in that container, SQL Server stores in a completely different way, in a completely different format, our data that we are writing to in-memory tables. So what I'm doing, I'm creating now a so-called memory optimized table. All those tables that we have used in the last decades, those were so-called disk-based tables, and those disk-based tables are very, very slow because they were built around locking, blocking, latches, and everything. With memory optimized tables, SQL Server is using a completely different approach, and SQL Server also stores our table data not on pages anymore. There are no pages in memory OLTP. It's a completely new relational engine within SQL Server. So within SQL Server, currently, you have 3 different engines. You have the old classical engine that we are using every day, the slow one, as we have seen. We have the faster in-memory OLTP engine with some side effects and a lot of restrictions. And the third one is the column store index engine for data warehousing workloads. So SQL Server currently consists of 3 different engines. And we are using here now memory optimized tables. Means we are storing that data in memory, but it is also persisted in that file group that we have created previously. So let's create that memory optimized table.
Hey, Klaus, I've got another question for you.
Yes.
So if we're scanning a range of pages, our page latch, page IO latches, oh God, I cannot read today. Our page IO latches
anymore, so.
Acquired and released on a per page basis, or are they maintained during the entire scan operation?
I think they are acquired and released on a page by page basis.
Great, thank you.
So we create here now a memory optimized table, as you see here with that hint with memory optimized on. Takes a few seconds. And now let's create again a stored procedure. This is a traditional DSQL stored procedure. Nothing special. Again, we have our while loop, 10,000 records, and we are inserting into that memory optimized table. Let's run our workload again. So we needed previously around 3 to 4 seconds, and oops. Didn't work. Now we run that again. And trust me, yeah, we already finished. 1.9 seconds. So instead of 3 to 4 seconds with a unique identifier, we are down to 1.9 seconds. When you think back, the int identity column needed 56 to 57 seconds. So we are 30 times faster. Amazing, isn't it?
Yeah, I've got another question for you.
I thought so.
So in memory OLTP, there are no deadlocks, and even in serializable isolation level,
there are no deadlocks because there are no locks. Without any locks, you can't have a deadlock. Quite simple.
Makes sense.
Yeah, I know. So we are currently 30 times faster, but we are not yet finished. Come on. The stored procedure that I have created here is a traditional interpreted stored procedure. Means when we run that stored procedure, the query optimizer generates an execution plan, and that execution plan consists of multiple operators, and they are just called during the runtime on the fly. Means a stored procedure or every execution plan in SQL Server is an interpreted computer program that we are running when we run a query. And interpretation is very, very slow because you're doing that interpretation during the runtime. And this costs you a lot of time. And therefore, within memory OLTP, you have also so-called native stored procedures with native compilation. Means when you create a stored procedure with native compilation, amazing things are happening in SQL Server. Well, let's drop that stored procedure. And when we create now that stored procedure, amazing things are happening. SQL Server generates through the query optimizer an execution plan. And that execution plan is handed over to in-memory OLTP. And in-memory OLTP transfers that execution plan to C program. And that C program is finally compiled and linked to a DLL file, which contains x64 assembly code. And that assembly code is finally loaded on demand into SQL Server. Means when you afterwards execute that stored procedure, you are executing native compiled machine code. So there is no interpretation anymore. So we are running that stored procedure as fast as possible. So more or less, we are compiling out of that stored procedure a DLL file, and that DLL file is loaded into the process space of SQL Server.exe. So we are enhancing the native code base of SQL Server.exe. Just think about it. And all that stuff happens during the creation of that stored procedure. And therefore, it also takes a little bit longer. It's just a little bit longer, maybe 1, maybe 2 seconds. Because now we have created and compiled the DLL file, and that DLL file was also already loaded into the process space of SQL Server.exe. Means when we are running that stored procedure, we're just executing assembly instructions as fast as possible. It's a native compiled program. There is no interpretation of that stored procedure anymore. So let's run that again. Whoops. Finished. 759 milliseconds. Just think about it. 759 milliseconds for 1 million of records. So this is quite fast. Just think back when we initially started with our int identity column, we had an execution time of around 56, 57 seconds. And now we are talking about 661 milliseconds, half a second. Just think about it. So in memory OLTP is amazingly fast. But this doesn't mean that you have now to change all your databases tomorrow or even today, depending on the time zone you are living in, and that you're transferring everything to in-memory OLTP. Trust me, don't do this. You will have a lot of different problems. In-memory OLTP, from my perspective, makes sense in specific use cases. For example, when you have that last page insert latch contention problem, maybe you have some tables which are written heavily, like logging tables, auditing tables. In those cases, in-memory OLTP can make sense. But please do me a favor and don't transfer your whole database to in-memory OLTP. That's not the goal. In some specific use cases, it makes sense, but not for your whole database. So that's the story about last page insert latch contention. As I've said initially, we don't have to blame SQL Server for that problem. It's not a problem of SQL Server, more or less it's a problem of the B tree, of the balanced tree data structure that SQL Server is using internally to represent a clustered and non-clustered index. So even in other databases which are using the balanced tree structure, they have the same problem. It's a problem of that data structure. It's not a problem of SQL Server. But as you have seen, there are some different solutions how you can solve that.
Hey, Klaus.
Yes.
So I have several questions.
Oh my God. I have a lot of time.
Okay. Do you want me to go ahead and start asking these? Because most of these are related to what you just were talking about with your in-memory stuff.
Yeah.
Okay. All right. So let's see. Are execution plans stored and reused as part of natively compiled stored procedure, or just as with a traditional stored procedure?
There are no execution plans anymore.
Okay.
Because you are executing a DLL file. Means you have no recompilations of stored procedures anymore, because they can't be recompiled. You have enhanced the code base of SQL Server.exe.
Okay. That actually answered a couple more that we're following after that. So let me...
I'm a mind reader.
You are a mind reader. It's amazing. So do you still have to write down the data to disk if you need to keep it through the database or for a restart, right? How does that work?
Still persisted data means when you're restarting SQL Server, you have not lost any record, any data.
Let's see. So when using in-memory OLTP as a shock absorber to solve that last page contention, how do you move it to an on-disk table in a timely manner?
You have to recreate the disk-based table, and you have to transfer those records from the in-memory table back to the disk-based table. It's up to you how you do that.
Okay. Let's see. So where does the SQL engine maintain the version of the modified pages for in-memory OLTP?
There are no pages with in-memory OLTP.
Well, then they can't store them anywhere, can they?
It's just a completely different engine, a completely different beast. More or less, you can forget everything that you know about databases. Those are completely new concepts. Just throw away your old knowledge. You don't need it anymore.
Or, man, my 20
I'm just
years
joking.
My 20 years of experience is gone.
Yeah.
In one statement.
Obsolete. It's just obsolete. Everything that we have learned over the last 20, 30 years, it's just obsolete knowledge.
Okay.
Memory OLTP solves all our problems.
Yeah.
Well, that's the thing that Microsoft tells you.
Well, sure it is. I've got a few more questions here. Do you want me to keep going or you
I want to continue now.
Okay, all right.
Otherwise, Thomas will kill me.
Okay, all right. We'll save the rest of these.
And the problem is he's also an Austrian guy and he knows where I'm living. So,
all right, I'll save the rest of these. And if we have time at the end, we can address them then. How's that?
Thank you.
Uh-huh.
Another demonstration that I want to show is about those non-buffer latches. As I've said previously, non-buffer latches are used by SQL Server to protect other shared data structures, which are accessed concurrently across multiple worker threads. And one very, very prominent example in SQL Server is our transaction log. Let's have a look on that one. I create here a new database. And I have set the transaction log for an initial size of 1 megabyte, which is insane. And I have set a file groove to 50 gigabytes. Every time when an autogroove operation kicks on the transaction log, SQL Server has to zero initialize that new chunk of data. Otherwise, crash recovery couldn't work within SQL Server. So there are just internal technical reasons why SQL Server has to zero initialize our transaction log during an autogroove operation. Even instant file initialization doesn't help you here because instant file initialization only applies to data files. The transaction log is always zero initialized. It's always zero initialized. This is very, very important. And during that autogroove operation, SQL Server acquires a latch on the transaction log, a non-buffer latch, and every other transaction which wants to access the transaction log has to wait on that latch. Means during an autogroove operation, your database more or less is just waiting. It's not doing anything anymore. Every transaction that wants to access the transaction log just has to wait. Means during that autogroove operation of 50 gigabytes, we have some time to explore what happens internally in SQL Server when we trigger that autogroove operation. So let's use that database. Let's create here a simple table. And now let's prepare here something. This is now a little bit more complicated setup, but it will work. So just give me a second.
And Klaus, just as a time check, you've got like 10 minutes left.
I know.
Okay.
Well, no, not 10 minutes. It's 11 minutes.
11. All right.
That's a huge difference.
It is a big difference.
So what I'm doing here now is the following. I have here a first transaction, which is just inserting some records. Means when we are inserting records, we have to write those transaction log records out to the transaction log. Our transaction log has a initial size of 1 megabyte. And when that 1 megabyte is fully written, our autogroove operation kicks in. SQL Server has to zero initialize our transaction log with 50 gigabytes of zeros. This takes some time, around a minute in my environment. And during that time, we are trying to insert in a different session another record into that table. Means we are trying to access the transaction log, but the transaction log is currently latched. Therefore, that insert is just waiting on a non-buffer latch on the transaction log. And in the third session, we will use just a few dynamic management views to show you which session is waiting on what. So let's try that. As you see, the insert is waiting. And now, perfect. When we go to our machine, you can see now our disk E, where I have stored my transaction log. We have some activity. We are writing with around 860 megabytes per second zeros into the transaction log, 50 gigabytes. This takes some time. And now we can see our session 83, the simple insert, is waiting on a latch exclusive. That's a non-buffer latch. We are in the suspended state. And when we go to the right-hand side, we have the wait resource. And guess what? Our log manager. We are waiting on accessing the transaction log. Just think about it. And even our session 64, which has triggered our autogroove operation, is also waiting on something. Our session 64 is waiting on a so-called preemptive wait type. preemptive OS wide file gather. Huh? What does this mean? What is a preemptive wait type in SQL Server? A preemptive wait type just means that SQL Server is calling some functionality in the Win32 API. In that case, SQL Server is calling the function wide file gather, which I have here in front of me. It's part of the Win32 API. And during that function call, the scheduler of SQL Server has no idea how long that function call will take. So we are leaving the code base of SQL Server and we are waiting until that function call in the Win32 API is finished. That's a preemptive wait type in SQL Server. We are waiting on the Windows kernel. But as you can see in the status column, we are still in the running state. We are not in the suspended state when we are waiting on the preemptive wait type. A wait on the preemptive wait type always occurs in the running state because we are calling into the Windows kernel and we are waiting until that call is finished. Just think about it. That's a preemptive wait type in SQL Server. Means when you see that wait type, it's a good indication that you have problems with autograph operations on the transaction log. Because we know now when we are triggering autograph operations on the transaction log, we are calling the Win32 API function wide file gather. And as you see, that autograph operation took around 1 minute, 63 seconds. And that simple insert also took exactly 1 minute, because we had to wait until the latch, the non-buffer latch on the transaction log was released. So this is also another quite nice example about a non-buffer latch in SQL Server. And when we now go to the latch stats, we can restrict on the latch class log manager that we also have seen here in the previous diagnostic output. Oops, I hate this. So we have here the wait resource log manager, and that's the latch class. And we can restrict on that latch class in system OS latch stats. And now we know how often we have waited on autograph operations on the transaction log. 72 times since the last restart of SQL Server. And in sum, we have waited for around 127 seconds. So quite easy to find out how often you have waited on autograph operations on your transaction log. So that's another nice example of non-buffer latches in SQL Server. So we have 5 more minutes and I have content for 3 more hours. I have thought this, and therefore I have written some blog postings for you. This was in the year 2014. So almost more than 6 years ago. And I don't want to talk now about Spinlocks anymore because we don't have any time anymore. But everything that I would have told you, you will find it in that blog posting. It's more or less the same thing that I would have talked about. Same content and the same thing about log-free data structures in SQL Server. I was also well prepared in the year 2014. And I will also tell you here in that blog posting everything that I would have told you in that session about log-free data structures in SQL Server. So I had just too much content for 75 minutes, but I assumed that doesn't matter. Okay, are there any other questions which we can handle in 4 more minutes?
Okay. Well, most of the questions that are here right now are still left over from the in-memory discussion that we were having.
Yeah. Go ahead.
So what's the performance for range queries in for in-memory OLTP. One of the reasons why the B tree has this limitation is to maintain an ordering. So are the in-memory OLTP data structures ordered?
No, they are not ordered because you are using internally other indexes. You have so-called range indexes. In a range index, the data is ordered, but in a hash index, which you are using by default, the data is not ordered.
Okay, great.
So based if you want to have ordering, you are choosing that or that index, this or that index.
Okay.
Hash index or range index.
Okay. And then going back to the last page issue. So removing that clustered index or replacing it with a non-clustered index, would that help at all?
It would also help, yes.
Okay.
This would be also a valid solution.
Okay. And then what recommendations on native compiled procedures? Can you use them on normal tables?
No.
Okay.
No. As soon as you have a native compiled stored procedure, I can only access memory optimized tables.
Okay, great.
If you're also interested in more information about in-memory OLTP, I have also a course on my website around 6 hours just about in-memory OLTP in SQL Server.
Wow, and you were going to try and fit all of that into 75 minutes today?
Sorry?
You weren't going to try and fit all that into 75 minutes today?
I don't think so.
You don't think so? All right. And then we have one that's left over from the very beginning. Somebody is just curious about your experience getting your MCM.
I have no idea about it anymore. It's already so
I was going to say that was probably a while
so
ago.
long time ago.
Have you slept since then?
I think I have passed it in September 2012.
Okay. All right.
I was 8 years younger.
8 years
I still had hair.
You still had hair. Awesome. I don't have any other questions right now. So
perfect. So thanks for attending my session. And as I've said previously, if you want to find out more about Spinlocks and log-free data structures, just check out my website, sqlpassion.ad, where I have also those 2 blog postings, which are just having the same content as I would have presented here in that session. Okay, so thanks for attending my session. Thanks for attending the whole online conference. And let's see and hope, or let's hope that we can see each other very soon again in person. So thank you and enjoy the remaining day.
Thanks, Klaus.
Yeah, thanks, Klaus. I do want to ask you though, Klaus, and we talked about it a little bit in the chat. Let's talk about the data rate on that transaction log expansion. It was nearly 900 megabytes a second. What is underneath?
My time is already over. I'm finished. I've already seen that email about the after party. Sorry. The 900 megabytes I'm using here, nothing special. I have here VMware, and I'm using a vSAN data store in the background.
Oh, okay.
With flash devices.
Many flash devices.
Yeah. Anthony, if you were impressed by the 800 megs, you should not attend the next session.
Well, I'm saying I'm working under the assumption.
Talk. Oh, I like it.
I'm working under the assumption that's his home lab and not the stuff that
29 gigabytes per second for log writes.
Right, but that you have probably a different budget than Klaus has in his home lab.
Yeah, I probably spend less on it because I'm not using a SAN. That thing is actually not expensive. I'm not joking. This stuff is not expensive anymore. This is the big difference. It's I unfortunately legally I cannot talk about the vendors and the pricing because that gets us all in trouble. So I avoid that. But
it's okay. You can tell us. No one will know.
Right. Let's stop the webinar for a second.
So if thing is, and I like the lineup today. We had the data compression, which basically deals with high level. Hey, this is my tables. Then we had the query processor. Now, then we had the locks and spin locks and all the in-memory details. And now I'm rounding this whole thing up with okay. And now let's start tuning the underlying hardware.
Totally done on purpose.
It's
Honestly.
almost like we planned it that way.
Yeah.
It actually should have been between Bob and Amit should have swapped, but I get it for him and presenting from India is.
Yeah, because I think it was 7:30 his time when we kicked it off today. 7:30 p.m.
We're going more and more down the stack during the day, and I like that. So.
That's the goal.
Yeah, and yeah, it's where you need to be. I mean, there's millions of machines where stuff that Klaus and I are doing has no effect because it's not needed. But when you need it, these things are very, very helpful.
Yeah.
Hey guys, I gotta drop. This was wonderful, Klaus. You're wonderful. I was sitting here taking notes, so I missed some of the questions when they first came up because I was taking notes. So that was awesome. And
thanks for handling the questions. Thank you.
Absolutely, absolutely. And thanks, Anthony and Andrew and Mark and everybody else who is putting this together. This is wonderful once again.
Angela, thank you so much. A fantastic job.
Awesome. Thanks, guys. I'll see you later.
Thank you.
Thank you.
Bye.
Bye. Thank you.
So all the attendees, you know the drill by now. We've said it a few times. Please do go ahead and leave some feedback for Klaus and the event on that link on the screen there, 8kb.online/feedback. We can only make this event better by hearing from you. So please do go ahead and tell us what you liked, what you didn't like, and give us some comments as well. And so up next we have Thomas for scaling SQL Server beyond 2 CPUs. You've already given us a bit of an introduction, but we'll give it a little bit, and then we'll get started at the top of the hour.
Can I take a poll while we're sitting here?
Oh, absolutely.
So, biggest box. I know Tom's going to talk about beyond 2 CPUs. I'm not sure how many you're going to talk about, but biggest box you've worked with thus far.
Right. I'm currently working on a 96 core, 876 gigabyte system. There's 4 servers like that, which is insane.
Does this have to be production work?
No, I did. I was going to use proof of concept work, which I did on a whatever the highest one in Azure is. So 400.
Where's Joey? Joey.
Yeah, whatever. Joey will probably know it off the top of his head. 400
right?
some vCPUs and 11 terabytes.
Whoa. Jeez.
That sounds like fun. I think that one's just called $signs.
Right.
What was that used for? A SharePoint farm?
No.
Just one.
No.
Just one.
And here's the kicker. Like bigger hardware, Jonathan says this a lot, bigger hardware, bigger problems.
Oh, yeah.
Right?
Well,
So
my experience was on a 128 core box, I think, and it had maybe 3 terabytes of memory. And the bigger problems came in. It was running SQL on Linux. I was running a load test against it, and something happened. Something hung. CPU was pegged at 100%. We had to reboot it. Took like a half an hour to reboot because it had to go through all the memory on boot up. So definitely bigger problems. Yeah.
Yep.
Yes and no. If you know how to configure these machines, all these problems go away.
As usual.
That's why you're here.
To break with my numbers, I'm trying to frame it a little bit simpler. It's 1.75 kilo cores, so 1,750 cores.
Kilo cores. That's a new metric.
New unit.
I'm not good at math, but that sounds like a lot.
What did the licensing people say when you tried to license that?
Thank you.
Yeah.
Thank you.
You license them in kilo cores.
So you declare that development. No, it's the licensing is a yes.
Hey kids, we're going to
things I can
Disneyland.
talk about and things I cannot talk about. If you have a box like this, you should talk to Microsoft about license.
I would imagine the salesperson just calls the yacht salesperson right afterwards,
You're
right?
not talking to the salesperson.
No, probably not.
The sales guy is nice enough to introduce you to the person you have to talk about. No, and don't forget, cores is not equal to CPUs and stuff like that. So there's a lot going on there, and yeah, but it's fun to work on, and we will look at it. But it's
Is that box busy?
yes, I can push it to 100 at any point in time by doing like an index rebuild or so. It should not go busy during normal operations because that's the reason it's that big, so that there's always buffer to do more.
Got it.
Yep. And the funny part on that box, the limit is not the CPUs. The limit for a long time is memory. That box is only constrained by memory.
How much does it have?
No, it's not the size, it's the performance. So it's 32 times.
He's got his calculator.
It's 48
tape.
It was what, Thomas?
48 terabytes of memory.
Wow. How is it cooled? Is there just like a dry ice thing in the fan that's blowing at it?
It's 8 boxes that are just regular, look like a regular server. They are 8 4U boxes. And the reason for the 4U boxes is we choose the option that has more I/O. The I/O is the more impressive thing. I don't know where the limit is yet, but I've seen more than a terabyte per second table scans. So
wow,
that's the thing. You stop using indexes when you can read that fast, because they just do that.
Don't give people bad ideas.
Don't say that.
My
Mark,
hardware
you
is fast enough. I don't need indexes.
Mark, you know when you're doing your editing for this, you just chop that bit out.
No, yes, there's cases so where indexes make a lot of sense, but we use this box for 2 cases. One is high concurrency, and the other one is data warehousing. And on the data warehousing side, we're doing table scans on very, very large petabyte-sized tables. And yeah, we all know when you have to read a petabyte, adding an index to that, it's not going to make a lot of a difference because SQL is not going to choose it. Yeah.
Is it Columnstore?
Some of it is in Columnstore, some is not. It depends. Some stuff is really good. If you need to scan it all, then Columnstore is great. If you need to just scan like portions of it and you can't partition and you can't these segment group eliminations doing for it,
yep,
then Columnstore is not your friend.
I was going to ask if you partitioned it. That was my next question.
Yes. So Columnstore we do no data type can be more than 8 bytes. We pre-sort the data. We insert 1 mega rows at a time, and we learned that. I have a whole talk on it. It was a learned process to get it right. And currently, the largest table has 3 to 4 trillion rows, and grows by several billion a day. And
I think that loading piece is often not understood, right? And then you have your row groups and all of that.
What we do in the loading is we have multiple in-memory tables.
Look at Thomas using all these features, man.
The application pre-sorts the data into the loading tables by grouping it, kind of. Loading. And then once we have a mega rows in there, we sort it 1 more times and then load that into the Columnstore. So by doing that, we could not only reduce the size massively because we have the repeating columns right next to each other, but it's also the partition elimination. So if we have 1 column that we not partition elimination, the segment elimination, we have 1 column. The segment will only contain 1 value.
Yep.
So it's perfect for eliminating it. Yeah, but that takes a lot of energy to get that in. And,
it does.
Yep.
It does. That's a whole session right there.
Yes.
I think we just had a whole session.
Right? That was like a mini session.
I think
I'm starting to think scaling SQL Server beyond 2 CPUs is a little bit of an understatement for what's coming up.
I'm just trying to wrap my brain around the development team, having worked with the database people, to have both things be nice to the other thing. That's nice to hear.
I was just going to say, I think the real missed, the talk everyone wants to hear is how you convince the developers to sort the data before they put it in the database.
Right. So what you normally have is you have application developers, and then you have DBAs, and that doesn't work. What we did is we put a group in the middle that we called database developers. And they had to take the code from the application team and make it database friendly. And then the DBAs didn't kill them. So to use Gail's methods of doing things. No, it's you need people that understand that it's the problem is the developer has the goal to get as many features out as possible, and the DBA has the goal to keep it as stable as possible, and that doesn't gel. Yeah. And if you have that group in the middle that has just one job to make this what they make to run fine here, you get a lot more done here, because you're not spending all day long with fighting issues, because the people in the middle know how to avoid them to begin with. It's not that hard. They just listen to the DBAs, and then they take the stuff from the application group and figure out how to run it by the rules and not just by random stuff.
Listen to the DBAs.
Yeah, it's a hard.
Gonna hold on to that one.
So serving them vegetables in form of beer.
Nice circle back. Nice.
Yeah.
I think all of the database engineers that work with Andrew and I are rolling their eyes at us right now.
Okay, I'm going to stop sharing my screen, Thomas, if you want to grab it.
Click share screen. That sounds good. Let's take this one.
Have a great session, Thomas.
You too. Thank you. Shift.
There we go.
And how would you like to handle questions? I've got the Q&A panel up. So, oh, very good. Oh, I have to remember pictures. Oh, man.
Yeah. So if it looks like this, it's a good point to pause. I will try to pause. If I don't pause, just interrupt me. This slide will repeat a lot during the presentation because I use it to do things. So let's go to the real one.
No problem. Slides are all yours, Thomas.
Yep. Should be.
Crack on. Have a good one.
Yep. So I start a minute early. That's fine. A minute longer I can take. So yes, hello everybody to the last session. I hope you're still with us. And let's see. Oops. What we can do. First thing, I had to change the title of the presentation. I submitted it about a year ago, and it's now, when I was actually making it, I figured out I had to start at a single core and not 2 CPUs so that everybody can follow the whole process. But it's the same session from a content. I just choose to change the title to Beyond 1 Core. Quickly, and I'm pretty sure in the virtual world, this is not going to go well with all the animations. But so a little bit about me. That's my name, Thomas Großer. Same as Klaus, I'm from Vienna, Austria. One difference, I live for the last 8 years in the United States. I work here. I'm with SQL Server almost till the beginning of time. So I started using it in 1994. So 10 years after Wonder Woman. And yeah, I'm busy around, and you can read this on the shared slides if you're interested. So before we start the whole thing about how to look at how to make machines big and responsive, the thing I had to learn over the years is how to compare stuff, because hardware vendors are really nice in disguising what they're actually selling. Yeah? And so the good saying in the English language, comparing apples and oranges, is not always as easy as in this case. Yeah? many cases, I have to deal with stuff like that looks more like this. Or sometimes it's even harder because one disguises inside the other one. And then there's the last and biggest problem I have. If you have a clear apple and a clear orange, and then you give it, it gets like masqueraded behind some obstructions. And that's what I call marketing. So marketing puts a big wrench into it. It's the problem is the louder a company pushes a feature, the more I learn to get suspicious that this might not be the thing that actually helps me. Yeah. And these pictures were not inspired at all by this person. So during the whole presentation, I will always tie it back to 4 workloads I use to explain this. Yeah. One is a machine that should have the goal of have the lowest latency, meaning each individual query should come back as fast as possible, yeah, as thing is. And it might be that this is the case. I often see this where there's only one connection to the SQL Server and there's only one query at a time. Yeah. And everybody's complaining that everything is so slow because, yeah, it's one. And everything is happening once after the other. So low latency machines, if I send a query, I want the answer as quickly as possible. The second one is high concurrency OLTP, meaning I want lots of the first one at the same time. Yeah, I want to have 1,000 people that can click on buy this on our website at the same time. I want to be able to run 500 stockbrokers and deal with each one at the same time, stuff like this. Small queries, lots of concurrent connections, nothing big, everything's quick and small queries, but I want to run thousands of them in parallel. Third kind of category I'm going to talk about is high throughput, basically the data warehouse. I have a large database. I want to read as much data from it as I can at the same time. Usually there's only a few connections at the same time, and they all hammer the machine with scanning through large amounts of data. And the last one is the generic server and the server that you use for virtualization. They are pretty much the same. They're interchangeable from a hardware perspective and point of view. It's the garden variety machine that everybody should use or is using. That's the thing that you want to do. And everything I'm going through, every technique I'm showing during this talk, I will then tell you if it's for which one of these 4 categories this makes sense and for which one it doesn't. Yeah. So before we go through that, we have to work through a little bit of theory, how scaling and parallel workloads works. What can you do to make things go faster? Yeah? And for everybody to understand that, if you attended the previous sessions today, this is picking up where Klaus just left off. Yeah. So we already optimized all our table structures, everything. We optimized the query processor, came up with a perfect plan. We already tuned everything so that we don't have any latches and don't have to wait for acquiring latches anymore. Yeah. We still need the thing to go faster. This is what this talk aims about. Yeah. So we have to talk, what tools do we have in our toolbox? What we can do? We can optimize stuff. Again, we talked about it. We can reduce stuff, which is funny, and not many people actually do that. The best way to speed things up is do less work. Scale up and scale out. Yeah? Optimize is basically get the same amount of work done by doing it more efficient or faster. So you're buying a CPU with higher clock speed, or you're tuning your queries, basically. Reduce is do less work. Find all the useless code in your database that runs for no reason. Yeah, I don't know how many times I saw queries doing the same thing 5 times over, just to at the end have the results combined instead of doing it in one step. Stuff like this. Yeah, and then scale up is goes, hey, take one server, make it bigger, and scale out is buy more servers and find a way to transfer workload across multiple servers. So optimize. You're basically having a certain amount of workload and you run it, oops, you have your workload and you run it piece by piece, yeah? And if you can run it faster, you will save some time. Yeah? So that's the concept of optimizing. Very simple. And trust me, we need to understand this to later on understand what CPUs are doing. Yeah? The second one is reduce. We get rid of a bunch of stuff that we don't need, which again gets the whole thing done faster. Third one, scale up, is instead of doing it one after the other, we're doing it all at the same time. Yeah, great. Problem with that is this is a very rosy and awesomely optimistic approach, because that assumes that these n workloads that we're running in parallel do not depend on each other. It's much more likely that it's going to look like this. This is, on the other hand, the opposite, the worst case scenario, where each and every workload depends partially on the other. There's one worse one. If each and every workload fully depends on the other one, yeah, then it would take the exact same amount of time. But even if it's partially overlapping, thing is, we're still saving some time, but not as much as in the previous case, which is the ideal. So with that, thing is, scale out is basically the same as scale up, with two additional steps, 3 additional steps in there. You have to send the workload out to the different nodes. You get the result back. You have to collect the results, and then you have to combine them. So scaling out overall takes longer, but therefore you're not constrained by the size of your server, what you can put in. And depending on what you're doing, it might be a cheaper approach than scaling up, which over the last 5 to 10 years, I found is no longer the case. When I started doing this about 20 years ago, every time you doubled the size of your server, you basically had a 10x cost increase. That's no longer the case. These days, when you double your server, it's about twice as expensive. And therefore, a lot of things have shifted. So, much more clever people than me came up with a formula that describes what I just explained. It's basically how much parallelism can I get? And I have to plug that in twice. And how many parallel threads can I run? That's this one. And that. So that formula says nothing, but if we visualize it, it makes suddenly total sense. So what does this diagram shows us? At the bottom, and on the x-axis, we see how many cores we have. We have 1 core, we get exactly 1x of performance. That's that little point here. If we have 2, we probably get 2, 4, 8, 16, and then 4096. And what these different colored graphs are is the p-value varies between what I plotted out was 80% to 99%. Yeah. So what this shows is at some point we have diminishing point of return. Yeah. So between here and here, we get like 10, instead of 40 times as fast, we get to 50 times, but we have to do 8 times as much CPU. So we're going from 256 cores to 4096. That makes no sense whatsoever. Yeah. If I can get my workload to be 99% independent from each other, I am getting much longer a reasonable return on my investment. Yeah. If I'm crappy and I don't pay any attention, I'm basically flat out anywhere above 4, 8 cores. Yeah. Yeah. So where does this point us with SQL Server? Yeah. This is what I've experienced over time in the real world out there. Yeah. Well-tuned queries, not constrained by locking and blocking, and things. The red curve is you take SQL Server out of the box, you click next, 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 and you run your stuff there. Yeah. The blue one is you tweak a couple of things when you install it. And the black one is you put a lot of effort into configuring the system and designing. So basically this is today's session, this is, we don't do anything. And you can see this can give you more than a 2x versus I'll just put in the box. Yeah? If you put buy crappy hardware, you're down here, yeah, and you will never go up. Yeah, that is a point that it stays. You might not notice because locking and blocking might keep you down there anyway, which is a different problem for someone else to explain how to solve that. So, how to get from 1 to 32 CPUs without completely messing it up? Yeah. So, long time ago, in a server far, far away, we had CPUs with 1 core, and these were the good times because it was almost impossible to mess up hardware because it worked all the same. Yeah. So I had that 1 core. Whenever that core decided I need to access memory, I can do it. Whenever I have to do IOs, I can do it. I am the happy king. I run 1 thread. The thing is, occasionally I switch to another work, but that's it. Yeah? There were nothing that would stop that core from running. And at this time, the only thing that Intel and AMD at the time were fighting about who has more gigahertz, or back then basically more megahertz on clock speed. Yeah? Then the problem started. Yeah, not the problem. So at some point, even back then, when we just had 1 core, the actual limitation for a database server would have been memory. Yeah, because memory is always slower than the clock speed inside a CPU. Yeah, you can run data between CPU registers much, much faster than you can ever exchange it with memory. Yeah, and we will come to timings later on, but on modern machines, to access memory, it takes about 19 clock cycles. So if all you do is shuffle memory from one place to another, every 38 cycles, you get 1 unit of memory transferred. Yeah? And 1 unit, I'm keeping it vague right now because it really depends on how the system is configured, what that unit is. But worst case scenario, it's 1 byte, but hopefully more. But 38 cycles for moving just data from one portion of memory to another one, which is probably something that a page split would do or something like this. This sounds very, very slow to me. So memory is a problem. For that reason, one thing that the CPU world did is they invented caches. Multiple levels, L1, L2, L3. In the early days, there were even ideas about an L4 cache, which was outside the CPU, like it was a faster memory chip. Things might come back or not. And what they added was direct memory access between the IO devices and the memory. Yeah? Still, we were at times where we still had 1 core, but they started implementing caches because the memory was the bottleneck. And that gave CPUs a massive performance boost. Moving on, we had a 2nd core, and now it gets interesting. The moment we had a 2nd core, all developers had to relearn how to write code, because unless you're running multi-threaded, you're not gaining any performance from 2 cores, because your code would still just run on 1 of them. Problem is, once you started using multi-threading, you had to do all the synchronization. We are back to the previous session with latches, locks, stuff like this to handle this. But even on a lower level, the CPU has to make. Yeah? Just assume this CPU will run some command that pulls some data and has it in its L1 cache. Now, that core runs another command that wants to access the same memory. If we would just pull it again from RAM and put it in the L1 cache, it would still have the old value. Yeah? So even down on the CPU level, the CPUs must have something internal that is like the latch we talked before to make sure that these caches don't hide the data from each other. Yeah. So what would happen is when this core requests the data, that L1 cache would basically ask the other caches, hey, any one of you having that data already? If yes, they would transfer it from there and not from the memory. If in some systems, they would write it back to memory and pull it in again. Yeah, stuff like this. So having multiple cores adds another thing is, yeah. And believe it or not, that costs time. Not much, but it costs. So if you look at a modern CPU, we not just having 2 cores, we have things like 8 cores here, which are in the middle. Then they have the PCI Express interface and multiple memory controllers so that memory can run much, much faster by accessing it in parallel. So if you read a couple of megabytes, it would, the memory controller and the OS would make sure that the data is nicely striped across these memory modules. Yeah. The QPI links are how CPUs are connected to each other. I'm not talking anymore about CPUs that are connected through buses, because that's not the case anymore. That 10 years ago, 15 years ago, that was the case. It's no longer the case. I completely removed all that from all my memory and teachings. High core CPU looks exactly the same, just more of these little cores here in the middle. Yeah. I deliberately choose an Intel CPU here because the next slide will show an AMD CPU in comparison. So what this shows is 28 cores with the same interface. This already shows you that when we go back to this one, that a CPU with more cores will have more overhead because the sharing is between much more cores and the synchronization happens more. Yeah? So how can we use a single CPU for? There's 2 things. If you want the lowest latency machines, that's where you use a single CPU for. No other, if you have more than one CPU socket, you are compromising on latency. And I will explain this in the slides coming right after this. Yeah. And the other one I recommend single core CPUs for, single sockets machines for, is generic and virtualization. If you have the choice of buying a server with 1 CPU and 20 cores, or a server with 2 CPUs, 10 cores each, if you don't want to deal with hardware and balancing and configuration and anything else, if you just want it in the data center, you are better off with a machine that has only 1 CPU, because you will run into less, you will have the gained latency will make up for other shortcomings. Yeah. You still have enough IO, you still have enough of all the other stuffs. Can you push a 2-socket machine to more work? Yes. But again, you need to do something. If you don't, just go with 1 CPU socket. Okay, any questions so far? Nope, moving on. Hyperthreading. We have to talk about it because it doesn't go away. So what's hyperthreading? Without hyperthreading, you have inside the CPU, you have your registers, your flags, everything, and then you have all the little transistors that do your math, multiplications, adding stuff, shifting things around, comparing things, everything. And the thread that runs on that core can access each one of these functions at any point in time they want. If you have hyperthreading, you have 2 of that state machines, and they share the tools basically. So here in your garage number 1, you have 1 mechanic that has 1 set of tools, and whenever he wants to repair your car, he just picks a tool and does it. With hyperthreading on, you have 2 mechanics that have to share the tools. Yeah. Can one mechanic diagnose your 1 engine in 1 car while the other one is messing around on it? Yes, and that's what makes it faster. But if both mechanics need to use the same tool at the same time, one has to wait. And this gives us, from a single thread perspective, you actually get 30 to 40% less performance when you turn on hyperthreading. So this guy here runs on 30 to 40% slower than this guy. If you look at the whole core that has 2 of these hyperthreads, you gain 20 to 40. So if you take these 2 together, you have plus 20 to 40%. Yeah, and the 20 to 40% really depends on what kind of code you're running. Yeah, and this is mostly what I see with SQL Server. Yeah? So from a single thread, you're slower, but overall you're faster. So how do we translate that into our 4 sets of standard workloads? Low latency, no. High concurrency, no. High throughput, yes, turn it on, because high throughput means I'm doing a lot of things in parallel. I'm doing a lot of things here. Gaining these 20 to 40% gains me 20 to 40%. Yeah. And you should also turn it on your generic servers, because most likely you have more like high throughput work than low latency. Questions? Good. So what happens if we add a second CPU? The picture just got way more complex. Before, we just had to deal with concurrency between 2 of these cores. Now we have to deal with concurrency across CPUs. If this guy needs to, let's get rid of this. If this guy needs data that is in this cache here, it has to go to get it. Yeah. Again, it could be, depending on the CPU design, that they go exchange it directly between the level 3 caches, but it now has to go a long path, yeah, to the other CPU. So every time you access memory in a machine that has more than 1 CPU in it, and I'm not talking cores, I'm talking actual CPUs, you will see this. You will get from 76 nanoseconds on a modern machine with average memory thing is, and this goes up and down depending which memory modules you use, which CPU exactly you're using, how you configure the machine. It even depends on how you cool your data center. Yeah, but basically you're going from 76. So if this guy needs to go here, but now it needs to go here, you're going from 76 to 98. If it actually is cross CPU, you are at 139 nanoseconds, which is almost twice as long as before. So you just cut, by adding a second CPU, you cut your memory performance basically in half. Again, in the real world, it's not that. And if you remember earlier this day in the very first session, when we were talking about NUMA nodes, that's why SQL Server was one of the very first applications in the Windows field embracing NUMA. Because if SQL Server can keep the memory of threads that run here, it's going to run and not have to go to the other CPU. They save a lot of time. Let me clean this up a little bit so people understand. Yeah. So this is the big thing when NUMA helps you. NUMA gets you from here to here. Yeah. Which is not as bad of an increase as when you go from here to here. So what happens is, and this is where marketing comes in. If you look, there's 28 core CPUs and there's 56 core CPUs. This is how a 56 core, if you add 2 of these CPUs, this is how it looks like. These QPI things are now no longer dotted because they are actually connecting the things. And whenever we are exchanging data, this is going through these QPI links. Yeah, and yes, everything is self. You have twice as much I/O, you have twice as much memory, but you have the delay if the memory has to go through the QPI bus. There's a throughput limit. This thing is like 3 units wide. Here we have 12 units, so it's a big difference. Yeah? So then, whereas more marketing kicks in. Intel built a CPU that has 56 cores. No, it did not. It just took 2 CPUs and put them in one box. Yeah, the 56 core CPUs from Intel are actually 228 core CPUs that are connected. AMD does the same. AMD's 64 core machine is great, but it's actually 8 core CPUs that sit within the same chip. And if this guy needs to get to memory from here, it has to, and then if it's in this guy's cache, this guy has to do the nasty through there. They cannot just cross access. So this 64 core thing is very different than a 28 core Intel CPU. from a memory access perspective. They're still all good CPUs, don't get me wrong, and they all have their use cases. When you're optimizing for them, you have to be aware where the limits are. So as long as you run a max stop that's within 8 on this CPU, and it can run within here, and then takes out a memory portion that it only runs here, it's perfect. If you increase that to 12 and you have add this, you suddenly decreased your performance massively on that CPU. So this is what you have to think about. Well, it's even funnier when you take these Intel CPUs that are actually 2 in one box. You can actually combine 2 of them, but then what you're actually getting is a design for a 4 CPU machine, which we will talk in detail before. But since theoretically, based on marketing, you're combining 2 CPUs here, but under the hood, you're actually combining. The reason I'm bringing this up is when they had the CPU before, we had these 3 links between the 2 cores, between the 2 dies. Yeah. Now, if you combine it with another CPU, this is down to 1. So whenever this guy needs memory from this die over here, this has now to squeeze through that 1 connection. Yeah? And that furthermore slows it down. So just choosing which one of the CPUs you're using makes a massive difference in when it comes to accessing memory. And trust me on one thing, databases is nothing else than reading and writing memory all day long. The calculations that are done inside a CPU are minimal compared to the amount that needs to go in and out of memory and in and out of storage. Yeah? Databases are not computation high applications. Even if you do some math in your query like thing, yeah, that's nothing compared to the work that it takes to shuffle around the data. So use cases for dual CPU, it's definitely no more low latency. It's not for high concurrency. The dual CPU machine is another good choice for a generic server. If you want less work, you go with the 1 CPU. If you want to do a little bit of configuration work, you go with the 2 CPU box. Just fine, same for virtualization. Just try to stick on one of the 2 CPUs that is in the box and you're fine.
Okay, so we've got a handful of questions that have stacked up here in the last few minutes. So we'll kind of work our way through these. So this one is from about 7 minutes ago, so maybe 4 or 5 slides back. Said, do we know if the hyper-threading instruction sharing works the same way on AMD's simultaneous multi-threading?
Yes.
And it's okay. All right, so there's that. And then we've got a handful more here. So from anonymous attendee, so a 4 CPU, 24 core this hyper-threaded is not an optimal setup. And then in parentheses it says 2.2 gigahertz, which I'm assuming is clock speed there.
Yes, can be. And again, there's use cases for it and there's not. We will talk about the 4 CPUs coming soon. We're only up to 2, so that's a 4 CPU question. But the indirect preview of me showing this one where you have a fake 4 core, fake 4 socket machine, yes, that's bad. That's not good. Yes.
Okay, and then we've got, looks like somebody just picked up one in Slack, which is awesome to see. So we have, I would say 1.5 more. So we'll do this one next and we'll see what you think about the last. It's fairly broad. So this says, are there any tools available that could be used to measure these timings over time? For example, yes. I believe Core Info. Okay, go ahead.
So the one I use it's called Busy, and it's on a website that's called SQLstress.com or .org. I will add the link somehow to the download thingy. Yeah, it's a very simple tool, but it gives you you basically start it and tell it how much memory and how many times in parallel you want to move it between cores. And it does it. So if you say 2 cores, so 2 locations and 1 gigabyte, it moves 1 gigabyte, it allocates a gigabyte on one CPU and 1 gigabyte on the other one, and then copies it from one side to the other, the fastest possible way that CPU can do it. And if you do the same and you give it do this for 64 cores at the same time, it will do the same on 64 cores. And the reason you have to specify the size, if you, for example, put the size in something that's within your cache size, you will see big difference. So you have to understand the tool was not designed for that, but it's awesomely, you can awesomely measure that stuff. Yeah? Because there are very few tools that measure memory performance correctly. You still have to do like 10, 15 runs and then average out the values to get consistent readings, because trust me, moving your mouse can affect the readings. Yeah. It's not like an awesome tool with a GUI that has you click and it tells you everything. But yes, there are tools.
Okay, cool. So we just got another one in. Then I'll give you both of these. I suspect you're going to want to hold the last one till the end. So the broad one is, how do we determine the best hardware configuration? So if you want to hold that till the end, if there's time, that makes sense. There's a less broad one that just came in that says, what's a real gain from hyperthreading on multiple core machines compared to the 20-40% of one CPU you estimated?
It's the same thing. So if you turn on hyperthreading, you get about, you double the number of cores, but you're only getting 20 to 40% more performance. That's what it is. If you have one CPU or 32 CPUs, it's the same thing. Yeah. You're not getting twice as many cycles to execute. You're only getting about 20 to 40% more throughput on the CPUs. You're reducing your latency by about 30 to 40%, but you're increasing your throughput by 20 to 40%. So if you are on a data warehouse, turning on hyperthreading makes total sense. If you're on an OLTP system, hyperthreading will slow you down.
Makes sense. So we've had another one come in. They said you can wait till the end. So I think back to you.
Okay. So 4 CPUs, same picture as before, just without the squares around these CPUs. So this is now the same thing. When you have 4 CPUs, one thing starts, you can only have one link between each one of the CPUs. So if this CPU needs anything from that CPU over there, they can use that link. If it needs something from here, it will use this link. If it needs something down here, it will use this link. Yeah. So now you have 4 independent CPUs running stuff. And as long as each CPU stays to itself, it performs still good. If you start needing to access constant data from the other ones, it starts getting crappy. Yeah. And this is what most people see. When you go from 1 to 2 CPUs, it's not that bad. But if you go from 2 to 4, it's a big difference. First big difference is this is no longer 3 connections. This is just 1. Yeah. So that throttles your throughput. Yeah. And I will talk about this later a little bit more when it comes to storage. Yeah. Because that's even worse. And so that's the big difference here. Yeah. So with 4, you will, if you don't do anything to optimize your system and help it run better, which I will show after I go through all the up to 32 cores, CPUs, you will see massive degradation. And that's what the graph at the beginning showed. Again, we doubled the number of cores, but we're not doubling the performance. We're adding percentage-wise now. Yeah, we're adding 20, 30, 50% on top of what we already had. Yeah, we're not seeing 2x, 4x performance anymore. Yeah, this is we're adding a little bit. Thing is, where it will help you is when you need throughput. Yeah, and you can run it independently. Yeah, just imagine a data warehouse. You run all your customer stuff here. You run your product queries here. You run your regional queries here, and you run something else over here. And each one can run mostly independently, and sometimes have to exchange data. Yeah, this is an awesome setup. Yeah, if you have an OLTP where you're working on the same page as we saw in Klaus's example before, you're trying to insert into the same table, and the table is right now used over here, and then it needs to be here, and then it needs to be here, and then it has to move around all the time. Yeah, that's going to be horrible. Yeah, that's things. Yeah? So if you go to 4, you have to start doing things, and we got through this. I want to stick with just what the CPUs the challenges first before we discuss how we can make it better. Yeah, 8 CPUs, and I now started super simplifying the whole thing because otherwise we'll run out of space on the screen. With 8 CPUs, we now start to not all CPUs are connected directly anymore. Yeah, and this is where it gets tricky. So if this CPU needs something from this one, it's still a pretty simple thing. But if it needs someone from this CPU, it would now have to go here, here, here. No, it's not that stupid. There's always a way to do it with one hop. So it would do this and then go here. Yeah. So one extra hop to get to the other CPU. Yeah. It will not do like something like this. It will never do that. But thing is, yeah. So with 8 CPUs, this becomes an even bigger challenge as before. If you have to transfer data between them, and this is why most people, before the session when we were talking, that people said we had a bigger machine and it just performed crappy. Yes, because if you don't do anything and you just run it like a one socket machine, it will perform crappy. And that's not the question. But if you do something to make it run better, you will get something. Yeah. Now you have 3 levels of memory latency. You have local, remote, and remote via one extra hop. And yes, the bandwidth between CPUs is down to 1/3 of a dual socket. And if you're unlucky, it's even down to 1/6, because you might have that these 2 CPUs want to exchange data, and this guy wants to exchange with this one, which means it has to run through, this one wants to exchange, let's get rid of this. This one wants to exchange too, and they have to run through the same pipe at the same time. Yeah? So then is when you're down to 1/6 each, instead of 1/3 when you just talk to the next one, or if you're the only one talking to the other guy. Yeah? So if you're the only one doing this here, you're still down to 1/3. But if 2 of them need to go at the same time, then you're down to 1/6 of the bandwidth available. And this can become a problem. So we're skipping 16 CPUs because 16 CPUs are basically the exact same as 32. Everything above 8 is basically not supported out of the box. So the Intel CPU has no idea, or AMD stops after 2 CPUs and Intel stops after 8. They have no idea how to connect to more. And some CPUs in the Intel space also stop after 2, and some stop at 4. Yeah. So not every CPU is saying this, but your hardware vendor knows which one. So 32 CPUs. This is how it looks like. I don't know if you can even see it through the internet, but that's how these are configured. It starts very simple. This is basically the same thing as this. Yeah, but instead of being connected with 4 connections to the other side, if you look at this guy, I remove all the stuff here. If you look at this guy has 1, 2, 3, 4 connections to the other guy. And it doesn't matter from which corner you look at it, it's always 4 CPUs are connected in a square, and then they are connected with 4 connections to the other square. If you look at the 32 one, that's the exact same thing. You have the square where each one is connected to the other one, and then you have 1, 2, 3, and 4 into that full mesh that is implemented by hardware made by the vendor. Yeah? And yes, I'm not naming the vendor, but you might figure out who it is. Thing is, yeah? So this is fun. And the interesting part is it's not much worse than 8 CPUs. And I say that lightly. Yeah. Within the 4 CPU node, it's the same as an 8 socket. It behaves exactly the same. If you stay within these 4 CPUs, you have the same behavior as with an 8 socket. It's a 1 or 2 hop connection and behaves exactly the same. If it needs to talk to another node, each one of the 4 CPUs has a direct connection to that ASIC And that ASIC has a direct connection to any other 4 CPU node. Yeah. And here again, it's one thing. Yeah. So that ASIC basically is one more hop. That ASIC is one more hop than the thing is, because it does nothing else. So it has much less overhead in it, and that's what a job does. Yeah. So from its slightly higher latency with that ASIC overhead, which is again a little bit faster than if it would go CPU to CPU. And it has about the same throughput between the CPUs. So that's a good thing. So if you go above 8, it doesn't get worse. It's a big jump between 2 and 4. It's another big jump between 4 and 8, but then it levels out because they're putting a lot of extra hardware in to compensate for the problem. Yeah. And it's very clear, the more sockets you use, the more you have to actively support NUMA. So, questions for 4 and 8 and 32 sockets especially.
Yes. So if we were in person and there was a microphone, you would have a line. So just tell me when to stop and we can kick all those to Slack or something like that. I've got a handful here. So I'll start with Hugo's. Sometimes there are multiple paths between CPUs with the same number of paths. Will it use a single pre-configured path, or will it dynamically load balance between the paths?
So if you have a 2-socket machine, you have, depending on which vendor you use, you have 1, 2, or 3 connections between the 2 CPUs. They will load balance across them. Yeah.
Okay.
Yep. If you have more than 2 CPUs, it's always 1 connection or less.
Okay. And we just got another one, so the line is increasing. So once we hit a point where there's latency internal to the CPU, that latency doesn't manifest itself as high CPU, correct?
So latency within the CPU, you mean when it has to communicate with the cache of another core or something like this? It will kind of show up as high CPU because a command just runs. What all these CPU busy things show you is what they all do is they run an additional thread that only gets cycles if no other threads needs them. So when you hit 100, it means everything's busy all the time. Yeah, and you're getting nothing else. Yeah, so measuring CPU utilization is kind of a reverse thing. You are basically measuring, is the CPU bored and I can do more on it. Yeah. I can run a CPU at 100% all the time, and your SQL Server will not be slower if I run the utility that pushes it to 100, 1 priority level below SQL Server, because it will never get a cycle. But if SQL is not using it, it will immediately pick up. Yeah. So 100% CPU utilization is an indicator something's wrong, but it doesn't really show you things. Yeah. And high latency inside the CPU will definitely show up as more CPU utilization.
Okay, we'll try to squeeze in like 1.5 more here. So Hugo said, had a quick follow-up, said his question was actually about the 8 CPU setup, where the CPUs are connected through 2 paths of length 2. So I don't know if that changes the answer or not, but he wanted to get that in.
In an 8 socket, I've never seen having 2 CPUs with 2 links. No.
Okay, and we'll throw one more in here. And then we'll see for the next break. So somebody asked, what about the Azure 64 and 128 cores that we use for SQL servers? I assume VMs here. How are these configured?
They are pretty much the same as here. They just screw up the I/O part. From a CPU's perspective, they are awesome machines. They just, and we'll talk about it when I come to the scaling the I/O part. They are really bad in doing this.
Gotcha. Okay, yeah, we definitely have some more queued up, but I'm sure you've got slides you want to get to, so we'll shift back to you.
4 and 8 CPU and 32 core machines. They're just for high concurrency OLTP and high throughput. Don't use them for generic servers. Don't try to use them for low latency. It's a waste of money. Yeah. If you don't buy a big machine and then virtualize it. Yeah, that's a crime. Yeah, it should be if it's not. Yeah, I guess. Yeah, small boxes for generic workloads. These big boxes, they have a very specific one. Yeah, I've seen people trying, can we buy one big machine and then put 100 databases on it? Like, yeah, yes, you can, but you can just give me the money and you stay with your current solution and we're fine. Because you will be worse off. Yeah, this is if you have one thing. If you can fully separate, if you have two databases, don't grow the machine. Try to separate them on two boxes. Yeah, this scale up is not the solution for everything. You can scale up, but it takes a lot of effort, and we will get there. So NUMA, a little bit of recap from the morning and looking from it from the other side. So you connect from the outside, from your application server through your database server through a network connection, which is then connected to a CPU and memory, and that grabs somehow to your data. This is the one CPU setup. It's very simple. Every connection comes in here, and every connection uses the same path to do something. Yeah? Most modern machines, if you have 2 or 4 or more sockets, you have the problem, lots of people, and this is where I said most cloud providers mess it up. They still have one network card, which is still connected to one of the CPUs. So if that CPU should run something, that query comes in this way. Yeah, or to be more accurate, it comes in this way. Yeah, but it has to go through the first CPU. Yeah? And for example, if you do that, it might still be fine. But then you run something with maxed out 4 that uses all 4 CPUs, and suddenly you have these CX wait packets. Why? Because the first CPU is much slower in running their 1/4 of the workload. Why? Because it constantly has to deal with the network card. Yeah. And this is where you then see unbalanced workloads, CX packets. I love them. They are not evil. They're just telling you, you are keeping one CPU outside of SQL Server more busy than it should be. Yeah, because if all 4 would run at the same pace and would have enough, the same amount of time for your query, they would finish all 4 at the same time. Yeah. So removing that bad query way of doing things. If you put in multiple network cards, and my recommendation is 1 network card per CPU. Doesn't matter how many CPUs you have, 1 network card per CPU. Yes, if you have 32, it's a lot. And I remember the times in the past where I had a machine with 128 CPUs. Each one only had 2 cores, but still was a lot. We had 128 network cards, and they were all connected at the same time. And queries were spread across them. So the way you embrace NUMA is by you partition your data between the NUMA nodes. So you're basically, a simple partitioning key would now be CPU modular number of CPU. So that gives you 0, 1, 2, 3, 4, 5, 6, and 7. Yeah. And on your application, you do the same thing. You know that a record is in partition number 4 because it's custom ID modulo 8, which translates to number 4 in this example. You know your record is here. What your application server does is it calculates, hey, custom ID modulo 8, that's 4 in our example, and I go to this network card, yeah, which is just, you have 8 connections open to the same SQL server, each one to the other network card that has an independent name, independent IP address, and you come in with the query here. And the next query that deals with the next customer, where the modular calculates out to 6, comes in here. And I think I just threw a lot of stuff that I already have with nice arrows. Yeah, same thing here or here. Yeah, so each one of them, you teach your application, hey, this is a very big box, and we have to talk to it through 8 different doors. Yeah, it's the same thing you would do with human beings. Yeah, you know, you have 8 different departments that do something. You can push all the work to the first department and they hand it off to all the other departments, or you pre-sort your stuff and you throw it to the right department immediately and go there. Yeah. So, can it be perfect? No. Will there be mistakes? And sometimes this guy needs some data from over here. Yes. The emphasis is on sometimes it doesn't matter. Yeah. If it's every freaking time, it's bad. Yeah. If you do the math wrong, and every time you come in here, you need something over there. Yeah. You come in here, you need every time because you have your modulo wrong. You use a different algorithm here than you use here. Yeah, you're screwed. But it's helping it a little bit. Yeah. And you will always have tables that you cannot partition. In this, my example here, I partitioned the customer table because we have much more operations that are per customer. The same would go by orders. Each order is assigned to a customer, so you would partition the orders in the same fashion. But if you look at your products, your items, that would be one table that is randomly distributed between all four, and every time SQL Server needs to join with items, yes, it has to go cross. Again, it's not like you can't do it at all. The idea is to reduce it as much as possible as you can. Yeah? And just choose one partitioning key, help it out against the odd. Yeah? So this is NUMA. Soft NUMA allows you to go one step further. We remember we had the one network card, one CPU, one thing is, but this CPU has multiple cores. So what we can do is, for each core, we can create a soft NUMA unit and assign it with a different IP address or port number to that individual core, and then just access that. So our example before, we did customer ID modulo 8, but let's say we have 8 CPUs with 8 cores each to keep the math simple. That would be 64 individual partitions. We partition the table into 64 partitions and modulo it by 64 when we spread the load. Yeah. The reason for that is that you even further help your CPU by having the chance that the data is in the local cache for that CPU, increase the chances for that. It's still going to be the same memory on the same chip here. Yeah. But the chances, if the same customer comes in the same core all the time, that the data that they need is already there. In a sales application where the typical customer does 1 transaction per day or 1 per week, that doesn't help you. This is for the case where you have this Internet of Things out there. It's that little measurement device that sends you a temperature read every 5 seconds. Yeah? If you push it into the right corner of your big server, there's a big chance that that record is still in the cache from 5 seconds before. Yeah? And if not, it's at least on the same NUMA node. Yeah. So this is where you have to think. Should you do this for your garden variety application where you do a couple of transactions per hour? No. This is for example, doing that spread out. Coming back to Klaus's example before, he tried to insert a couple of 100,000 rows in a second. Doing this, you can push it to insert like 1.5 million rows per second, as an example. Yeah. But you have to do something, because what you're doing is you're basically making each node work independently from the other one, and therefore you push up your scalability by a lot. So I have to talk about latches as well. There's something that very few people see in their lifetime. It's called super and sub latches. Imagine, and I will draw this here, you will encounter them on systems with many NUMA nodes and many cores. Yeah? And what they basically do is they duplicate active pages that are mostly read-only, like index root pages, to every NUMA node. So when we go and we have our individual NUMA nodes with the memory in it, instead of having a page once and each one has to go here to read the same index root page, what they do is they say, hey, we create a super ledge, and then we make a copy of that page on each node, and we're fine. If you need to read that page, all you need is a ledge on your local page, on your local CPU, local memory, and you're good to go. If you want to write that page, if you want to modify it, what you have to do is you have to acquire the super ledge, which basically goes down and acquires a ledge on each and every node. And then when you write the page, you have to write it each and everywhere to copy. Yeah. So don't do this on your leaf pages, and SQL is very clever. So the only thing that SQL Server considers there is basically index root pages. and only stable ones. So it would not, on a small table, if they basically look, is this table modified a lot, then this page modified a lot, then we're not doing it. But if this page sits there for hours and hours with no content change, then this will speed it up a lot. Yeah? They introduced that, by the way, in SQL Server 2008, when they first ran on the Superdomes with 64 cores, and it boosted the performance immensely. Yeah? So SQL does stuff internally to do this. Yeah. So for all reads, you need a ledge on the local copy. For writes, you need a ledge on each one of them, and then do the write n times. Yeah. And again, it's an internal feature, but don't be surprised when you see new ledge types that you've never seen before, because they don't exist on a small box. They never exist on a system with 2 nodes. I've never seen them there. I've started seeing them 4, 8, 16 NUMA nodes. That's where they start making sense. I don't think they make any sense on a 1 or 2 socket machine. 4 and up, they might be around. Good. When should you actively support NUMA nodes? Low latency, yes. If you want the lowest latency, direct your query exactly where your data is. High concurrency, of course. You don't want to influence any other thing here. Yeah. That's it. So, questions?
Yes, there are a multitude. So I'm going to handle one that came out of the Slack channel, because we don't have a good way to record those like we do in here. And that was, how do you assign the NICs to the individual CPUs, and how do you configure that?
Okay, so there's a tool around. If you Google NUMA config tool, it's a little thing that it's registry keys. Microsoft never made it like nice. It's purely hex editing in the registry. Yeah. Someone wrote the tool that is there. I wrote some PowerShell that does it for my setups. It's basically ones and zeros in registry keys that assign them. So it's basically, you take the IP address and you say it. Yeah. The easiest thing is, and if you look at the latest version of SQL servers, like 2016 and up, or 2014 and up, they start using soft NUMA by default by breaking larger CPUs into smaller bricks for the same reason. And they just create the registry entries for you. But there's a tool, there's a GUI where you literally click, I want this IP address mapped here, I want this. And inside SQL Server Configuration Manager, and it's a very bad idea. No, I'm not doing it.
So while you're going through that, kind of the overarching question we have is, there are 9 outstanding questions in the Q&A panel. Obviously, only 15 minutes left. I'll hand you over to Anthony or Rob, I think, here in a minute, because I have a breaking issue that I have to handle. What would you like people to do? So there are records of this. Do you want the organizers to email you questions? Do you want to tackle them in Slack?
At the last slide, I have my email address, and everybody can email me questions after that. I will try to answer as quickly as possible. But if it's hundreds, then it will take a day or 2. And yeah, all the questions that are here, if I get them, I will answer them in like a little document, a text file, and post it right next to the slides.
Okay, awesome. Yeah, there are several. Like I said, there are 9, and as you might guess, they're a bit detailed, some of them as well.
So let's use the 15 minutes to go to the slide deck, and then I'll stay around for questions as long as till they shut down the session. Yeah. So CPU affinity. It's the next thing. If you have a core and you add a schedule, each core has a scheduler on top. That's a one-to-one relationship that never changes. While you run SQL Server, it assigns one scheduler. On the other hand, a query gets assigned to a worker thread. There's many worker threads, way more worker threads than other schedulers. And then SQL Server assigns the worker thread to a scheduler and runs it. Yeah. After a while, when it gets off the scheduler because someone else has run, the next time SQL Server might assign it to a different scheduler. This is when the CPU is not affinitized. This is the normal behavior. The best way to show that is you have a bigger machine with a couple of cores, and you run an index rebuild, and you run other queries in parallel. While the index rebuild is running and you look at your CPU, one is at 100%, because it's doing the index rebuild. And over time, it will move from CPU to CPU. It's really funny to watch because every time the scheduler picks a different one, it's rarely coming back. Yeah? So that's that. And then it goes back to the original scheduler again. Yeah. So what happens, you can affinitize and you can do it through the GUI, or usually when you have bigger machines, you don't want to click 100 or 1,000 times. You want to do it through T-SQL, where you can say affinitize auto is basically, we don't have any affinity set at all, or you can affinitize certain CPUs. That gives you two tools. A, it limits the CPUs this instance is running on. So for example, if you have two instances on the same box, you can give 8 cores to one instance and 8 cores to the other one. By the way, that's the fastest way to virtualize on SQL Server. It's the fastest way. It's faster than running 2 databases on one instance. It's way faster than using any kind of hypervisor. And you can say, you can assign a whole NUMA node and affinitize a whole NUMA node. Yeah. If you have auto, the query while it's running can migrate between all the schedulers and cores. If you set an affinity, the scheduler can only pick the worker thread will only be running on one of the selected cores, and it will stay there, and it will never move. And then you can set the trace flag 8002. That means you are selecting a certain number of cores / schedulers to only use these, but the query, as with auto, can migrate between them. Yeah? And that is important because while on an old TP system, you want to set maxstop to 1. You never want them to go parallel to begin with, and you want to have them stick on the same schedule and not move around. Yeah, but in a data warehouse, you don't. In a data warehouse, you want them to be able to migrate between the schedulers because it might be that much more data is on that other core, and you want SQL Server give the ability to move there. So going back to our slide, in low latency, you want to affinitize again. High concurrency, you want to affinitize. For high throughput, you might not want to affinitize unless, and that's in the next couple of slides. Generic servers don't affinitize. It's just too confusing. So scaling I/O as well. And I have to speed up a little bit to go through all that content. The wrong approach is you have your box, which is 1x in size, which is your baseline, which has 1x CPU memory and everything. What I see most people do, the average is 1x size. What I see is we want to have an 8-time bigger machine. So we give it 8 times the capacity. But we give it 8 times the CPUs, but yeah, memory is expensive, so we only give it 4 times the memory. We use the same network card because the switch won't change anyway. And yeah, if we are really lucky, you get like more connections to your storage array. Yeah, and the latency to the storage array will definitely stay the same. Yeah, and that's not what you want. That's half the speed in the best case scenario. Usually it's even less. Yeah, so that's the wrong approach. This is how people do it for 50 years, and it's so hard when you start in a company to explain to them that's not how you can scale. This will never work. And this is why so many people, they buy a bigger box, say it's crap. Yes, because you did not scale any of the other ones. You only scaled the CPU and your capacity, and that's not how it works. Yeah, yeah, so let's throw that away. I'm going to skip over that. Current storage options, very quick. SAN should not be on the list. If they want to connect, if you talk about scaling beyond anything that has 2 sockets, even with 2 sockets, I wouldn't use it anymore. But anything above that, SAN is your bottleneck, and you will die trying to use it. Yeah. Just to explain, SANs still measure latency in milliseconds. Yeah, even if they use flash. Yeah, they might get to 0.2 milliseconds, but that's not what you do. Is microseconds and nanoseconds. That's how storage latency should be measured these days. With NVMe PCI Express cards, you can do a petabyte in 70 minutes. Yeah, the same thing on a SAN array will take you a day and a half. Yeah, you can with persistent memory, you can do 24 terabytes in about 300 seconds. Yeah, with NVDIMMs, even more, you can do 1.5 terabytes in about 3 seconds. And the reason I didn't list a petabyte here is very simple, because there's a limit how much you can connect. Yeah, so this is current options. For a low latency server, we have our one CPU that we have. We have all the memory modules, and we fill the box up with as much memory as we can, because whatever is in memory is for sure faster than if it's on storage. And then we put in as much storage as we can and we need. And this is NVMe drives that are directly attached. And then we put a network card in the remaining PCI slot. So that's what you have. And that's the basic building blocks. Yeah. So this gives you about 60 terabytes, up to 60 terabytes. If you take smaller drives, you get less. Yeah. 60 terabytes, that's 1.5 terabytes of memory. And that could be 2 times 25 gigabit Ethernet. Yeah. And just to be very clear, that's less than 30K to purchase, including the storage. Yeah. So you didn't hear it from me, but that's the price of that box, including the memory. Sorry, it's not 1.5 terabyte. It's 768 gigabytes, one CPU. You can do the 1.5, but then it's not 30K. You need the newest chips, and they are insanely expensive. If you take out one of the memory chips and you put in one of these NVDIMMs, which is basically a memory chip with a battery glued to it, you can do about 1.5 million inserts, as Klaus showed you before, per second on this box, from multiple threads through that. Lowest latency on inserts possible things. The commodity server, the one with 2 CPUs, is basically the same box with the difference. It's higher latency, twice the memory, twice the disk capacity, twice the CPU. You can go up to 128 cores, 112 cores on Intel, 56 cores if you don't want that tricky core thing. It's the exact same design. The important thing is you have to scale it. So you see, now I have 2 network cards, one on each CPU. I have twice the number of drives. I have twice the number of memory chips. Yeah? Very important, balancing. Yeah? I remember this morning a question that was, we've seen a server, but we only see memory on 2 nodes and we don't see memory on the other 2 NUMA nodes. Yep, they didn't have that configuration where, and this is so common. This is so common from hardware vendors. They give you 2 CPUs, they fill them in memory, but they put all the IO on one of the CPUs because they save you the money of like $25 to give you a second PCI eraser in your hardware. Yeah, this saves you $25, and you just gave away half the IO performance, and NUMA will suck. So don't do that. And this is the worst one, and this is the one I'm referring to this morning. They had 2 CPUs, or they had a case before, and only half of them were populated with memory. That means any memory access from that CPU has to go through the other one. That's insane. Go away. Yeah, don't do that. This is how it should look like. One CPU, half the stuff, the other CPU, half the stuff. Sometimes you can't do it and you have to like have 3 drives here and 4 drives here, something like this, because you're physically constrained. But then you should look for a different vendor because it's possible. And that goes back to the question, how do you find the hardware, the best hardware before? What you have to do is you have to test, or you find people like me that do this for a living. You shoot me an email and I can give you pointers. I can't give them in public because that would be illegal and violate the license agreement that you have with your hardware vendor, because you can't talk about the performance in public. But I can have a nice little email chat with anybody and share my experience in a one-to-one session. So last thing I want to go through, I/O affinity. That's the second affinity you can set with SQL Server. What you have on a CPU, what you want if you have bigger systems, or the moment you have more than one CPU, I/O affinity might help you. On 2 CPUs, not much. On higher ones, yes. So first, what you should do is you should take one core out of the CPU affinity. So if you have 32 cores, define one for I/O, the other 32 for things. This will not affect reading your data files. Your data files will still be done by each core individually. What this means is that the transaction log, the buffer, the memory buffer that is used for the transaction log is affinitized to that one CPU. It will not move around. Yeah? And that means the I/O process that grabs that data from that buffer will be running on that one core, on that one CPU that you affinitize it to. And that should be the CPU that has the NVDIM. Yeah? Because then this is your log buffer in your memory here, and it's on the same CPU as here. If you have your second CPU and your log buffer is over here, and then every time you have to go through the other CPU to write it to that memory DIM, that would be horrible. So let's get rid of that. But if you have it on the same CPU, it's really great. Yeah? So doing that, and then you have your NVMe drives where you actually put the log files. And these drives should also be connected to a PCI bus that is on the same CPU. And then if you're really good and you torture the vendor a lot and they give you an extra registry setting that allows you to affinitize the driver to the same core that you affinitized SQL Server on. So we have SQL, the log buffer, onto one core. We have this on the same CPU. That means that core has probably a cache image of that. And then we have the driver that runs these I/O things on the same core. Yeah? That means your log write goes into a cache, gets duplicated on the NVDIM, but then when the NVDIM gets copied to the drive, the data is already in the cache of the same core and can just be written down here. Yeah? So that massively things. Yeah. So this is how you get to 1.5 million log writes per second instead of 500-600 than you can do on a SAN. So to write that down, 500 versus 1.5 million log writes per second. SAN. This. Yeah. As you have to do. That's log write. That only helps you with inserts. Yeah. And there's a setting inside SQL Server persistent log buffer on. If you have that battery thing, you have to tell it that you have that battery. SQL doesn't figure it out by itself. Thing is, yeah. So you're setting your I/O affinity when you have, again, for low latency, high concurrency, and for high throughput. But for high throughput, you also need to set that trace flag I mentioned before. And if you set I/O affinity, you have to set CPU affinity as well, because it doesn't work without. You cannot affinitize a core that is used by SQL Server for the log buffer. So this one had CPU affinity already. This one, now you need to add CPU affinity if you're planning on doing the I/O affinity as well. If you're just having a big data warehouse where the load and everything is not that critical, don't waste your energy on figuring out how to do that NVDIM and everything else. But if your data warehouse load has limits and doesn't finish anymore, that is a way to fix it on a large box. This, I'm just gonna skip over it. I'm thinking is, yeah. One more important thing, if you have like this 8 CPU setup where not every CPU is connected directly, and you need to do a RAID between 2 drives, which is done in software RAID on these big boxes, which is much faster than a SAN. You can either hook up the 2 drives to the same CPU, or if for any reason you don't want them on the same CPU for redundancy reasons, because you might want to have the connector redundant, you can connect them. You should connect them to 2 CPUs that have a direct connection. So here and here. If you connect them to 2 CPUs that are not directly connected, your RAID software will suffer massively because it constantly has to go through hops to synchronize the data. Yep, that's just a tip. Unfortunately, we're running out of time massively. That's the direct attached storage, how you can double the capacity by using PCI Express switches for your data. It also gets the thing up. Yeah. So, questions. Thank you for listening. I don't know who is still here.
So Thomas, firstly, truly super end last session. That's definitely done some mind melting. We have a few thousand questions.
Yep.
So as you know, Matt had to leave us. So I'm going to start with the one that
I'm going to regret this, but look here. So this is my email.
I'm going to start with the one that I can understand, which is, can you explain how max stop setting translates to NUMA CPU cores hyperthreading?
So first of all, if it's high performance, there's only one max stop setting that you should use, max stop 1. Yeah, and let me explain that. Yeah, max stop tells max stop 1 on an instance level tells SQL Server, don't bother figuring out if this query should go parallel or not. Just don't run it parallel. Just run it as a single thread. That doesn't mean you shouldn't run parallel queries, but you should not waste SQL Server's time to figure that out. You have a massive big query, put maxstop equals 64 if you have enough cores to do that, or maxstop equals 8 at the end of the query as a hint. That's one of the hints I'm agreeing, because you're saying this is a big query. I know it's going to take a lot of juice to run it, so I'm requesting more. And even if you have maxstop equals to 1, you can still run a maxstop equals 8 query if you put the hint in. Maxstop 1 is not limiting you. If you set maxstop to 1 on resource governor, that's a different story. But again, then you're not in the high performance business. So maxstop on the machine. The problem is your developer figures it out once. Yeah, that's a big query. We use multiple threads for it. It makes sense to run in parallel. Yeah. But why would you ask SQL Server to figure this out every time it runs a query? And especially in the mixed workload systems where you have thousands of small queries and then one large one. Yeah, because look at most OLTP systems. Yeah, they run both small and large queries, but the large queries are rare. They don't happen often. Yeah, get the developer to put the maxstop 8 in, and the thing is, yeah, how much should you have maxstop? You should never have a maxstop larger than 1 NUMA node, because then SQL Server can still run it within 1 NUMA node. If you go above 1 NUMA node, you will have funny effects. Yeah, that goes for queries. If you do an index rebuild, go maxstop whatever your system allows you to do. Yeah, because you want that out of the way as quickly as possible. You don't want your system be hold up. Thing is, because you're probably blocking and locking everything anyway. So let's get it done as quickly as possible. But for normal queries, I would not recommend going above a single NUMA node. If you only have 1 NUMA node, I would not go above half the number of cores, because the problem with parallel queries is they only work to your advantage if each portion of the query can be done independently in about the same amount of time as the other portions. And if this is not possible, so if you already have a query that pegs one CPU to 100%, and then you run a query with maxstop of all your cores, that one core will not get any work done. But SQL Server will schedule the same amount of work for that one core, and then you see these hours and hours of CX packets, meaning the other cores are waiting for this one to finish, which they're not actually wasting time. They're just telling you, yeah, we're waiting for this guy. We're doing other stuff. Yeah? But it's the problem. Yeah? And I get it that maxstop makes lots of queries faster when you run them in parallel, but in the high-end business, you specify it on a per query basis. That is much more efficient than doing it in a general way. On your garden variety general server, yes, pick a number that is not too high and not too low. In most machines that I work with, it's somewhere between 4 and 12, maybe 16. And we're talking about boxes that usually have between 2 and 3 times as many cores as that maxed up value is.
So we've learned something from the session, and we've learned that 2 CPUs is better than 1. So Anthony's going to ask the next question.
So, oh, okay. So, now that was the joke. I missed the joke. I was like, wait, there's no question in this list about 2 CPUs. All right. So generally, there's a couple patterns in the questions to cover. Do you want to offer any? You can pick which one you want to go after. Do you want to offer any guidance about how to apply these techniques to virtualization? Because we're talking a lot of questions around how you scale out or up in virtualization. And the other kind of main theme in the questions, Thomas, is can you describe how you have applications connect to those multiple NICs when you had that distributed network card scenario down into the separate memory controllers and processors? If you want to grab either one of those, go for it.
Yeah, so I do both. So first one is the virtualization. In a dream perfect world, if I would have to build virtualization from scratch, I would take a box with one CPU with as many cores as that CPU can run, put all the memory I can squeeze in on that box, and then since it's virtualization, I have to deal with SAN because otherwise you can do all the vMotion magic and everything. Put as many storage controllers in that box as I can, yeah? And then put a hypervisor on top of it, and then you can define VMs in any size, and you will have no issues. Yeah, because you have one CPU, and you split it between whatever you virtualize on there. Yeah, then that's a no-brain configuration, and this will give you the most juice out of the box. I get it that for density reasons, lots of corporations want to add a second CPU here. Yeah, the problem is if you have that scenario, you have 2 options. You have an option that you take a VM. If you have then 2 VMs, that you run the VM, one VM on this CPU and the other VM on the other CPU. Yeah. CPU. That's one option. And that might be great. And you're certainly getting it. The other option is that you take that away and you take half the cores from this CPU and half the cores from the other one and run both VMs here. And people like Alan Hurt and David Klee have written hundreds and hundreds of pages of white papers that explain why you should do either one or not do either one of them. Yeah, it's if you're in a virtual world and you see constantly performance issues, try thinking about maybe virtualization is not the right thing for that workload. I get it. Some places want you to do virtualization because they want to do everything the same way. But then think if you constantly still have performance problems, use one. When you do virtualization, when you create the virtual machine, it's very clear. You have to tell the VM the setup. Yeah. So in the first setup where we had a 1-to-1 mapping, you would say it's one NUMA node, it's one CPU in the virtual machine. In the other one, you would tell it it's 2 CPUs and 2 NUMA nodes. Yeah. So you create it that way. Yeah. You can still have just one CPU and create 2 NUMA nodes virtually. That will still work as a better. The second problem is if you run multiple CPUs on the hypervisor, the bigger the VM gets, the harder it gets for the hypervisor to give you all the cores. The problem is if you are on a VM with 16 cores, they can't give you 15 because they don't have more right now. They need to give you all 16 while you're running. And that's a big problem sometimes. I personally so in production, what I advise all my customers is don't oversubscribe CPUs to begin with. That means I do the same thing as Microsoft does in the cloud and AWS does. 1 or 2 cores are reserved for the hypervisor. They do not get assigned to VMs. And if then, for example, I had 64 cores to begin with on the box, I assign up to 62 cores to the VMs. And the total number of cores in the VM cannot exceed 62. Yeah, that's just for production, because I don't want to deal with oversubscribed CPUs to begin with. Development environment, totally different story. Yeah, 200 VMs on one box with 10 cores, we're good. Yeah, write better code, it run faster. It's training, but yeah, it's a,
if it runs well there, it'll run well in production.
Thing is, yeah. If you need to go above, I usually don't see much gain to go from 8 to 16 or so, because then the problem of not getting all the cores and waiting for it just runs pretty high the risk. So the other question was, what was the second one?
Basically, how do you get applications to connect to any one of those independent NICs to guarantee that
this
you're
is
hitting
really
a
hard to
specific
show on a
minimum?
workstation, but I try. I try, and this is, don't do demos without doing this. Where is this freaking thing? Now you see all the secret tools I'm using. No, it's on the server. It's this nice little thing. I think it's computer management. I hope it's there. Hello. Yes. So, and you probably can't even see that in my screen share, but if you go there, SQL Server Configuration Manager, and I hope you see I have way too many instances installed. Yes, but that's not a running one. Yeah, but that shouldn't matter. So if you go in SQL Configuration Manager, and in the network part, the TCP/IP protocol, you see these IP addresses over here? You can create new ones in the registry, and when you create them in the registry, you can add more IP addresses. My tip is, if you don't want to deal with the registry, add all the IP addresses to your network card before you install SQL Server, because then SQL is really nice and creates all the entries for you. If you forgot that, you will be sitting in the registry and typing hex numbers for a long time. But once you have that, you can do and say, for example, this one, IP7, which is, let's take a TCP/IP. So this one, IP4 port. And what you can now do is, so this would go to NUMA node 4. If you do the angle brackets and the 4 here.
What?
Yes. So everything coming in, it's Microsoft. It was a quick hack. So this is everything to that IP address goes here. But then you can do, oh, I want port 1500 goes to 4. Port 1600 goes to 5, and so on. Yeah. So, yes. And again,
all I can do is laugh.
Right.
It's painful. The nice thing is you can do all that from PowerShell.
Okay.
The problem is PowerShell is not designed to do that, because all PowerShell do is call read registry and write registry, because this is all registry entries. Yeah. So I have to talk with the company I wrote this for if I can share it. If you're interested in actually doing this, give me a call. It's about 600-700 lines of PowerShell, where you have a nice little config table in a SQL Server that says this IP address goes here, there, and then this PowerShell reads that configuration nicely from the table, connects to that machine, and does all the matching in the registry, and then reboots the box, and it comes up again and works or not. So far, it worked all the time, but it adds all the nodes, it removes it. It's tedious, but it's not rocket science. It's 5 or 6 registry values per NUMA node, and that's it. Yeah. But anyways, yeah. So yeah, that's basically how you do that. Sorry for the small font, but I have a large monitor. So and thing is, but so to show this a little bit better, let's use the newest documentation tool. So for everybody. So it was basically, if you do this, it would connect to NUMA node 4. This would take port 1433 to 4, and then 1435 to NUMA node number 6, and so on. Yeah? And how small you make your NUMA nodes. Normally on a 2-socket machine, you have 2 NUMA nodes. But if you add soft NUMA, you might have 16, 32, whatever NUMA nodes. I would not go above 64. And that is just experience that lots of tools and Microsoft development code has issues when you go over 64 NUMA nodes. So don't break 1,000 server, 1,000 core CPU into 1,000 NUMA nodes.
So we only have about 3,000 more questions, but Andrew's on top of 9:30 on.
We are at the end of the event now. We have 1,000 more questions for you, but as the old saying goes, leave them wanting more.
Right. And we will get the questions to you.
We will get the questions to all the speakers. I'm just going to grab the screen here.
Yeah, I will upload the slides in the next 5-6 minutes to the Git thingy.
Fantastic. So we have, please, for all the attendees that are still there, please leave feedback. Let us know what you liked, what you didn't like, any comments, things like that. And then we have all of our resources here. So right at the top there is the GitHub, where everyone will be uploading all the content for their sessions. We have the YouTube channel where the streaming live will finish, but the whole event will still be there, because I'm pretty sure some people will want to rewatch the sessions, myself included, just to actually get a handle on some of the stuff that was discussed. We have a web page, or on Twitter, our email address. Everyone's in the Slack, and then again the SQL community, the feedback at the end there. So just want to say a massive thank you to all of our speakers, all of our moderators. We can't put this event on without you. You've done a fantastic job today. The sessions have been fantastic. The engagement that we've had on the Slack channel and in the Q&A has been unbelievable. And finally, just want to say thank you to all the attendees for coming up and watching the sessions that we've put on. Anthony, Mark, have you got any comments?
I think you covered it for me. I think, but my one thing I did want to call out is just, I think the interaction today between the community, the speakers, and the moderators, that was, I felt super fantastic. So it kind of made today special. Get a little misty, right?
I would, I'd agree with that. Having a hard time forming words at this point in the day. So
you think?
I will leave it at that. Thank you for everybody for coming.
It's been 7.5 hours of absolutely amazing content. So I think we're going to sign off now. We're going to say thank you once again to all the speakers, the moderators, and yourselves, the attendees, and we will be back.
All right.
Bye now.
All right, thank you, everybody.
Yep. So.
In your own time there, Mark.